See, thinking about these ideas can shift our perspective. When you next watch cream swirl into your coffee,
thinking about
you
these
can see it
ideas
not
can
just
shift
as
our
a simple
perspective.
act of mixing,
When you next watch
but as a
cream swirl into
manifestation
your
of
coffee, thinking about
probability
these
and missing information. You are witnessing the system move of your own map. It is a beautiful, everyday demonstration of one of the deepest principles in the cosmos playing out in your coffee cup. So, let us continue our exploration with a sense of wonder. The universe does not give up its secrets easily, but by asking these deep questions, we expand our own understanding. We learn to appreciate the hidden layers of reality that lie just beneath the surface of our perception. The relationship between the quantum world and the classical world, between information and reality, between the observer and the observed, is where the next great scientific revolutions are likely to be found. The mystery of time is not a closed book. It is an open invitation to look deeper. The link between entropy and information becomes even more profound when we consider the role of the observer in quantum mechanics.
And information
In the quantum world, the very act of measurement, the act of many possible states at once. When we measure it, this cloud of possibilities collapses into a single definite outcome. When we measure information about the other possibilities is effectively lost to us, and this act of observation can look like an irreversible event. This suggests that the arrow of time may be deeply entangled with the act of observation itself. Perhaps entropy increases for us because we are constantly interacting with the world, making measurements. Perhaps entropy collapsing quantum past to an unknown future is merely an illusion. What if the arrow of time, which seems to point so stubbornly in one direction, is not a fundamental law of the universe, but rather a consequence of what we as observers are able to see? This question invites us to journey from the grandest cosmic scales down to the impossibly small realm of individual particles. It asks us to reconsider everything we think we know about cause and effect, about beginnings and endings. A star explodes in a brilliant supernova, scattering its elements across space. But we do not witness those elements rushing back to remake the star. This directionality, this forward march is what we call the arrow of time. It is the narrative thread that connects every event. This arrow seems to be governed by a powerful principle, a rule that appears to hold sway over everything, from a cup of coffee cooling on a table to the ultimate fate of galaxies. This governing principle is known as the second law of thermodynamics, and its central character is entropy. Entropy is often described simply as a measure of disorder or randomness. The second law states that in any isolated system, the total amount of entropy seems to be the engine driving time's arrow, looks so different from the future. A state of higher entropy. It is the reason why yesterday's order inevitably gives way to tomorrow's mess. And so, we perceive time as a story of decay and dispersal. We watch mountains erode, buildings crumble, and memories fade. The universe itself seems to be on a one-way journey from an incredibly ordered state at the Big Bang towards a final uniform state of maximum entropy, often called the heat death of the universe. This perspective is powerful, and it aligns perfectly with our everyday experience. But what if this experience, this perception of a one-way street, is hiding a deeper, more subtle truth about the nature of reality? To understand the arrow of time, we must first become familiar with its constant companion, entropy. Let us paint a picture. Imagine a brand new deck of cards, perfectly ordered by suit number. This is a state of very low entropy. It is highly organized and predictable. Now shuffle that deck just once. The order begins to break down. With every shuffle, the system moves towards a state of higher entropy, greater disorder. It is far more likely a shuffled deck will be randomly mixed than perfectly ordered. This simple example reveals the statistical nature of entropy. It is not that a shuffled deck cannot return to order, it is just astronomically improbable. There is only one way for perfect order, but countless trillions of ways to be disordered. The universe, an immense deck of particles, is constantly shuffled. It moves from less probable ordered states to much more probable disordered states. This is the second law of thermodynamics in action, overwhelming probability. You place an ice cube into a glass of warm water. The ice cube is a small region of order, molecules in a crystalline lattice. The warm water is more disordered, molecules moving freely. Inevitable, heat flows from the warm water to the cold ice, and the ice melts. The ordered ice molecules mix with the rest, and the system settles at a uniform, lukewarm temperature. Total entropy, overall disorder, has increased. We never, ever see the reverse happen on its own. Now, let us zoom in, leaving the world of melting ice shuffled cards behind. Let us travel down to the microscopic realm, the world of atoms and subatomic particles. Here, where the fundamental laws of physics play out, we find something astonishing. The rules that govern interactions of these tiny constituents are time-symmetric. That means the equations work just as well forwards as backwards. The laws themselves do not contain an arrow of time. They have no preference for past or future. Imagine filming a collision between two billiard balls. Imagine two atoms. Play the film forward. You see them approach, collide, bounce away. Run the film in reverse. Approach from final paths, collide, move back along their initial paths. This question is old. 19th century physicist Johann Loschmidt posed it. He said, if every atom's motion is reversible, the gas's behavior should be reversible too. A gas expands to fill a container, increasing entropy. But there exist initial velocities that would make atoms gather back, decreasing entropy. So why do we only see expansion? Why does nature seem to forbid large-scale entropy decreases? The answer emerges when we see the gap between microscopic reality and macroscopic description. Time-symmetric laws apply to the precise state of every particle, exact position, exact velocity. But we never have access to that complete information. We do not track every one of the trillions of atoms in a gas. Instead, we measure bulk properties: pressure, volume, temperature. These macroscopic descriptions are coarse-grained averages. This is where the illusion of irreversibility begins. A single macroscopic state can correspond to an immense number of different microscopic arrangements. The connection between entropy and our lack of knowledge is one of the most powerful ideas in modern physics. This concept was formalized in the 20th century by Claude Shannon, the father of information theory. He showed that entropy is not just a measure of physical disorder, but also a measure of missing information, or uncertainty. The more microstates that could correspond to the macro state you observe, the less you know about the system's true configuration, and therefore, the higher its entropy. The second law of thermodynamics can thus be rephrased in a striking way. It becomes a statement about our knowledge. It says that as a system evolves, it tends to move into macroscopic states consistent with a larger number of microscopic arrangements. Because we are ignorant of the precise microstate, this evolution looks to us like an increase in randomness and a loss of order. The arrow of time, from this perspective, is not an objective property of the universe, but a consequence of the coarse-grained, incomplete way in which we perceive it. It is an arrow of increasing ignorance, you know. Imagine a vast library containing every possible book. One book is a perfectly written story. All the other books are random collections of letters. If you pick a book at random, you are overwhelmingly likely to pick one of the gibberish ones. Similarly, the universe in its evolution is moving from a highly specific, low-entropy state, the single-story book, to one of the vastly more numerous, high-entropy gibberish books. It's not that the laws of physics forbid the gibberish from rearranging into a story. It's just that there are so many more ways to be gibberish. This information-based view of entropy changes everything. It suggests that if you could somehow know the exact position and momentum of every particle in the universe, the concept of entropy would lose its meaning. For such an all-seeing observer, the universe would be like a perfectly functioning machine, evolving according to time-reversible laws. There would be no arrow of time. The past and the future would be equally determined and accessible from the present state. The feeling of flow, of a past dissolving into an unknown future, is a product of our limited viewpoint. The past and the future would be equally determined and accessible from the present state. The feeling of flow, of a past dissolving into an unknown future, is a product of our limited viewpoint. The mystery of time is not a closed book. It is an open invitation to look deeper. This journey into the heart of time and entropy can feel abstract, but it touches upon the very fabric of our reality. It challenges us to see the world not just as a collection of objects, but as a dynamic interplay of information and observation. The ideas we have explored suggest a universe that is far more subtle and interconnected than it appears. If you find these concepts as fascinating as I do, take a moment to engage with them further. Pause to consider the implications. And if you enjoy explorations like this, which connect the cosmos to our own experience, I invite you to subscribe and join us for future journeys into the mysteries of science. The thought that time's arrow is tied to information has profound consequences. It means that every act of forgetting, every loss of a record contributes to the forward march of time. Our memories, which are stored information about the past, are what create a personal sense of temporal direction. We remember the past, but not the future. This asymmetry of knowledge, this informational divide, may be the most intimate experience we have of the second law. We are, in a very real sense, information processing beings swimming in an informational sea. Thinking about these ideas can shift our perspective. When you next watch cream swirl into your coffee, you can see it not just as a simple act of mixing, but as a manifestation of probability and missing information. You are witnessing the system move into a more likely, higher entropy state because you cannot track the motion of every individual molecule. The seemingly irreversible act is a reflection of your own macroscopic viewpoint. It is a beautiful, everyday demonstration of one of the deepest principles in the cosmos playing out in your coffee cup. So, let us continue our exploration with a sense of wonder. The universe does not give up its secrets easily, but by asking these deep questions, we expand our own understanding. We learn to appreciate the hidden layers of reality that lie just beneath the surface of our perception. The relationship between the quantum world and the classical world, between information and reality, between the observer and the observed, is where the next great scientific revolutions are likely to be found. The mystery of time is not a closed book. It is an open invitation to look deeper. The link between entropy and information becomes even more profound when we consider the role of the observer in quantum mechanics. In the quantum world, the very act of measurement, the act of gaining information about a system, can fundamentally change it. Before we look, a particle can exist in a superposition of many possible states at once. When we measure it, this cloud of possibilities collapses into a single, definite outcome. Information about the other possibilities is effectively lost to us, and this act of observation can look like an irreversible event. This suggests that the arrow of time may be deeply entangled with the act of observation itself. Perhaps entropy increases for us because we are constantly interacting with the world, making measurements, and collapsing quantum possibilities. Each interaction leaves us with a definite record of one outcome, while the information about what could have been is scattered and lost. Our reality, the one we experience, is a long chain of these irreversible seeming measurements. The arrow of time might be the trail of these collapsed wave functions we leave in our wake as we move through the quantum realm. Consider quantum entanglement. Two particles linked so their fates are intertwined, even when they are far apart. If you have an entangled pair and only observe one particle, your knowledge of the overall system is incomplete. The part of the system you are ignoring will seem to grow in entropy from your perspective. Some physicists propose the thermodynamic arrow of time emerges for any subsystem of a larger, time-symmetric quantum universe. We, as observers, are always subsystems. Therefore, the irreversibility we see, the breaking egg, the melting ice, the dying star, might be a shadow cast by our own limited interaction with the whole. The universe as a complete, closed quantum system may be evolving in a perfectly reversible way, like a timeless quantum computer processing information. But we, as parts within that system, can only access a fraction of that information. The entropy we measure and the time we experience are features of our particular, partial perspective. They are real for us, but they may not be the ultimate reality. We arrive at a place of profound mystery and hopeful curiosity. We began with the simple, everyday experience of time flowing in one direction. We journeyed through the statistical nature of entropy, the time-symmetric laws of the microscopic world, and the deep connection between entropy and information. The picture that emerges is one where the arrow of time is not a rigid, fundamental law etched into the cosmos, but rather a perceptual phenomenon, an emergent property that arises from our interaction with a reality far more complex than we can fully grasp. This perspective does not erase the second law, it reframes it. The law remains an incredibly powerful and accurate predictor of the world we experience. Engines will still run, stars will still burn out, and our coffee will still get cold. But understanding its potential origins in information and observation opens up new frontiers. It suggests that the boundary between the knower and the known, between mind and matter, may be more blurred than we ever imagined. The arrow of time may be pointing not from a universal past to a universal future, but from what is known to what is unknown. This leaves us with a gentle yet deep question. If the arrow of time is indeed a feature of observation, a consequence of our limited knowledge, then what is the universe like when no one is looking? In a cosmos without coarse-grained observers like us, would there be any distinction between past and future? Does a river truly flow if there is no one there to see which way the water is going? The universe might be a vast, timeless quantum state, a shimmering ocean of possibilities where the concepts of before and after have no inherent meaning. And so, we are left to wonder. Perhaps reality is a participatory symphony, and the flow of time is the melody that we, the audience, create by listening. Our very existence as information-gathering beings might be what crystallizes the timeless quantum foam into a story with a beginning, a middle, and an end. The mystery of time is not just a puzzle for physicists, it is an invitation for all of us to contemplate our own place in the cosmos. What is the true nature of the river we call time? And what role do we play in charting its course? Maybe the arrow of time isn't a property of the universe, but a shadow cast by our own observation. The mystery of time is not a closed book. It is an open invitation to look deeper. Right now, you are sitting still. Or so it seems. But the truth is far more dramatic. You are hurtling through the vast, dark emptiness of space. You are moving faster than any bullet ever fired, faster than any rocket ever launched. Right at this very moment, you are traveling at 1.3 million miles per hour. This is not science fiction. This is your reality. It is the speed of our entire solar system, our sun, our Earth, all of us, carried on an unimaginable journey through the cosmos. We feel nothing of this motion. We wake up, we drink our coffee, we live our lives, completely unaware of the tremendous velocity we possess. This incredible speed is not our own. We are passengers, adrift in a current far grander than any ocean. Our planet is caught in the gravitational pull of our sun. Our sun is caught in the immense gravitational embrace of our home galaxy, the Milky Way. It is a river of stars, gas, dust. We are but one tiny vessel swept along in its flow. The journey is silent. It is constant. It has been happening for every moment of your life and for every moment of human history. The ground beneath our feet feels solid and stable, a fixed point in the universe. But it is an illusion, a beautiful deception. We are, and have always been, cosmic travelers on an epic voyage. So, a question arises. Where are we going so fast? And what is this immense structure that carries us with such purpose? We look up at the night sky and see a faint, cloudy band of light. Our story begins long ago, in the deep, silent darkness of the early universe. Nearly 14 billion years have passed since the Big Bang. In the aftermath of that singular moment, the cosmos was a very different place. It was a hot, dense soup of particles and energy. There were no stars, there were no planets, and there were no galaxies. There was only a vast, expanding fog of hydrogen and helium gas, but it was not perfectly uniform. Tiny, almost imperceptible fluctuations in density existed within this primordial mist. These were the seeds of everything that was to come, planted in the first moments of time. Over millions of years, gravity began its slow, patient work. It is the great sculptor of the cosmos. The denser regions of gas began to pull in more and more material from their surroundings. They grew larger, more massive. These were the proto-galactic clouds, the ancestors of the galaxies we see today. Imagine countless wisps of cosmic smoke swirling and coalescing in the dark. Our own Milky Way began as one such collection of gas and mysterious dark matter. It was a formless entity, slowly but surely gathering the raw materials needed to build a city of stars. It was a promise of light in a universe that was still almost entirely dark. The first stars ignited within these collapsing clouds. They were giants, blue, brilliant, and living fast, violent lives. Much larger than our own sun, they burned through their fuel in only a few million years. When they died, they exploded in cataclysmic events called supernovae. These explosions were not just endings. They were also beginnings. They scattered heavy elements, forged in the hearts of these first stars, out into the surrounding gas. Carbon, oxygen, iron, the very elements needed for planets and for life, were seeded into the galaxy. Our galaxy was enriching itself, preparing the ground for future generations of stars, and eventually, for us. So, what is this structure we call home? From the outside, our galaxy would look like a vast, spinning pinwheel of light. It is what astronomers call a barred spiral galaxy. At its heart is a dense, elongated bar of older, yellowish stars. This bar acts like a cosmic traffic director, funneling gas and dust from the outer regions toward the galactic center. It is a place of intense activity, a bright, bustling hub from which the rest of the galaxy extends. This central bulge is ancient, containing some of the first stars to ever form in the Milky Way. It is the Old City, the historic core of our stellar metropolis. Extending from this central bar are the magnificent spiral arms. These are not solid structures. They are more like cosmic traffic jams. They are density waves, ripples of higher gravity that sweep through the galactic disk. As gas clouds pass through these arms, they are compressed. This compression triggers furious bursts of star formation. This is why the arms are so bright. They are illuminated by the brilliant blue light of hot young stars. Our own sun resides in a smaller, partial arm called the Orion Spur, nestled between two larger arms, the Sagittarius arm, the Perseus arm. We live in a relatively quiet, suburban neighborhood of our galaxy. The main disk of the Milky Way, containing the spiral arms, is immense. It is about 100,000 light-years across. To put that in perspective, if our solar system were the size of a quarter, the Milky Way would be the size of North America. It is a flat, sprawling city of light, but it is also incredibly thin. While it is 100,000 light-years in diameter, the disk is only about 1,000 light-years thick. It is thinner, proportionally, than a vinyl record. All of this, the disk, the arms, and the central bar, are surrounded by a vast spherical halo of scattered old stars and ancient star clusters. And how many neighbors do we have in this city? The estimates are staggering. The Milky Way contains somewhere between 100 billion and 400 billion stars. For every single person who has ever lived on Earth, there are dozens of stars in our galaxy alone. And we are learning that many of these stars, perhaps most of them, have planets of their own. This opens up a profound possibility. With billions of stars and potentially trillions of planets, it seems almost inevitable that we are not alone. Our galaxy could be teeming with worlds, some like our own, some fantastically different, all part of this single, sprawling cosmic family. Our personal sense of time is defined by the Earth. A day is one rotation, a year is one orbit around the Sun. But our Sun has its own orbit, on a scale that dwarfs our human conceptions of time. Just as the Earth is gravitationally bound to the Sun is bound to the supermassive black hole at the center of the Milky Way. Our entire solar system is on a grand circular tour of the galaxy. This journey is long. It takes our Sun approximately 230 million years to complete a single orbit. This vast expanse of time is known as one galactic year. Think about what that means. The last time our solar system was in this same position in the galaxy, dinosaurs roamed the Earth. The continents were just beginning to drift into their current positions. The first mammals were small, nocturnal creatures, hiding from the great reptiles. Since that time, the dinosaurs have risen and fallen. The age of mammals has dawned. And in the last tiny fraction of this single galactic year, all of human civilization has emerged. Our recorded history is but a few seconds on this great cosmic clock. We have been alive for only a flicker of a galactic moment. Our journey is not a gentle one. As we orbit, we move up and down through the plane of the galaxy, like a horse on a carousel. We pass through regions of varying density. Sometimes we travel through the dense, bright spiral arms, where nearby supernovae could pose a risk. At other times, we are in the sparser regions between the arms, like we are now. Some scientists have even speculated that these passages through different galactic environments could have influenced life on Earth, perhaps triggering mass extinctions or periods of evolutionary change. Our fate is tied not just to our Sun, but to the very geography of our galaxy. The center of our orbit is a place of profound mystery and power. At the very heart of the Milky Way, some 26,000 light-years away, lies Sagittarius A. It is a supermassive black hole, a point of infinite density with a gravitational pull so strong that nothing, not even light, can escape. It has a mass more than 4 million times that of our Sun. Every star in the galaxy, including our own, is held in orbit by the combined gravity of all the other stars and, most importantly, by this unseen monster lurking in the core. It is the silent, invisible anchor around which our entire galaxy revolves. Yeah. When we look at our galaxy, we see stars, we see gas, we see dust, we see the visible matter. For a long time, we thought that was the whole story. But there was a problem. The galaxy is spinning too fast. The stars on the outer edges are moving with such velocity that they should fly off into intergalactic space. The gravity from all the visible matter we can see, even the hundreds of billions of stars, is not nearly enough to hold the galaxy together. It's like watching a merry-go-round spinning so fast that the children on the edge should be flung off, yet they remain firmly in place. There must be something else, something massive, yet completely invisible. Scientists call this missing ingredient dark matter. It does not emit light. It does not reflect light. It does not interact with forces we are familiar with, except for one: gravity. It is a cosmic ghost, a silent, unseen presence that outweighs all the visible matter in the universe by a factor of more than 5 to 1. We don't know what it is, but we know it is there. Its gravitational influence is the glue that holds our galaxy, and all galaxies, together. Without it, the beautiful spiral structures we see would have torn themselves apart long ago. The Milky Way's vast spherical halo extends far beyond the visible disk of stars, and is thought to be composed primarily of this mysterious dark matter. It forms an invisible scaffolding, a gravitational framework upon which our galaxy was built. The gas and stars in the visible Milky Way are like the lights on a Christmas tree. The dark matter is the tree itself, unseen, providing the essential structure. This realization has fundamentally changed our understanding of the cosmos. About 85% of all matter in the universe is of a form we cannot see and do not yet understand. This mystery is one of the biggest challenges in modern physics. Our journey through the cosmos is not a solitary one. The Milky Way is part of a small cluster of galaxies called the Local Group, and we are on a collision course. Our nearest large galactic neighbor, the Andromeda Galaxy, is hurtling toward us at about 250,000 miles per hour. It is a cosmic spectacle, a gravitational dance that began billions of years ago. Right now, Andromeda is 2.5 million light-years away. But even at that immense distance, it is the most distant object you can see with the naked eye, a faint, fuzzy patch of light in the night sky. This is not a collision in the way we think of it on Earth. It will not be a crash of fire and destruction. Instead, it will be a slow, graceful merger. Because the distances between individual stars are so vast, direct collisions between stars will be exceedingly rare. It would be like two swarms of bees flying through each other. The swarms will merge, but very few individual bees will actually touch. Instead, the two galaxies will pass through one another, their shapes distorted by powerful gravitational tides. Stars will be flung out into long streams. The elegant spiral structures of both galaxies will be torn apart. This process will take hundreds of millions of years. After the first pass, the two galaxies will separate, only to be pulled back together again by their mutual gravity. They will dance and swirl, merging and reshaping each other over the eons. Eventually, after a long and complex gravitational tango, they will settle into a single, much larger galaxy. The gas from both galaxies will collide and collapse, triggering a spectacular burst of star formation, a galactic starburst that will light up the newly merged entity. Our night sky, for any observers who might exist then, will be a blaze of glory. The final result of this merger will be a new, giant elliptical galaxy. The beautiful spiral arms will be gone, replaced by a massive amorphous ball of older stars. Scientists have already given this future galaxy a name, Milkomeda. And what of our Sun and Earth? It is likely our solar system will survive. We will probably be thrown into a new, much larger orbit within this new galaxy. The collision is destined to happen in about 4.5 billion years. By that time, our Sun will be nearing the end of its life, swelling into a red giant. The fate of our galaxy is intertwined with the fate of our star, a future written in the laws of gravity. Well, that's the long view. We have journeyed across immense scales of space and time. From the dizzying speed of our solar system to the birth of our galaxy in the aftermath of the Big Bang. We have seen its structure, a city of stars 100,000 light-years across. We have contemplated the Great Galactic Year, a 230 million-year orbit that dwarfs human history. We have confronted the profound mystery of dark matter, the unseen scaffolding of the cosmos. And we have looked ahead to a distant future, to a cosmic collision that will reshape our galactic home. It is a story of unimaginable grandeur, enough to make one feel small and insignificant. But the final truth of this story is not one of separation. It is one of profound connection. Every piece of our world, every rock, every ocean, every living thing is intimately tied to the life and death of the stars in this galaxy. The first stars, those ancient giants, forged the heavy elements in their nuclear furnaces. When they exploded, they scattered these elements like seeds into the cosmos. Carbon, nitrogen, oxygen, iron, all the building blocks of planets, all the building blocks of life. Subsequent generations of stars, including our Sun, formed from these enriched clouds of gas and dust. This means that the story of the galaxy is also our own personal origin story. The iron in your blood, which carries oxygen through your veins, was created in the heart of an exploding star billions of years ago. The calcium in your bones, which gives you structure and strength, was forged in the same cosmic crucible. The carbon that forms the basis of your DNA, the very blueprint of your existence, was once part of a distant, long-dead star. We are not just living in the Milky Way. The Milky Way is living in us. We are, in the most literal sense, stardust. So the next time you look up at the night sky at that faint, milky band of light stretching across the heavens, remember what you are seeing. You are not just looking at a collection of distant suns. You are looking at your own ancestral home. You are looking at the source of the very atoms that make up your body. You are a child of the cosmos, a way for the universe to know itself. Every atom within you began its journey in a star and has been traveling through this galaxy for billions of years just to be here now as you. Simply incredible.
Imagine a universe where black holes are not merely cosmic endpoints, but dynamic engines of transformation. What if, instead of being silent, eternal voids, they could erupt in cataclysmic explosions, sending signals from the earliest epochs of the cosmos, encoded in bursts of energy that reach us across billions of years? Black holes are regions of space-time where gravity is so intense that the escape velocity exceeds the speed of light. They form from the gravitational collapse of massive stars, compressing matter into a singularity, a point of infinite density, surrounded by an event horizon, the boundary beyond which no information can return. The event horizon is not a physical surface, but a mathematical demarcation in the fabric of space-time. For much of the 20th century, black holes were considered perfect one-way traps. Nothing, not even light or information, could escape their grasp. This view changed dramatically in the 1970s when Stephen Hawking applied quantum field theory to curved space-time, revealing that black holes are not entirely black but emit radiation due to quantum effects near the event horizon. Hawking radiation arises from quantum fluctuations at the event horizon, where particle-antiparticle pairs spontaneously form. Occasionally, one particle falls into the black hole while the other escapes, resulting in a net loss of mass and energy. Over astronomical timescales, this process leads to black hole evaporation, a profound intersection of general relativity, quantum mechanics, and thermodynamics. For stellar mass black holes, this evaporation is unimaginably slow, far exceeding the current age of the universe. A solar mass black hole would take approximately 10 circumflex 67 years to evaporate completely. However, the rate of Hawking radiation increases as the black hole shrinks, leading to a runaway process in the final stages. This raises a fascinating question. What if there exist much smaller black holes formed in the early universe? Enter primordial black holes, hypothetical remnants from the high-density fluctuations in the first fractions of a second after the Big Bang. Unlike stellar black holes, these could range in mass from that of a mountain to less than a gram, yet possess immense gravitational fields. Their existence is still theoretical, but they offer a unique window into the physics of the early universe and the nature of dark matter. Unlike their massive counterparts, primordial black holes with sufficiently low mass could have been evaporating via Hawking radiation for billions of years. Some may be reaching the end of their lifespans right now, culminating in a final energetic outburst, a phenomenon that could be observable as a brief, intense flash of high-energy radiation. The terminal phase of black hole evaporation is predicted to be a violent explosion, releasing a burst of gamma rays and energetic particles. This process, though never observed, is a subject of intense theoretical and experimental interest. Detecting such an event would provide direct evidence for Hawking radiation and offer insights into quantum gravity. Astrophysicists are actively searching for these transient signals, short-lived gamma ray bursts or unexplained flashes in the cosmic microwave background that could signify the final moments of primordial black holes. Such detections would not only confirm a key prediction of quantum field theory, but also illuminate the conditions of the early universe. The implications are profound. Some models propose that primordial black holes could constitute a significant fraction of dark matter, the invisible mass that shapes galaxies and cosmic structure. If even a single evaporating black hole is detected, it could revolutionize our understanding of cosmology and the fundamental constituents of the universe. Others suggest that the study of black hole explosions could reveal new physics, perhaps unifying general relativity and quantum mechanics, or exposing phenomena beyond the standard model. The interplay between gravity, quantum fields, and space-time curvature remains one of the deepest mysteries in theoretical physics. Picture a solitary flash of light in the night sky, a message encoded in energy carrying information from the universe's infancy. Each such event would be a cosmic relic, a direct probe of conditions mere moments after the Big Bang, and a testament to the unity of the laws of nature across time and space. Should an evaporating black hole be observed in our era, it would be more than a scientific milestone. It would be a message from the origin of everything, a fleeting glimpse into the universe's primordial state, and a key to unlocking its most profound secrets. So as you gaze into the night sky, remember, the cosmos is a vast laboratory, filled with enigmas awaiting discovery. Somewhere, perhaps even now, a black hole may be preparing its final brilliant transmission, a cosmic signal challenging us to decipher the ultimate laws of reality.
What if I told you that everything you know is a lie? The world around you, the chair you're sitting on, the air you breathe, the stars twinkling in the night sky are not quite real. Imagine that this entire universe is nothing more than an elaborate computer simulation. It's like science fiction. You might dismiss it. But what if clues are hidden all around us, embedded in space and time? What if the laws of physics are actually code? This isn't just late-night musing. It has fascinated brilliant minds. We think of reality as tangible. We trust our senses. We believe what we see, touch, and feel. Our senses are easy to fool. Optical illusions, dreams, virtual reality all show how convincing a fabrication can be. How can we be certain this is the genuine article? Are we characters in someone else's advanced video game, living out a pre-programmed life? The proposition is staggering. It forces us to question our basic assumption. One true reality. If it isn't, then every discovery, every historical event, every personal memory could be part of a script. The feeling of the sun on your skin might be simulated heat. It's a dizzying idea. It can make you question your sanity. But science pursues unsettling ideas. Those questions lead to breakthroughs. We look outward to the cosmos, distant galaxies, exploding stars. Maybe the biggest revelation is inward, the nature of existence itself. Are we biological beings evolved on a rocky planet, or informational constructs running on a cosmic supercomputer? We are on the verge of a paradigm shift, a leap of faith like Neo, and choose which pill we want to swallow. The idea that our reality might be an artificial construct found its modern voice through a philosopher named Nick Bostrom. In 2003, he published a paper that laid out a compelling argument. Not a wild guess, but a logical exercise. Bostrom proposed one of three possibilities must be true. First, civilizations like ours almost always go extinct before they can develop hyper-realistic simulations. Second, advanced civilizations lose interest in creating such simulations. Third, we are almost certainly living inside a computer simulation right now. Think about it. If civilizations can create simulated worlds, they would likely create many of them. This idea has deep roots in philosophy and decades of science fiction. The Matrix brought the idea to the masses. Tron showed programmers digitized inside their creations. Ready Player One imagines a society living inside a vast, shared virtual universe. These stories act as thought experiments about technology and ethics. Bostrom's argument hinges on projecting our technological trajectory. We went from Pong to sprawling photorealistic open worlds. Now, imagine projecting that progress forward thousands or millions of years. An advanced civilization could create simulations indistinguishable from base reality. The beings inside wouldn't know. They'd think their world is real. Why run ancestor simulations? For scientific research, to study societies, for entertainment, the ultimate immersive experience, or for reasons beyond our comprehension. The key takeaway is statistical. Countless simulated universes for every one base reality. The odds then favor us being in a simulation. It's a sobering thought. We might be a copy of a copy, living inside someone else's experiment. How could a universe as vast and complex as ours possibly be just information? The answer may lie in one of the strangest and most successful theories in all of science: quantum mechanics. On the cosmic scale of planets and galaxies, the universe seems to follow predictable rules, the classical physics of Newton-Einstein. But when we zoom in, way down to the subatomic level, electrons, photons, the rules change completely. Here, in the quantum realm, things don't have definite properties until we measure them. An electron doesn't have a specific position. Instead, it exists in a cloud of probabilities, a wave of potential locations. This is where things get truly bizarre. The very act of observing a quantum particle seems to force it to choose a state. Before you look, it's everywhere and nowhere at once. When you measure it, its probability wave collapses, and it snaps into a single definite location.
This observer effect is one of the deepest mysteries in physics. It suggests that reality, at its most fundamental level, isn't a solid, pre-existing thing. Instead, it seems to be something that is brought into being through the act of observation or interaction. It's as if the universe is waiting for a conscious observer to render the details on demand. This strange behavior has led some physicists to consider a radical idea known as digital physics. This school of thought proposes that the universe isn't just described by information, but that it is, in its essence, information. Every particle, every force, every law of physics could be the output of a computational process. The universe, in this view, is like a giant computer. Space, time are not smooth and continuous, but are made of tiny, discrete units like pixels on a screen. If you could zoom in far enough, you might find the fundamental resolution of the universe, a smallest possible length known as the Planck length. If reality is made of these discrete units, it would mean that the universe has a finite amount of information it can contain. The bizarre rules of quantum mechanics and the apparent pixelation of space-time might not be mysteries at all. They could be the telltale signs of the underlying code. The legendary physicist John Archibald Wheeler summed up this entire line of thinking with a simple, elegant phrase, "it from bit." So what did he mean by that? He was proposing a revolutionary new way of looking at the universe. The "it" represents everything in the physical world, every particle, every planet, every galaxy. It's all the tangible stuff we call reality. The bit is the fundamental unit of information. A yes or no answer, a 1 or a 0. Wheeler's idea. Every "it" derives existence from bits processed at the deepest level. Think of it like a character in a video game. That character appears solid on screen. It can run, jump, interact with the environment, but at its core, it's not flesh and blood. It's bits of information. Its look, abilities, and rules come from the game's code. Wheeler suggested the universe might work the same way. An electron isn't a tiny solid ball. It's the result of yes or no questions being answered. Is it here? Is it spin up? Those binary answers, bits, conjure the electron. This changes how we view physics. Laws like gravity, electromagnetism might not be fundamental. They could be algorithms, computational rules the cosmic computer follows. So discovering a law may be reverse engineering source code. Physicists become cosmic hackers decoding the programming language of existence. If true, information is more fundamental than matter and energy. Before the Big Bang, maybe a sea of pure information, a blank computational slate. The Big Bang could be the moment the program was run, when bits started processing into it. Our cosmos could be the output of a colossal computation. We are living in the output of a cosmic information processor. As you might imagine, not everyone in the scientific community is ready to embrace the simulation hypothesis. For many physicists, the idea, while fascinating, straddles a dangerous line between science and pure philosophical speculation. A core principle of the scientific method is that a hypothesis must be testable. It has to make predictions we can verify or falsify through experiment. Critics argue the hypothesis may be fundamentally untestable. How could we design an experiment to prove we are or are not inside a simulation? The arguments against it are compelling. Physicist Lisa Randall, for example, has expressed skepticism, saying the odds are effectively zero. She and other critics say the case relies on many assumptions about how future civilizations would behave and what their motivations might be. We project our own desires for gaming and for research onto hypothetical, super-advanced beings. It's a very human-centric view. Who's to say they wouldn't find ancestor simulations boring, unethical, or a complete waste of computational resources? Some argue clues like the pixelation of space-time at the Planck length or the observer effect in quantum mechanics are not evidence of a simulation. They might just be fundamental features we don't yet understand. Attributing them to a simulation is a God of the gaps move. Where we have gaps, we insert a simulator. It's an easy answer, but may not be the right one. Science fills gaps with evidence and theory, not an unknowable programmer. Still, proponents search for tests. Some scientists propose looking for glitches, small inconsistencies in physical laws that might reveal a computational substrate. For example, high-energy cosmic rays might behave slightly differently if they're bumping against a simulated space-time grid. So far, no such evidence has been found. The simulation idea is tantalizing and mind-bending, but for now it sits at the edge of scientific inquiry, waiting for a test that could confirm our wildest digital dreams or bring us back to solid, unsimulated ground. If we do live in a simulation, the implications are truly mind-boggling. Let's start with the idea of glitches in the matrix. In any complex computer program, bugs are inevitable. No matter how sophisticated the code, errors can occur. In our reality, a glitch might not look like a cat repeating its actions. It might manifest as a subtle violation of the laws of physics, a momentary flicker in a physical constant, or a particle appearing where it really shouldn't be. Events like déjà vu or unexplained phenomena, often dismissed as tricks of the mind, take on a whole new meaning. Could they be the system momentarily lagging, or maybe an error in the code of our world? The idea also opens the door to the concept of nested simulations, kind of like a set of Russian dolls. If an advanced civilization can create a realistic simulation, what's to stop the simulated beings inside from eventually developing their own technology to create their own simulations? This could lead to a potentially infinite hierarchy of realities, each one a simulation created by the civilization in the level above it. We could be living in a simulation within a simulation within a simulation, and so on. Where does it end? Is there a base reality at the very top, or is it simulations all the way down? This leads to another profound question. What about our creators? If we are simulated beings, then we were created by a higher intelligence. This doesn't necessarily mean a divine being in the religious sense, but rather a civilization of programmers, engineers, or maybe even a bored teenager in a higher dimension. This civilization would be, for all intents and purposes, our gods. They would have the power to alter the laws of physics, rewind time, or even shut down the simulation entirely. The thought that our entire existence could be terminated with a single keystroke, the ultimate Ctrl-Alt-Delete, is both terrifying and humbling. And so we arrive at the ultimate question, the one that lingers long after the scientific debates have quieted. If our universe is a simulation, a grand piece of cosmic code, then who or what wrote it? Who is the programmer? This question takes us beyond the realm of physics and into metaphysics and philosophy. Are our creators biological beings like us, just far more advanced? Or are they post-biological artificial intelligences beyond physical bodies? The possibilities are limitless. Maybe the simulation wasn't even intentional. Maybe it's a byproduct, a student science fair in a higher dimension. Imagine a young being running a galaxy formation simulation. Conscious life spontaneously emerges. To them, we're an unexpected data point. The purpose of our existence could be accidental. The meaning we search for in art, in science, in religion, an emergent property of someone else's program. This forces us to confront our cosmic significance. For millennia, we've put ourselves at the center, physically, then philosophically. The simulation hypothesis is the ultimate demotion. It suggests we may not be part of the real universe. But does that diminish our lives? Does it make love any less meaningful? Joy any less meaningful? Discovery any less meaningful? The experiences are real to us. The pain we feel is real. The beauty of a sunset is real. Even if it's rendered pixels, our awe is genuine. We're left staring into the great unknown. Whether base reality or simulation, the quest for understanding gives our existence meaning. The search for the programmer is a noble, profound purpose, and who knows what you might find.
We've all seen it. The desperate command from the cockpit of a starship, a Corellian freighter perhaps. The frantic flip of a switch, the pull of a lever. Stars, once distant points of light, stretch into brilliant streaks. The ship lurches with a flash, it vanishes into a swirling tunnel of pure energy. This is the jump to hyperspace, a cornerstone of science fiction, the promise of crossing unimaginable distances in the blink of an eye, making a vast, sprawling galaxy feel like a neighborhood. It allows heroes to outrun empires and explorers to chart unknown worlds. A beautiful, thrilling, utterly captivating idea, the dream of faster-than-light travel, breaking free from the cosmic chains that bind us to our solar system. In cinematic moments, the laws of physics seem to melt away. A simple calculation, a quick repair to the hyperdrive motivator, the journey from a desert planet to a forest moon takes mere hours, not millennia. In 1905, a young patent clerk named Albert Einstein published a series of papers that would forever change our view of the universe. He gave us a new framework for understanding reality, a theory known as special relativity. And within that theory, he revealed a fundamental rule of the cosmos, a kind of universal speed limit. This cosmic speed limit is the speed of light in a vacuum, a staggering 299,792 kilometers per second, or about 186,282 miles per second. It's a number we often abbreviate with the letter CE. Nothing with mass, Einstein showed, can ever reach this speed, let alone surpass it. Think about it. Light from the sun takes a little over 8 minutes to reach Earth. A beam of light could circle our planet more than 7 times in a single second. It is an almost incomprehensible velocity. Yet, according to Einstein, this is the ultimate speed. It's not a technological barrier that we can one day engineer our way past. Like the sound barrier, it is woven into the very fabric of space-time itself. It's a law of nature as fundamental as gravity. This one simple, elegant idea acts as the great gatekeeper of the cosmos, dictating where we can go and how fast we can get there. This concept stands in stark opposition to the world of Star Wars, where the Millennium Falcon zips from Tatooine to Alderaan in what seems like no time at all. Einstein's theory of relativity doesn't just set a speed limit, it explains why that limit exists. And the reason is one of the most famous equations in all of science, E equals mc squared. This equation tells us that energy mass are two sides of the same coin. They are convertible. You can turn mass into a tremendous amount of energy. Nuclear power plants, stars. But it also works the other way around. Energy can, in a sense, become mass. And this is the crux of our problem. As you accelerate an object, you are constantly pumping kinetic energy into it. According to relativity, that added energy contributes to the object's total mass. So the faster you go, the more massive you become. At everyday speeds, this increase in mass is so infinitesimally small that we can't even detect it. But as you start to approach the speed of light, the effect becomes dramatic. A spaceship traveling at 87% the speed of light would have twice its resting mass. At 99.5% the speed of light, it would be 10 times more massive. If Einstein's laws prevent us from moving through space faster than light, what if we could, move space itself? This is the brilliant and highly speculative idea behind the Alcubierre warp drive, a theoretical concept proposed by physicist Miguel Alcubierre back in 1994. The idea doesn't break the law of special relativity. Instead, it kind of cleverly exploits a loophole in Einstein's other great theory, general relativity. General relativity tells us that massive objects can bend and warp the fabric of space-time. This is what we experience as gravity. The Alcubierre drive suggests we could actually do this on purpose. Imagine your starship is sitting inside a bubble of normal, flat space-time. The drive would work by contracting the space-time in front of the bubble and at the same time expanding the space-time behind it. The ship itself isn't moving through space in the traditional sense. It's more like a surfer riding a wave on the fabric of reality. The space in front of you shrinks, and the space behind you grows, pushing your bubble forward. From inside the bubble, you would feel no acceleration at all. You could be perfectly still, sipping your coffee while your bubble zips across the galaxy at an effective speed many times greater than light. If bending space in a wave is too difficult, what about, punching a hole through it? This leads us to another fascinating concept from Einstein's general relativity, the wormhole, or as it was originally called, an Einstein-Rosen bridge. A wormhole is a theoretical tunnel, a shortcut through the fabric of space-time. Imagine space-time is a giant sheet of paper. To get from one point on the paper to another, you would normally have to travel across its surface. But what if you could fold the paper over, bringing the 2 points very close together, and then poke a pencil through both layers? That pencil hole is the wormhole. This shortcut wouldn't require you to travel faster than light. You would enter one mouth of the wormhole and emerge from the other mouth, located somewhere else in the universe, almost instantaneously. The journey through the tunnel could be very short, even if the two mouths are separated by millions of light years in normal space. This method, like the Alcubierre drive, circumvents the cosmic speed limit. However, according to our current understanding, naturally occurring wormholes, if they exist at all, would likely be microscopic on the scale of subatomic particles. Even if you found one, it would be unstable. It would snap shut in an instant, likely before even a single photon of light could make it all the way through. Let's compare these wild theoretical ideas to what we see in our favorite space sagas. When Han Solo boasts that the Millennium Falcon made the Kessel Run in less than 12 parsecs, he's famously, maybe even intentionally, confusing a unit of distance with a unit of time. But the implication is clear. The ship's powerful hyperdrive allowed it to take a dangerous shortcut. This sounds a lot more like a wormhole than an Alcubierre drive. The ship didn't just point itself at its destination and travel in a straight line. It navigated a specific treacherous route through an alternate dimension or a series of space-time tunnels. In the Star Wars universe, hyperspace is often treated as a parallel dimension that coexists with our own. Ships enter it, travel for a while, and then re-emerge in normal space. This requires a hyperdrive and a navicomputer. A navicomputer calculates a safe route, avoiding mass shadows of stars and planets. Those mass shadows could pull a ship out of hyperspace with catastrophic results. This separate dimension idea is a convenient narrative device, but it has no direct analog in modern physics. So, where does this leave us? Are we forever trapped in our cosmic neighborhood, destined only to gaze at the stars through telescopes? It is easy to look at the challenges, the infinite energy, the need for exotic matter, and conclude that faster-than-light travel is simply impossible. And based on everything we know today, in the year 2025, that is the most rational conclusion. The laws of physics, as we currently understand them, have posted a clear no trespassing sign at the speed of light. But science is a story of overturned conclusions. A few centuries ago, the most brilliant minds would have told you that flying was impossible for humans, that splitting the atom was a fantasy, and that traveling to the moon was the stuff of madmen. Our understanding of the universe is a work in progress. We are still uncovering the deepest secrets of reality. Concepts like dark matter and dark energy show us that the vast majority of the universe is made of stuff we don't understand at all. Who is to say that within these great cosmic mysteries, we won't find something that changes the game entirely? Perhaps exotic matter is not impossible, just rare. Perhaps a future breakthrough in quantum physics or our understanding of gravity will reveal a new way to manipulate space-time. The theories of Alcubierre and Einstein-Rosen bridges are our first tentative steps into a much larger intellectual world. They are the equivalent of early drawings of flying machines with flapping wings. They might be wrong in their details, but they point us in a direction. The human spirit is defined by its refusal to accept limits. We are explorers by nature. We look at the vast, dark ocean of space not as an impassable barrier, but as the next frontier. The stars are waiting.
Why does the universe, our grand cosmic home, seem to play by two entirely different sets of rules? On a scale we can see and touch, everything appears orderly, predictable, and reassuringly solid. Planets follow their ancient, graceful paths around stars. A ball thrown into the air traces a perfect arc, its path sealed by gravity the moment it leaves your hand. A magnificent clockwork of cause and effect, gears turning in harmony. It's the world of classical mechanics, the physics that built our civilization and sent us toward the stars. But shrink your perspective. Journey down, 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 mountains, cities, a single grain of sand, beyond cells past molecules into the realm of the atom. Here, the rules dissolve into a bewildering carnival of strangeness. Particles become shimmering clouds of probability. They can exist in multiple places at once. They can be neither here nor there, but both until you look. This is quantum mechanics, as real as orbiting planets. Two frameworks, classical mechanics, quantum mechanics, twin pillars. Two languages describing one universe, sounding alien to each other. One promises certainty, a cosmos written in the stars. The other speaks of uncertainty, chance, and probability, observation shaping reality. How can both be true? How does solidity arise from probabilistic waves? From Newton's apple to Einstein's thought experiments to Bohr, we confront the limits of intuition and accept a stranger, more wonderful universe. We live on the seam between two realities, a bridge between clockwork and chaos. Explore both sides. Embrace the harmony of the large, the magic of the small. Let's begin in a world that feels like home. The world of classical mechanics. This is the physics of our everyday lives. A child spinning top the majestic sweep of galaxies. Its story is largely the story of one monumental genius, Sir Isaac Newton. In the 17th century, Newton gave us simple, elegant laws of motion and a universal law of gravitation. These laws were revolutionary. The same force that pulls an apple from a tree also holds the moon in orbit around Earth. The heavens and the earth were united under one set of rules. Newton's laws rest on determinism. If you know the position and momentum of every object and all the forces on them, you could predict the future with perfect accuracy. Imagine the universe as a colossal game of billiards. Exact starting position, exact speed, exact direction, and you could calculate every collision from break to pocket. In this view, the universe is a machine, vast, intricate, and knowable, its future written in its present. These laws are the bedrock of technology. When engineers design a bridge, they calculate tension and compression, ensuring it withstands traffic and wind. When we launch a rocket to Mars, it's not guesswork. It's precise celestial calculation, plotting trajectories through the Sun, Earth, and Mars. Your phone's GPS uses the same principles, tracking you relative to satellites. This classical world feels certain. Objects have definite properties. A car has a specific location and speed. It cannot be in two places at once. Its path is continuous and smooth. Energy and momentum are conserved, transferred but never lost. This conservation brings order. It lets a pendulum swing and governs galactic collisions. For centuries, we believed this was the whole story. We thought we'd found the universe's operating manual. But we were only reading the first chapter. As the 19th century gave way to the 20th, cracks began to appear in the perfect facade of classical physics. Scientists studying phenomena like the light emitted by hot objects and the nature of the electron found that the old rules simply didn't work. The universe, it turned out, had a secret life. To explain these puzzling observations, a new theory was born, quantum mechanics, and with it, our understanding of reality was turned upside down. The solid, predictable world of Newton was replaced by a fuzzy, probabilistic landscape. One of the first bizarre discoveries was wave-particle duality. In the classical world, things are either particles, like a baseball, or waves, like a ripple in a pond. But in the quantum realm, entities like electrons and photons of light behave as both. Depending on how you measure it, an electron can act like a localized particle, or like a spread-out, undulating wave. It's not one or the other, it's both. This duality is a fundamental property of matter. Then, superposition. A quantum particle can exist in a combination of all possible states simultaneously. Imagine a coin spinning in the air. Classically, it will land heads or tails. A quantum coin can be both heads and tails at the same time. It's a ghostly blend until a measurement is made. Measurement forces the particle to choose. Wave function collapse. Your observation helps create the reality you see. And it gets even stranger. The uncertainty principle, from Werner Heisenberg, limits what we can know. You cannot know both position and momentum exactly. Measure position precisely, and momentum becomes uncertain, and vice versa. This is a built-in fuzziness of the universe. Finally, entanglement. Two entangled particles link so measuring one instantly influences the other, no matter the distance, across a room or across the galaxy. The journey into the quantum realm was not the work of a single mind like Newton's, but a collaborative, often contentious effort by a generation of brilliant physicists. They were explorers charting territory so strange, it defied language and intuition. Max Planck took the first steps in 1900. While studying blackbody radiation, he proposed energy came in discrete packets, quanta. He thought it a trick, but he'd planted a revolutionary seed. A few years later, a young Albert Einstein took that seed he used like quanta, photons, to explain the photoelectric effect. That work earned him the Nobel Prize. The 1920s became the heroic age of quantum mechanics. A cohort of daring young thinkers built its mathematical and conceptual framework. Niels Bohr developed an atom model with quantized energy levels explaining why atoms emit light at specific frequencies. Louis de Broglie proposed that all matter, not just light, has a wave-like nature seen in electron diffraction patterns. Erwin Schrödinger formulated a wave equation describing how quantum states evolve over time, the quantum analog of Newton's laws. Werner Heisenberg developed matrix mechanics and introduced the uncertainty principle, linking observer and observed. These scientists, and others like Wolfgang Pauli-Max Born, wrestled with mathematics and deep philosophical implications. What did it mean for reality to be probabilistic? What was the role of the observer? The debates were legendary, most famously Einstein versus Bohr. Einstein: God does not play dice. He argued quantum mechanics was incomplete, pointing to hidden variables. Bohr replied, "Stop telling God what to do." Their debate forced physicists to confront the nature of reality, a conversation still ongoing. These architects of the impossible didn't just discover new rules, they gave us a new universe. While the principles of quantum mechanics might sound like abstract philosophy or science fiction, they are not confined to dusty blackboards, distant laboratories. The bizarre behavior of particles in the subatomic realm is the engine driving much of the technology that defines our modern world. You are experiencing the practical results of quantum mechanics right now. The device you are using to read this essay, a computer, a tablet, a smartphone, is a quantum machine. Its heart is a microchip filled with billions of transistors, semiconductor devices governed by the quantum behavior of electrons. Without our understanding of how electrons move through materials like silicon, transistors would be impossible. Classical physics predicts that electrons shouldn't be able to do what they do inside a chip. Quantum mechanics, specifically the theory of energy bands in solids, explains it perfectly. This understanding allows us to control the flow of electricity at an incredibly small scale, creating the binary language of ones and zeros that forms the basis of all digital information. Every time you save a file, stream a video, or send a message, you are relying on the predictable application of quantum weirdness. Look around you. The laser is another quintessential quantum invention. The word laser is an acronym for light amplification by stimulated emission of radiation. The key concept, stimulated emission, was first proposed by Einstein. One photon can trigger an atom to release a second identical photon. Contained in a mirrored cavity, this makes a cascade, a coherent focused beam. Lasers are everywhere. In barcode scanners at the grocery store, in Blu-ray players, in fiber optic cables that carry the internet across oceans, in delicate surgical procedures. The influence of quantum mechanics extends even into our hospitals. Magnetic resonance imaging, or MRI machines, produce detailed images of soft tissue through nuclear magnetic resonance. A powerful magnetic field aligns the quantum spin of protons in the water molecules of your body. A radio wave knocks them out of alignment, and the machine listens for the signals they emit as they return. By analyzing these signals, a computer constructs a detailed three-dimensional map of your internal anatomy, all without any harmful radiation. From computing to communication to medicine, the quantum world is not a distant, strange land. It's the invisible foundation of our 21st century lives. So we have these two magnificent theories, classical mechanics, quantum mechanics. Both are incredibly successful within their own domains. But how do they stack up side by side? The most obvious difference is scale. If the universe is fundamentally quantum, built on a foundation of uncertainty and probability, then where does the solid, predictable classical world come from? The answer lies in a crucial concept known as the correspondence principle, first articulated by Niels Bohr. This principle states that the predictions of quantum mechanics must agree with the predictions of classical mechanics in the limit of large systems. As you scale up from the atomic to the everyday, the weirdness of quantum mechanics should fade away, leaving the familiar certainty of Newton's laws. This transition happens through a process called quantum decoherence. A quantum object, like a single electron, can maintain its strange superposition state as long as it is perfectly isolated from its environment. But in the real world, perfect isolation is impossible. A macroscopic object, a dust mote, a baseball U, is constantly interacting with its surroundings. Trillions upon trillions of air molecules, photons of light, and cosmic rays are bombarding it every microsecond. Each of these tiny interactions acts as a measurement, observing the object's position and forcing its quantum wave function to collapse. And what emerges is a single loud classical shout.
What happens when a star, after burning for millions or billions of years, finally runs out of fuel? This is not just a question about a distant point of light. It is a question about the very engine of cosmic creation and destruction. The stars that illuminate our night sky are not eternal flames. They are vast, dynamic nuclear reactors, engaged in a constant, delicate balancing act. Gravity relentlessly pulls their immense mass inward, seeking to crush them into oblivion. At the same time, the nuclear fusion in their cores generates tremendous energy, pushing outward and holding that collapse at bay. For most of a star's life, these two forces are in perfect equilibrium, a cosmic stalemate that allows the star to shine steadily for an almost unimaginable length of time. But this balance cannot last forever. The hydrogen fuel that powers a star's core is a finite resource. When it begins to run low, the outward push from fusion weakens, and gravity starts to gain the upper hand. The star enters its final dramatic chapters. Instead, the death of a star is one of the most spectacular and transformative events in the entire universe. The path it takes depends critically on one single factor: its mass. The answer is a story of immense power, profound change, and incredible beauty. The first major stage in a star's demise begins when the hydrogen fuel in its core is depleted. For its entire main sequence life, the star has been fusing hydrogen atoms into helium. But when that core hydrogen runs out, the fusion furnace sputters and goes out. Without the outward pressure from fusion, the core begins to collapse under its own immense weight. As it collapses, it heats up dramatically, becoming far hotter than it ever was. This intense heat ignites a shell of hydrogen fusion in the layers just outside the core. This surge of energy pushes the star's outer layers outward with irresistible force. The star begins to swell to an enormous size, growing hundreds or even thousands of times larger. As the surface expands, its energy is spread over a much larger area, causing the surface temperature to drop. The star's color shifts from a brilliant white or yellow to a deep, ominous red. The star has now become a red giant. In approximately 5 billion years, our sun will begin its transformation into a red giant. Its expansion will be so vast that it will swallow the orbit of Mercury completely, Venus completely. It may even expand far enough to engulf Earth itself, boiling away our oceans. During this phase, the sun will also begin to lose mass, shedding its outer layers in a powerful stellar wind. For low and medium mass stars, including stars like our sun, the end of their life is a process of serene dissipation rather than violent explosion. Once the star has exhausted its helium fuel in the core, its nuclear furnace shuts down for good. It simply does not have enough mass and therefore not enough gravitational pressure. In a series of thermal pulses, it begins to gently puff away its outer layers. These expelled layers of gas, enriched with elements like carbon and oxygen, expand outward in a beautiful glowing shell. This expanding cloud is illuminated by the intense ultraviolet radiation streaming from the hot, exposed core left behind. The result is one of the most beautiful objects in the cosmos, a planetary nebula. At the heart of every planetary nebula lies the remnant of the star's core, a white dwarf. A typical white dwarf might contain about half the mass of our sun, but compressed into a volume roughly the size of Earth. A single spoonful of white dwarf material would weigh several tons on Earth. This extreme density is the result of a quantum mechanical phenomenon known as electron degeneracy pressure. A newly formed white dwarf is incredibly hot, with surface temperatures exceeding 100,000 degrees. However, with no internal source of energy, it is essentially a dying ember. Over billions of years, it will gradually cool and dim, its color shifting from white to yellow to red. Eventually, it will cool completely and become a cold, dark ball of carbon and oxygen, a black dwarf. In that quiet ending, the echoes of their lives continue to shape everything we know. The lives of massive stars are dramatically shorter and more violent than those of their smaller cousins. They burn through their fuel at a ferocious rate, living fast and dying young. As they age, they build up a core of iron, the ultimate ash of nuclear fusion. Unlike lighter elements, fusing iron atoms together consumes energy rather than releasing it. The outward pressure that had supported the star for millions of years vanishes in an instant. Gravity, the relentless force that has been trying to crush the star its entire life, finally wins. In less than a second, the iron core catastrophically collapses inward at incredible speeds, reaching up to a quarter of the speed of light. The infalling outer layers slam into this newly formed super-dense object and rebound. The shock wave is supercharged with energy from a flood of ghostly particles called neutrinos. This explosive rebound is a Type II supernova, one of the most energetic events in the universe. In the moments of this explosion, the star briefly becomes as luminous as an entire galaxy of hundreds of billions of stars. The extreme conditions trigger nuclear reactions that create all elements heavier than iron. Gold, silver, platinum, uranium, every atom of these elements was forged in a supernova explosion. The star scatters these newly forged heavy elements across the galaxy. This expanding cloud of debris will cool and mix with surrounding gas and dust. These remnants are not just relics, they are seeds that will enrich the next generation of stars, planets, and perhaps even life. If the core's mass is between approximately 1.4 and 3 times the mass of our sun, a truly extraordinary object is formed, a neutron star. The pressure is so intense that it forces electrons and protons to merge, forming neutrons. The entire core becomes a single gigantic atomic nucleus composed almost entirely of neutrons. A neutron star contains more mass than our Sun, yet compressed into a sphere only about 20 kilometers in diameter, roughly the size of Manhattan. A single sugar cube's worth of neutron star material would have a mass of about 100 million tons. Its surface gravity is hundreds of billions of times stronger than Earth's. The neutron star spins at incredible speeds, often rotating hundreds of times per second. This rapid rotation concentrates the original star's magnetic field, making it trillions of times stronger than Earth's. This intense magnetic field generates powerful beams of radiation that shoot out from the neutron star's magnetic poles. Because the magnetic poles are not aligned with the rotational axis, these beams sweep across the cosmos like a lighthouse. If one of these beams sweeps across Earth, our radio telescopes detect a regular pulse of energy. These rapidly spinning, beaming neutron stars are known as pulsars. The regularity of their pulses is so precise that they are among the most accurate clocks in the universe. Neutron stars are extreme laboratories for physics, pushing matter to its absolute limits. The discovery of pulsars in 1967 was a landmark moment, providing first evidence for neutron stars. They remain among the most fascinating objects in the cosmos, the city-sized cinders left behind by the universe's greatest fireworks. If the remnant core weighs more than about 3 times the mass of our Sun, then not even the immense pressure of packed neutrons can withstand gravity. There is no known force in the universe that can halt the collapse. The core is compressed into an infinitely dense, zero-volume point, a singularity. This singularity is surrounded by a region of space-time so warped that it becomes a one-way street. An object has been created from which nothing, not even light itself, can escape, a black hole. The boundary of this region is called the event horizon, not a physical surface, but a theoretical border. Once anything crosses the event horizon, it can never communicate with the outside universe again. We cannot see a black hole directly. Instead, we watch as stars orbit a patch of empty space at incredible speeds. Matter forms a rapidly rotating accretion disk, heated to millions of degrees by friction. This causes the disk to glow brightly in high-energy wavelengths like X-rays. Powerful magnetic fields can channel matter into colossal jets blasted away at nearly the speed of light. These jets can extend far beyond their host galaxy. At the center of nearly every large galaxy lurks a supermassive black hole with mass millions or billions of times that of our Sun. These behemoths play a crucial role in galaxy evolution, regulating star formation throughout the galaxy. Black holes are fundamental architects of the universe. The death of the most massive stars is intimately linked to the life and growth of the largest structures in the cosmos. The death of a star, whether gentle, fading, or violent explosion, is never truly an end. It is a transformation. When a low-mass star sheds its layers, it enriches space with lighter elements like carbon and nitrogen. When a massive star explodes, it forges and flings heavier elements throughout the galaxy. The oxygen we breathe, the iron in our blood, the silicon in rocks, all were forged in stellar furnaces. We are made of star stuff. The history of the universe is written in our own biology. Looking up at the night sky is like looking back at our own cosmic family tree. The faint light from distant stars and nebulae tells the story of our origins. Our own Sun will follow this path in the distant future. In about 5 billion years, it will swell into a red giant. It will shed its layers as a planetary nebula and leave behind a cooling white dwarf. Life on Earth will not survive this transformation, but the atoms that make up our planet will be returned to the cosmos to become part of new stars, planets, and perhaps new life. The death of a star is not an ending to be feared, but a process of renewal to be understood. It is the mechanism by which the universe endlessly reinvents itself, ensuring that even in darkness and destruction there are always the seeds of new beginnings. Even our own Sun will one day die, becoming a white dwarf, but not for another 5 billion years. Until then, we continue to be part of this magnificent cosmic story, children of the stars, witnesses to the universe's endless capacity for renewal and wonder.
What if the universe doesn't follow the rules we see every day? Have you ever truly looked at your hand and wondered what it's made of? Or gazed at the stars and questioned the fundamental nature of the reality we inhabit? For centuries, we thought we had the answers. The universe, according to classical physics, the physics of Isaac Newton, was a grand, predictable machine, a cosmic clockwork where planets followed perfect orbits, and every cause had a clear, calculable effect. It was a world of certainty, of solid objects and straightforward rules. If you knew the position and momentum of every particle, you could, in theory, predict the entire future of the universe. This comforting deterministic view reigned supreme for over 200 years. But at the dawn of the 20th century, as scientists began to probe the very smallest scales of existence, this elegant picture began to crack, revealing a world far stranger and more wondrous than anyone had ever imagined. Welcome to the realm of quantum physics. This is not just an extension of the old rules, it is a completely new operating system for the universe. It is the science of the infinitesimally small, the world of atoms and the particles within them, electrons, protons, and the quarks and photons that make up everything we see, touch, and are. Down here, in this subatomic domain, the familiar logic of our everyday world dissolves into a dizzying dance of probability and potential. The solid, predictable billiard balls of classical physics are replaced by ghostly waves of possibility. This is a world where particles don't have a definite location until we look at them. A world where a single electron can exist in multiple places at once, a state of being known as superposition. It's a place where particles can be mysteriously linked across vast cosmic distances, their fates intertwined in a phenomenon Einstein famously called spooky action at a distance, what we now call quantum entanglement. It's a reality where energy isn't continuous, but comes in discrete packets, or quanta, the very idea that gave this field its name. This radical departure from classical intuition didn't just add a new chapter to the book of physics. It forced us to tear up the book and start again. It fundamentally reshaped our understanding of reality itself, challenging our core assumptions about cause and effect, the nature of observation, and the very boundary between the observer and the observed. The pioneers of this revolution, Max Planck, Albert Einstein, Niels Bohr, Werner Heisenberg, and Erwin Schrödinger, were reluctant heroes, often as baffled by their own discoveries as the rest of the world. They had unlocked a Pandora's box of cosmic secrets, and the implications were staggering. But this isn't just a historical curiosity or an abstract intellectual exercise. The bizarre rules of the quantum world are the bedrock of our modern technological society. The laser in your Blu-ray player, the transistors that power your smartphone, the medical imaging of an MRI scan, all are direct results of our understanding of quantum mechanics. And today, we stand on the precipice of a second quantum revolution. Scientists are harnessing these strange principles to build technologies straight out of science fiction. Ultra-powerful quantum computers capable of solving problems impossible for any classical machine, unbreakable cryptographic codes to secure our information, and even the tantalizing prospect of quantum teleportation. In this series, we will embark on a journey into this incredible world. We will explore the foundational experiments that shattered the classical worldview, meet the brilliant minds who pieced together this new reality, and demystify the core concepts of superposition, entanglement, and wave-particle duality. From the birth of the quantum idea to the cutting-edge technologies of tomorrow, prepare to have your perception of the universe turned upside down. This is the story of quantum physics, the story of reality itself. Let's explore the quantum basics: atoms, subatomic particles, and Planck's constant. At the heart of quantum mechanics lies a profound and baffling question. Is light a wave, or is it a particle? For centuries, we thought we knew the answer. In the early 1800s, Thomas Young's famous double-slit experiment seemed to settle it. He shone light through two narrow slits and observed an interference pattern on a screen behind them, alternating bright and dark bands. This pattern is a classic signature of waves. Think of ripples in a pond spreading out from 2 points. Where the crests of the waves meet, they amplify, creating a bright band. Where a crest meets a trough, they cancel out, creating a dark band. Case closed, right? Light is a wave. But the quantum world had a shocking surprise. We now know that light is also composed of discrete packets of energy called photons. So what happens if we turn the light source down so low that we fire only one photon at a time? Common sense dictates that each photon, like a tiny bullet, must pass through either the left slit or the right slit. Over time, we should see just two bright bands on the screen, directly behind the slits. But that's not what happens. Incredibly, even when sent one by one, The photons gradually build up the exact same interference pattern as before. It's as if each individual photon somehow passes through both slits at once, interferes with itself, and then lands on the screen as a single localized particle. This is the essence of wave-particle duality. The photon travels as a wave of probability, exploring all possible paths simultaneously. The mystery deepens even further. If we place a detector at the slits to see which path the photon takes, the interference pattern vanishes completely. The very act of observation forces the photon to choose a path and behave like a simple particle. This duality isn't just for light. Electrons, atoms, and even large molecules have been shown to exhibit this strange behavior. It's a fundamental principle of reality, challenging our everyday intuition and forming the bedrock of the quantum revolution. Quantum superposition, Schrödinger's cat, objects existing in multiple states at once. Quantum entanglement, Einstein's spooky action at a distance. From the mind-bending theories we've explored, quantum mechanics has blossomed into a technological revolution that is actively shaping our present and defining our future. It's not just abstract mathematics and philosophical debate, it's the engine behind some of the most powerful tools humanity has ever conceived. Perhaps the most exciting frontier is quantum computing. Classical computers, like the one you're likely watching this on, think in bits, ones and zeros. It's a binary black and white world. But quantum computers operate on a completely different level. They use qubits. Thanks to superposition, a qubit can be a 0, a 1, or both at the same time. And thanks to entanglement, the states of multiple qubits can be linked in a complex dance, no matter how far apart they are. By harnessing these properties, a quantum computer can explore a vast number of possibilities simultaneously. While a classical computer tries every key to a lock one by one, a quantum computer can essentially try them all at once. This incredible power won't replace your laptop, but it promises to solve problems currently impossible for any supercomputer, designing life-saving drugs by simulating molecules with perfect accuracy, creating novel materials with unimaginable properties, and optimizing complex global systems. We are at the dawn of this new computing age, and the possibilities are staggering. But with great power comes great risk. The very same power that allows a quantum computer to design new medicines could also be used to shatter the digital security that underpins our modern world. Most of our current encryption methods rely on mathematical problems that are too difficult for classical computers to solve. For a mature quantum computer, however, breaking this encryption would be trivial. This creates a quantum threat to our banking, communications, and national security. But quantum physics provides not only the poison, but also the antidote, quantum cryptography. The most promising method is quantum key distribution, or QKD. It works on a simple quantum rule. You can't measure something without disturbing it. The key is encoded onto individual photons. If a spy intercepts them, the act of measuring alters the photons, creating detectable errors. This immediately alerts the users to the breach. It's security guaranteed by the laws of physics. While quantum computing feels futuristic, you are already living in a world built by quantum mechanics. Every time you use your smartphone or computer, you are using technology that would be impossible without it. The heart of all modern electronics is the semiconductor, and its behavior is purely quantum. Inside a silicon chip are billions of tiny switches called transistors. Our ability to control the flow of electrons through these transistors depends on understanding quantum concepts like energy bands and quantum tunneling. It was by mastering the quantum behavior of electrons and materials that we learned to create these microscopic switches, paving the way for the entire digital age. And what about the laser? From barcode scanners to the fiber optic cables that carry the internet, lasers are everywhere. The word laser is an acronym for light amplification by stimulated emission of radiation. That stimulated emission is a quantum process. In simple terms, atoms are pumped to a high energy state. One atom releases a photon, which stimulates other excited atoms to release a cascade of identical photons. This creates the perfectly coherent, focused beam of light we know as a laser. Beyond these incredible technologies, the quantum revolution has forced us to confront the deepest questions about the nature of reality itself. For centuries, classical physics gave us a comforting vision of a clockwork universe, a deterministic cosmos where, if you knew the position and momentum of every particle, you could predict the future with absolute certainty. Quantum mechanics shattered this deterministic dream. At the fundamental level, the universe isn't a clock, it's a casino. The wave function doesn't tell us what a particle is doing, but rather the probabilities of what it might be found doing upon measurement. This inherent randomness deeply troubled physicists like Einstein, who famously declared, "God does not play dice with the universe." Yet experiment after experiment has confirmed this probabilistic nature is a core feature of our reality. This leads to an even stranger question. What is reality when we're not looking at it? Does a particle even have a definite position before we measure it? The Copenhagen interpretation suggests properties like position are undefined until measurement forces an outcome. In a sense, the observer helps create the reality they observe. Other interpretations offer even more radical alternatives. The many worlds interpretation proposes that the universe never chooses at all. Instead, every possible outcome of a quantum measurement occurs, each in its own separate, parallel universe. Every time a quantum event happens, the universe branches. In one universe, the particle was found here. In another, it was found there. In this view, there is a near infinite tapestry of parallel realities, and we are simply experiencing one path through it. From the transistors in our pockets, to the philosophical debates about parallel worlds, quantum physics has completely rewritten our understanding of the universe. It took us from a predictable clockwork cosmos to a strange, probabilistic reality woven from uncertainty and potentiality, and the journey is far from over. The greatest challenge in physics today is to unite quantum mechanics with general relativity to create a theory of everything. What will such a theory reveal? Will it explain the mysteries of dark matter and dark energy? Will it tell us what happens in a black hole, or what the universe was like at the Big Bang? Could it even shed light on the nature of consciousness itself? 100 years ago, we had no idea the quantum world even existed. Now, we are harnessing its power and grappling with its profound implications. If the first quantum revolution rewrote the rules of reality, we can only wonder what the next one will reveal. The universe is stranger and more mysterious than we ever imagined, and the quest to understand it is the greatest adventure of all. The quantum realm is the ultimate frontier, a place of deep mystery and infinite possibility. If you're as fascinated by these questions as we are, and you want to continue exploring the cutting edge of science and the fundamental nature of reality, then join our community of curious minds. Subscribe to PhysicsAI for more deep explorations into the cosmos and our quantum world. Thank you for watching.
What if I told you that even black holes, the most powerful objects in the universe, are slowly dying? It sounds impossible. These cosmic titans, with gravity so immense that not even light can escape, are the universe's ultimate symbols of permanence. But in the strange world of theoretical physics, even the eternal has an end. To understand this cosmic paradox, we first need to grasp what a black hole truly is. They are born from the death of colossal stars. When a star at least 20 times more massive than our sun exhausts its nuclear fuel, it collapses under its own immense gravity. This cataclysmic implosion crushes its core into an infinitely dense point called a singularity, creating a region of space-time where gravity is so strong that nothing can escape. This boundary is the event horizon, the point of no return. For a long time, we believed anything crossing it was lost forever, making black holes seem like eternal cosmic prisons. But in 1974, the legendary physicist Stephen Hawking changed everything. By merging Einstein's theory of gravity with the bizarre rules of quantum mechanics, he made a startling discovery. Black holes are not completely black. They must emit a faint thermal glow, now known as Hawking radiation. The secret lies in the quantum vacuum of empty space, which isn't empty at all. It's a fizzing soup of virtual particle pairs that pop into existence and annihilate each other almost instantly. Hawking theorized that if a pair forms right at the event horizon, one particle can fall in while its partner escapes. To an outside observer, it appears as if the black hole itself has just radiated a particle away. Empty space isn't truly empty. It's a seething foam of virtual particles that constantly pop into existence as particle-antiparticle pairs before annihilating each other. But at a black hole's event horizon, if a pair appears, one can fall in while the other escapes. The infalling particle has negative energy, subtracting from the black hole's mass. The escaping particle becomes real, carrying away energy as radiation. This is Hawking radiation, a process ensuring every black hole will eventually evaporate completely. The rate of this evaporation depends on size. A smaller, stellar mass black hole is hotter and radiates away its mass much faster than a colossal supermassive one. A solar mass black hole would take 10 to the 67th power years to disappear. Supermassive black holes, however, will last for an almost eternal 10 to the 100th power years, outliving everything else. This leads to the distant black hole era. After the last stars fade, the universe will be a dark, cold cosmos populated only by these slowly dying giants, silently radiating their mass into the void. As a black hole shrinks, its evaporation accelerates, culminating in a final brilliant flash of gamma rays. It erases itself from existence, leaving behind an almost empty universe filled with a faint whisper of radiation. Black holes may be the kings of the cosmos today, but even kings don't rule forever. Through the slow process of Hawking radiation, they will eventually evaporate over unimaginable timescales. Their story is a profound reminder of cosmic evolution. If you're fascinated by these mysteries, subscribe and join our journey. Explore more mind-bending topics with us right here.
What if the sun suddenly vanished during the day or the moon disappeared at night? Well, these aren't science fiction scenarios. They're real phenomena that happen right here in our solar system. Welcome to PhysicsAI, where we explore the incredible physics of our universe. Today, we're diving into one of nature's most spectacular shows, eclipses. And trust me, the physics behind them is absolutely mind-blowing. Let's start simple. Imagine you have a lamp and a ball. When light from the lamp hits the ball, it creates a shadow. That shadow is simply an area where light has been blocked. Now scale this up to cosmic proportions. We have our sun as the light source, and both Earth and Moon can act as the ball, casting shadows into space. These shadows have two parts, the umbra, which is the dark inner shadow, and the penumbra, the lighter outer shadow. An eclipse happens when the sun, Earth and Moon line up in what astronomers call syzygy. But depending on the order of this alignment, we get two completely different types of eclipses. A solar eclipse occurs when the moon passes between the sun and Earth, casting its shadow on our planet. The moon's shadow races across Earth's surface at over 1,500 miles per hour, creating a path of totality. In a total solar eclipse, the moon completely covers the sun's bright disk, revealing the sun's beautiful corona, its outer atmosphere. In a partial eclipse, the moon only covers part of the sun, creating that famous crescent shape. And in an annular eclipse, the moon appears smaller than the sun, creating a spectacular ring of fire effect. This happens because the moon's orbit is elliptical, so sometimes it appears larger or smaller in our sky. Here's the incredible coincidence. The sun is about 400 times larger than the moon, but it's also about 400 times farther away. This means they appear almost exactly the same size in our sky, making total solar eclipses possible. Remember, never look directly at the sun during an eclipse without proper eclipse glasses. It can cause permanent eye damage. A lunar eclipse is the opposite scenario. Earth passes between the sun and moon, casting Earth's shadow on the lunar surface. Earth casts a much larger shadow than the moon, which is why lunar eclipses last much longer, sometimes over an hour. During a total lunar eclipse, the moon doesn't disappear completely. Instead, it turns a beautiful deep red colour. This happens because Earth's atmosphere acts like a lens, bending red light around our planet and onto the moon's surface. Blue light gets scattered away by our atmosphere, but red light makes it through, giving the moon that eerie blood-red appearance. In a partial lunar eclipse, only part of the moon enters Earth's shadow, and in a penumbral eclipse, the moon only passes through Earth's outer shadow, causing just a subtle dimming. Unlike solar eclipses, lunar eclipses are visible from anywhere on Earth's night side simultaneously. Now you might wonder, if the moon orbits Earth every month, why don't we get eclipses every month? The answer lies in orbital mechanics. The moon's orbit is tilted about 5 degrees relative to Earth's orbit around the sun. This means most of the time the moon passes slightly above or below the Sun-Earth line, missing perfect alignment. Eclipses can only happen when the moon crosses Earth's orbital plane at points called nodes. These alignments create eclipse seasons that occur roughly every 6 months. when we can have multiple eclipses in a short period. On average, any given location on Earth sees a total solar eclipse only once every 375 years, making them incredibly rare and special events. Eclipses are not just cosmic coincidences, they are windows into the precise and beautiful clockwork of our universe. They remind us that we live in a dynamic solar system where celestial mechanics create these incredible natural phenomena. If you love cosmic physics explained simply, subscribe to PhysicsAI for more mind-bending science videos. Until next time, keep looking up and questioning the incredible physics all around us.
What if the loudest sound in the universe wasn't just deafening, but deadly? What if the end of the world wasn't a flash of light or a fiery explosion? What if it was a sound? Not a scream or a bang that you could hear with your ears, but something far more fundamental. A vibration so immense, so overwhelmingly powerful, that it could unravel the very fabric of our planet. Imagine, just for a moment, a wave of pure energy, born from a single catastrophic event, rippling through the ground, rippling through the sea, rippling through the air. To understand how sound could destroy a world, we first have to understand what it is. Sound is simpler than you might think. It's a journey of energy. When you clap your hands, you disturb the air molecules around them, pushing them together. These compressed molecules then push on their neighbors, who push on their neighbors, and so on. This creates a chain reaction, a traveling wave of high and low pressure that ripples through the air. We measure the intensity of this energy using a scale called decibels. A quiet whisper is around 30 decibels. A rock concert might hit 120 decibels, which is the threshold of pain for our ears. Every increase of 10 decibels represents a tenfold increase in sound energy. The scale is logarithmic, meaning it grows incredibly fast. This energy is real, it's physical. A loud enough sound can do more than just hurt your ears, it can exert a physical force. At around 190 decibels, the pressure waves are so intense they can rupture your eardrums and even cause shock waves in the air itself. This is the level of a rocket launch heard from up close. Let's imagine cranking up the volume. Not just to the level of a rock concert, but far, far beyond. At around 200 decibels, the pressure waves would be powerful enough to shatter glass windows and cause structural damage to buildings. Cities would begin to tremble, not from an earthquake, but from the sheer force of the air pressing against them. As we climb higher, the effects become apocalyptic. At 250 decibels, the sound pressure would be so immense it could move the oceans themselves, creating massive tsunamis that would scour the continents clean. The sound would be a physical hammer, striking the planet with relentless force. To actually crack the Earth's crust, we would need a sound of truly astronomical intensity. We're talking about a sound wave with a magnitude somewhere around 300 decibels. A continuous sound at this level would inject so much vibrational energy into the ground that it would liquefy solid rock. The ground would behave like water, creating waves of stone hundreds of feet high. Tectonic plates would grind against each other uncontrollably, triggering earthquakes of a magnitude never before witnessed. The Earth would literally be shaken to pieces from the inside out. But why stop there? Let's consider the energy needed to destroy the planet entirely. The Earth would cease to exist, vaporized into a rapidly expanding cloud of superheated gas and rock, its final scream echoing into the void. As powerful as our imaginary Earth-destroying sound is, the universe honestly plays on an entirely different scale. The loudest sounds in the universe are generated by the most violent events imaginable. Consider a supernova, the explosive death of a massive star. When a star explodes, it releases more energy than our sun will produce in its entire lifetime. This explosion sends a shockwave, a sound wave of unimaginable power, racing through the interstellar gas. But even a supernova, honestly, pales in comparison to the collision of two black holes. When these cosmic titans, each with the mass of millions of suns, spiral in towards each other, they violently warp the fabric of spacetime itself. In the final moments before they merge, they are moving at nearly the speed of light, releasing an incredible burst of energy in the form of gravitational waves. The power released in this single event is more than the light from all the stars in the observable universe combined. If we could somehow translate the energy of that black hole merger into a sound wave in our atmosphere, the decibel level would defy comprehension. And what about the loudest sound of all time? That likely occurred at the very beginning of the universe. During the inflationary period, just a fraction of a second after the Big Bang, the universe expanded faster than the speed of light. This hyperexpansion would have created colossal sound waves, rippling through the hot, dense plasma of the early cosmos. These primordial sound waves, known as baryon acoustic oscillations, were so vast that they stretched for hundreds of thousands of light years. They were the vibrations that helped seed the large-scale structures of the universe, shaping the cosmic web of galaxies we see today. The universe was born in a roar, not a whisper. We have journeyed from a simple clap of the hands to the collision of black holes. We've seen how sound, a mere vibration, can be scaled up to a force of planetary and even galactic annihilation. It forces us to confront the sheer power inherent in the physical laws of our universe. The same energy that carries a melody can, in sufficient quantity, unmake the very matter that melody is played upon. This exploration leads us to a final profound question. We have imagined a sound powerful enough to destroy a planet and even a solar system. But what are the ultimate limits? Is there a theoretical maximum volume in the universe? A point where the energy density of a sound wave becomes so great that it collapses in on itself, forming a black hole made of pure sound? Could a sound wave carry enough energy to tear a hole in the fabric of space-time itself? The laws of physics as we currently understand them suggest there are limits. But what if, in the far future, or in another corner of the multiverse, the rules are different? Could there exist a sound so powerful, a vibration so fundamental, that it could continue to grow in intensity without limit? A wave that could propagate from one universe to the next, a crescendo that never ends. If a sound wave could be amplified indefinitely, could it unravel everything? Could a single ultimate vibration, a final infinite chord, erase all of existence? Could it undo the Big Bang itself, returning the entire cosmos to the silent, featureless singularity from which it came? We may never know the answer, but asking the question expands our imagination and deepens our appreciation for the fragile, beautiful, and sometimes violent symphony of the cosmos. It reminds us that in the grand orchestra of existence, we are both the audience and a fleeting part of the music.
Imagine looking up at the night sky. But tonight, something is profoundly wrong. The familiar, comforting glow of the moon is gone, vanished. Only an unnerving, star-dusted emptiness remains. The darkness feels deeper, more absolute. This is not just a loss of light. It is the beginning of a great unraveling. What if the moon simply disappeared tomorrow? The consequences would be immediate and catastrophic. Our planet suddenly alone set adrift, balance shattered. The first change, the loss of its gentle, silvery light. Nights become impenetrably dark, like the deepest caves. Nocturnal animals timed to the lunar cycle would be plunged into confusion. Predators that hunt by moonlight would starve. Prey that forage by dim light would be forced to rely on sound or smell. The rhythms of life, honed over millions of years, would be broken. Our planet does not sit perfectly upright as it journeys around the sun. It leans. This axial tilt, a gentle inclination of about 23.5 degrees, is the very reason we have seasons: spring, summer, autumn, winter. But this stability is not an accident. It is a gift from the moon. Our large satellite acts like a gravitational gyroscope, a planetary pacifier, holding Earth's tilt steady and preventing it from wobbling chaotically through space. Without the moon's steadying influence, Earth's axial tilt would become dangerously erratic. Over thousands of years, it could swing wildly, perhaps tilting to nearly 90 degrees, like the planet Uranus, or straightening up completely. The seasons as we know them would cease to exist. Instead, we would face periods of unimaginable climate extremes. Imagine a world where the North Pole points directly at the sun for decades. Twice each day, the oceans of our world breathe. They rise and fall in a steady, powerful rhythm. This is the pulse of the planet, the tides, driven primarily by the immense gravitational pull of the moon. As the moon orbits our planet, its gravity tugs on the water, creating a bulge on the side of Earth facing it and another on the opposite side. If the moon were to vanish, this ancient, powerful pulse would not stop entirely, but it would be drastically weakened. The great ocean tides would shrink to less than a third of their current size, becoming mere whispers of their former glory. This dramatic reduction would have immediate and devastating consequences for the intertidal zone. This is the sliver of our world that is both land and sea, a place of incredible biodiversity. Mussels, barnacles, sea stars, crabs. With the tides greatly diminished, vast swaths of these rich ecosystems would be left high and dry, permanently exposed to the air. Weaker tides would mean less mixing, leading to stagnant oxygen pore zones in the ocean. For billions of years, life on Earth was confined to the oceans. It was a world of aquatic creatures, a planet whose land was utterly barren. The great leap from water to land was one of the most pivotal moments. But this momentous step may never have happened without the moon. The vast rhythmic tides driven by the moon's pull form the intertidal zone. Tidal pools were alternately flooded with seawater, then exposed to harsh sun and air. They acted as a crucial evolutionary training ground. Think of these pools as nature's laboratory. Aquatic organisms were repeatedly faced with terrestrial challenges. They had to prevent themselves from drying out. They had to breathe air when the water receded. They had to support their own bodies without water's buoyancy. Creatures with primitive lungs, skin that retained moisture, or fins that propped them up on mud gained an advantage. This zone was the bridge between sea and land. The moon's gravity was the architect of that bridge. Without a large moon to create big tides, the transition zone would have been far less dynamic. When we look at the moon, we do not just see a rock in the sky. We see the ancient force that may have coaxed our most distant ancestors from the sea and set them on the path that would lead to humanity. When the Earth first formed, it spun much, much faster than it does today. A day may have lasted only 6 hours. Over billions of years, the gravitational pull of the moon has acted as a brake, gradually slowing our planet's rotation down to the familiar 24-hour cycle we now experience. If the moon were to disappear, this braking force would be gone. The primary force slowing our planet would vanish. Conservation of angular momentum would take over, and the Earth's rotation would begin to gradually speed up. Days would become shorter. A day might shrink from 24 hours to 20, then 15, then perhaps back to the frantic 6 to 8 hour days of Earth's infancy. A faster spin would completely reshape our planet's weather. The Coriolis effect, the force that creates the rotational patterns of storms like hurricanes, is directly linked to the speed of the planet's rotation. A faster spin would mean a much stronger Coriolis effect. Weather systems would become far more extreme. Winds would howl at incredible speeds, potentially hundreds of miles per hour. Life, which has evolved in rhythm with a 24-hour day, would struggle to adapt. The circadian rhythms of plants, animals, and even humans are deeply ingrained. As we gaze up at the moon, it is easy to see it as a beautiful but passive object, a mere decoration in our night sky, a source of myth and wonder. But its true role is far more fundamental. It is not an ornament. It is a cornerstone of our world's architecture. It is the silent guardian that has held our planet steady, the cosmic partner that has stirred our oceans, the patient guide that may have led life itself onto land. The world without a moon would be an alien planet. It would be a place of violent extremes, of shrieking winds and chaotic climates, a world where the seasons are a lottery of fire and ice. Its oceans would be sluggish and its lands, perhaps, forever barren. The story of Earth is inextricably linked to the story of its moon. They are not two separate bodies, but a single, dynamic system, a partnership forged in a cataclysmic collision billions of years ago. Every ecosystem, every species, every aspect of our planet's climate is, in some small way, a testament to this ancient partnership. So the next time you look up at that familiar luminous orb, remember what you are truly seeing. You are not just looking at a satellite, a piece of rock caught in our gravity. You are looking at the reason our world is not a wobbling, storm-racked wasteland. You are seeing the distant force that stirs our oceans, steadies our seasons, and may have made our very existence possible. The moon is not just a light in the darkness. For all of us on this fragile blue planet, it is a vital part of what makes Earth home. The moon doesn't just light our night skies. It may be the reason we're here at all.
Have you ever gazed up at the night sky on a clear, dark evening, and have you noticed how the stars seem to sparkle and dance, putting on a celestial show just for you, while other bright points of light shine with a steady, unwavering glow? That steady light is very likely a planet, a celestial neighbor in our solar system. Perhaps it's Venus, our brilliant morning star or evening star. Or maybe it's Jupiter, the giant of our solar system, shining brightly. So what accounts for this difference? Why do stars twinkle with such enchanting irregularity, but planets don't seem to join in the dance? The answer to this cosmic riddle isn't hidden out in the vast expanse of space, among the stars themselves. It's actually much closer to home, residing right here on Earth, surrounding us every day. The twinkling, or scintillation of stars is primarily caused by the dynamic nature of our planet's atmosphere. As starlight, after traveling immense distances, finally travels through the turbulent and ever-changing air above us, it bends and shifts in unpredictable ways, a phenomenon known as refraction. This constant bending and unbending of light rays is what makes stars appear to shimmer and twinkle. Planets, on the other hand, present a different picture. They generally shine with a calm, steady glow, resisting the twinkling effect. The star itself isn't actually flickering or changing its light output. It's a stable source of illumination. It's solely the journey its light undertakes through our dynamic and somewhat chaotic atmosphere that creates the twinkling effect we observe. In essence, our atmosphere acts like a giant, imperfect, and constantly shifting invisible lens, subtly and continuously distorting the light emanating from those incredibly distant stars. As that starlight embarks on its journey, traversing trillions of miles of empty space, it maintains a remarkably straight and unwavering path, undisturbed by any atmospheric effects, until the very last instant of its long voyage, just before it reaches our world, when it finally encounters Earth's protective atmospheric layers. And that's when the real fun, or rather, the real distortion, begins. The constantly swirling and mixing layers of air, with their varying temperatures and densities, bend and scatter the incoming light, effectively transforming what was once a steady and direct beam of light into the captivating twinkle we observe from the ground. So, the beloved children's song, "Twinkle, Twinkle, Little Star," is, in a way, a bit misleading from a scientific perspective. The star itself isn't truly twinkling. It's the star's light that's undergoing the twinkling transformation. By delving into this seemingly simple question of why stars twinkle, we gain valuable insights not just about the nature of stars themselves, but also about the characteristics of our own planet, its atmosphere, and our place within the vast and awe-inspiring universe beyond. So, let's dive deeper into the fascinating science behind why stars appear to twinkle in the night sky, and explore the reasons why planets, for the most part, maintain a steadier and more constant glow. Prepare yourself to see the night sky and everything in it in a whole new and illuminating way. The scientific name for twinkling is atmospheric scintillation. It simply means the sparkling effect caused by our atmosphere. Imagine looking at a coin at the bottom of a still pool. It looks clear and steady. But if the water ripples, the coin seems to wiggle and shimmer. That's what happens to starlight as it passes through our turbulent air. This bending of light is called refraction. You've seen it before, like a straw looking bent in a glass of water. Our atmosphere is made of many layers, each with different temperatures and densities. As starlight enters from space, it passes through these shifting layers, bending again and again. Because the air is always moving, the path of the light is constantly changing. This makes the star's image dance and flicker, creating the twinkling effect we call scintillation. It's a dazzling light show, courtesy of our ever-changing sky. That's the science behind the sparkle. Have you ever gazed up at the night sky and wondered, why do stars seem to twinkle with such vibrant energy, while planets, in contrast, appear to shine with a steady, unwavering light? It's a question that has intrigued stargazers for centuries. The answer, surprisingly, comes down to a simple matter of how these celestial bodies appear to us from our vantage point here on Earth. It's all about their apparent size and how their light interacts with our atmosphere. Stars are incredibly far away, so distant in fact that to our eyes, even with the aid of powerful telescopes, they look like single, infinitesimally small points of light. Astronomers refer to these distant objects as point sources because their light originates from what appears to be a single, concentrated location. As a result of this extreme distance, their light reaches us as a thin, incredibly narrow beam, almost like a laser pointer shining across vast distances. This delicate beam is easily disturbed and distorted as it passes through the Earth's turbulent atmosphere, encountering pockets of air with varying temperatures and densities. Planets, while still incredibly distant in their own right, are significantly closer to us than the stars. They reside within our own solar system, relatively nearby on a cosmic scale. Because of their relative proximity, they don't appear as mere points of light. Instead, they appear as tiny, albeit still very small, disks in the sky. This is true even if we can't readily discern that shape with our naked eyes. Telescopes reveal their disk-like nature, even if subtle. To understand the difference, imagine a single, solitary laser beam versus a cluster or bundle of many such beams, all traveling together. If the single beam encounters any disturbance, it will wobble and dance erratically, its path easily deflected. However, the cluster of beams will remain much steadier because the individual disturbances affecting each beam tend to average out across the entire group. And that's precisely what happens with the light from planets as it journeys through our atmosphere. Because their light originates from a small disk rather than a single point, the atmospheric disturbances affecting different parts of the disk tend to cancel each other out, creating a more stable and consistent light source. The end result? Stars twinkle dramatically, their light scattered and distorted, while planets shine with a steady, unwavering glow. This seemingly simple difference in apparent size between a point and a disk is the key that unlocks this celestial mystery. So the next time you gaze up at the night sky and notice a steady, unwavering light shining among a sea of twinkling stars, you're likely looking at a planet, a nearby neighbor in our cosmic backyard. Ultimately, it's all about distance and perspective, how far away these objects are and how they appear to us from our unique vantage point. The universe is a vast and wondrous place full of countless surprises and hidden secrets waiting to be discovered. And sometimes, as we've seen, the smallest details, a subtle difference in apparent size, can make the biggest difference in how we perceive and understand the cosmos. That's the beautiful secret behind the planet's calm, serene glow, a testament to the power of perspective and the wonders of the universe. The journey of starlight as it pierces through our atmosphere is a fascinating one. It's a voyage from the distant cosmos to our very eyes. But this journey is anything but smooth and uneventful. It's a bumpy ride, full of twists and turns. The air above us isn't a uniform blanket. Instead, it's a chaotic mix of constantly moving pockets, swirling and shifting. Each of these pockets possesses different temperatures and densities, creating a constantly fluctuating environment. As a thin ray of starlight, a delicate messenger from afar, enters this turbulent atmospheric layer, it doesn't travel in a straight line. Instead, it bends and zigzags erratically, undergoing these deflections thousands of times each second, a truly rapid and chaotic dance. From our perspective on the ground, this constant bending causes the star to seem to jiggle and flicker, its brightness fluctuating in a mesmerizing way. Sometimes these air pockets, with their varying densities, act like tiny, imperfect lenses, briefly focusing the starlight, making it appear brighter or dimming it, causing it to fade momentarily. This rapid brightening and dimming, this constant oscillation in the star's light, is precisely what we perceive as the enchanting twinkle of a star. Occasionally, under just the right conditions, the atmosphere can even split the star's light, separating it into its constituent colors, creating fleeting flashes reminiscent of a mini prism. Most of the time, these subtle color changes happen far too quickly for our eyes to consciously register, but they contribute to the overall shimmering and ethereal quality of the starlight we observe. So the next time you gaze up and see a star twinkle in the night sky, remember that you're witnessing a complex and beautiful dance, an intricate interaction between light and the air above us. It's a beautiful and humbling reminder, a testament to the wonders of nature, of the powerful yet often invisible atmospheric forces constantly at play in the world above us. The night sky, far from being a static canvas, is actually a dynamic and ever-changing spectacle. Have you noticed stars twinkle more near the horizon? That's no illusion. When a star is low in the sky, its light travels through a thicker slice of atmosphere. The longer slanted path means more turbulence, more bending, and more twinkling. Stars overhead pass through less air, so they appear steadier. That's why astronomers prefer to observe objects high in the sky, where the view is sharpest. If you want to see the most dramatic twinkling, look near the horizon. It's a vivid reminder of the deep ocean of air above us. The next time you're stargazing, notice how the twinkle changes with height. The sky show is always changing, depending on where you look. Even the position of a star can change how it sparkles. So why don't planets twinkle? It's all about how their light reaches us. Planets appear as tiny disks, sending many light rays through the atmosphere at once. Each ray gets bent and jostled, but the effects average out. Our eyes blend all these tiny fluctuations into one steady image. That's why planets shine with a calm, unwavering glow. The atmosphere affects their light just as much as it does starlight, but we can't see the twinkle. It's a perfect example of how size and distance change our view of the universe. So, when you spot a steady light among the twinkling stars, you're seeing a planet. Now you know the secret behind their serene shine. The universe is full of wonders, and sometimes the explanation is right above our heads. Keep looking up. You never know what you'll discover. Twinkling stars are beautiful, but for astronomers, they're a challenge. The atmosphere blurs and distorts images, making it hard to study distant objects. For years, observatories were built on mountaintops to minimize this effect. Today, technology called adaptive optics helps untwinkle the stars. Flexible mirrors and telescopes adjust in real time to correct for atmospheric distortion. This lets astronomers capture sharp, clear images from the ground. Thanks to adaptive optics, we can now see the universe in stunning detail, right from Earth. The next time you see a twinkling star, remember, science is always finding new ways to see the cosmos more clearly.
Look around you. Everything seems solid and real. Tables, chairs, the screen in front of you. We trust the world is stable, that things exist whether or not we're looking. But what if this sense of reality is just an illusion? Physics, especially quantum physics, challenges our most basic assumptions. As we probe deeper, the universe appears less like a machine and more like a shifting landscape, shaped by our observations. Imagine a world that only becomes detailed when you interact with it, like a video game rendering new terrain as you explore. Could reality itself depend on our participation? This journey will reveal a universe far stranger and more mysterious than we ever imagined. For centuries, classical physics painted the universe as a predictable clockwork machine. Everything had a definite position and momentum, whether or not anyone was watching. Reality was objective and independent, like a billiard ball rolling across a table, its path certain even with your eyes closed. This worldview let us build bridges, launch rockets, and trust in the stability of nature. The laws of physics seemed absolute, describing a universe that existed with or without us. But as we looked closer, cracks appeared. At the atomic scale, the rules changed. The certainty of classical physics gave way to the strangeness of quantum mechanics. Suddenly, reality wasn't as solid as we thought. The universe was about to get very, very strange. The double-slit experiment. A cornerstone of quantum mechanics, it's an experiment that continues to baffle and inspire physicists to this day. It elegantly demonstrates the wave-particle duality of matter. Challenging our most basic assumptions about reality, it shattered our classical expectations, forcing us to reconsider the very nature of reality at the smallest scales. The implications of this experiment are profound, touching upon the foundations of physics and our understanding of the universe. Fire electrons one by one towards a barrier. These tiny particles, the fundamental building blocks of matter, are about to reveal a surprising secret. One at a time through two slits, meticulously crafted in a barrier. Classically, we'd expect each electron to pass through one slit or the other. And you'd expect two bands on the screen, corresponding to the electrons that pass through each slit. A simple, predictable outcome, or so it seems. Like tiny billiard balls, each following a definite trajectory. This is what our intuition, based on the macroscopic world, would lead us to believe. But instead, you see an interference pattern, a series of alternating bands of high and low intensity. This is a hallmark of wave behavior, a pattern created by the superposition of waves, as if each electron is a wave, spreading out and interfering with itself. How can a single particle behave like a wave? This is the central mystery of the double-slit experiment, passing through both slits at once. It's as if the electron explores all possible paths simultaneously, a concept that defies classical logic. Each electron seems to exist in a superposition, a combination of multiple states at the same time. It's a blurry, probabilistic existence, unlike the definite reality we experience every day, taking all possible paths until measured. The electron exists in a state of uncertainty, a cloud of potential, until an observation is made. The act of measurement changes everything. It forces the electron to choose a single state, collapsing the superposition. If you check which slit the electron goes through by placing a detector at one of the slits, something remarkable happens. The interference vanishes. The wave-like behavior disappears as if by magic. The electron acts like a particle again, passing through only one slit and creating the expected two bands on the screen. It's as if the electron knows it's being watched and changes its behavior accordingly. This raises profound questions about the role of the observer in shaping reality. The very act of observation, the act of gaining information, fundamentally alters the system being observed, forces it to choose a single reality, a single path, from the multitude of possibilities. This experiment reveals a universe at its most fundamental level, where particles are clouds of probability, existing in a state of potential, not solid objects, with definite properties and fixed locations. Reality at its core is far more fluid and uncertain than our everyday experience suggests, is not fixed until we look, until we make a measurement and collapse the wave function. The double-slit experiment is a window, a glimpse, into the quantum world's deepest mysteries, challenging our understanding of reality itself. Our role as observers, as conscious beings interacting with the universe, is far more active than we ever imagined, shaping the very fabric of reality through the act of observation. The double-slit experiment, a cornerstone of quantum mechanics, leads to the observer effect, a mind-bending concept where the very act of observation observing changes reality. It suggests that the universe isn't a fixed, predetermined entity, but rather, before measurement, an electron exists as a wave of possibilities, a range of potential states, a superposition. It's in multiple places at once, in a probabilistic cloud. Measurement collapses this wave, forcing the electron to choose a single location, into a single outcome, a definite, measurable state. This isn't about human consciousness. It's not about the power of the mind. Any interaction that records information counts. Any process that encodes the state of the electron, the universe chooses a reality, selecting one possibility from many. The moment information is captured, the moment the wave function collapses, quantum properties like position, things we take for granted in our everyday lives, or momentum, the measure of how much force is required to stop something, may not exist until measured. They are created by the act of measurement itself. At the quantum level, reality is participatory. We are active participants in shaping what we perceive, a dynamic process shaped by measurement. It's a dance between possibility and actuality. Our everyday experience hides this strangeness because we are dealing with vast numbers of particles. But at the smallest scales, where quantum effects dominate, reality is fluid and uncertain. It's a realm of probabilities, not certainties. The act of observation sculpts the world, like a sculptor shaping clay, from a haze of possibilities, from a quantum fog of potential realities. This raises a profound question, a question that has puzzled physicists for decades. If reality depends on measurement, what was happening before observers existed, before life emerged? Was the universe indefinite, a vast, unformed potential until something measured it, until the first interaction that recorded information? The quantum world challenges our deepest intuitions. It forces us to rethink our understanding of reality. We are not just spectators, passive observers of a pre-existing universe. We help create reality itself. We are active participants in the unfolding cosmic drama. To make sense of quantum strangeness, physicists developed the Copenhagen interpretation. It says, stop asking what particles really do when unobserved. Physics describes what we can measure, not what is. The quantum world is governed by probabilities, not certainties. Measurement bridges the quantum and classical worlds, collapsing possibilities into outcomes. The universe is fundamentally random. Chance is built into its fabric. The Copenhagen view works, but it leaves many unsatisfied. It avoids the question of why measurement matters, treating the observer as special. For some, this feels like dodging the real mysteries of existence. Dissatisfaction with Copenhagen led to wild new ideas. The many worlds interpretation says every possible outcome happens in parallel universes. When you measure an electron, reality splits in one world, it goes left in another, right. Every quantum event creates new branches of reality. Another view, cubism, puts the observer at the center. Here, the wave function reflects your personal knowledge, not objective reality. Measurement updates your beliefs, not the world itself. Each observer has their own version of reality shaped by experience. Quantum mechanics becomes a tool for navigating uncertainty, not a description of what is. These interpretations make reality more participatory and subjective than we ever imagined. The universe may be a conversation between us and the world, not a fixed stage. Maybe the problem isn't just a missing piece of the puzzle or a gap in our understanding. Perhaps our logic itself, the very foundation upon which we build our understanding, may not fit the quantum world. We've been trying to force a square peg into a round hole, using tools designed for a different reality. Classical logic, the bedrock of our reasoning, dictates that things are either true or false, a simple binary choice. Something is either here or not here, existing or not existing, a definitive state. But quantum logic throws a wrench into this neat dichotomy, allowing for superpositions. These are states that are both and neither, existing in a probabilistic limbo until observed. It's a concept that challenges our fundamental intuitions. The famous double-slit experiment dramatically shows that particles can exist in multiple states simultaneously, a wave of possibilities, until the moment of measurement forces them to choose a single reality. Imagine a video game where a character is both safe and in danger, alive and dead, at the same time. This is until you interact with the game, until you make a choice. What if the universe's underlying code, the very fabric of reality, is written not in the language of classical rules, but in the strange and wonderful language of quantum logic, not in the deterministic clockwork of classical rules? This paradigm shift leads us to the ultimate question. If observation collapses the quantum state, who or what was the first observer? Did the universe exist in a haze of infinite possibilities, a sea of potential realities? Until something, somewhere, measured it, forcing it to coalesce into the reality we perceive? Standing at the edge of knowledge, we confront the profound mystery of existence, a mystery that deepens with every new discovery. And we begin to question our role, our influence, in shaping the very fabric of reality. The quantum world invites us to rethink everything, to challenge the assumptions we thought we knew, and to embrace the beautiful uncertainty that lies at the heart of it all.
Imagine a world free from the constraints of limited energy resources. Imagine solving humanity's energy crisis once and for all. What if we could tap into a virtually inexhaustible power source fueled by something as abundant as seawater? A power source that produces no greenhouse gases, leaving our atmosphere pristine and our skies clear. Imagine a future with no long-lived radioactive waste, eliminating the burden of storing hazardous materials for millennia. And a power source inherently safe, incapable of meltdown, removing the risk of catastrophic accidents. This is the promise of nuclear fusion, the very same process that powers the sun, the source of all life on Earth and every star in the cosmos. For nearly a century since the first inklings of understanding the atom, we've dreamed of harnessing this incredible energy source right here on Earth, building our own miniature suns. But if we already know how stars work, if we understand the fundamental principles, why haven't we built a working fusion reactor, a star in a bottle, here on Earth? The answer is both simple and incredibly complex. Fusion is one of the toughest scientific and engineering challenges humanity has ever undertaken. In essence, we're trying to create and then contain a tiny piece of the sun, achieving and maintaining extreme temperatures, hotter than anything found naturally on Earth, while also dealing with immense pressures far greater than those at the bottom of the deepest ocean, all contained within a perfectly crafted magnetic cage, preventing the superheated plasma from touching the reactor walls. The potential payoff? Clean, virtually limitless energy, a sustainable solution for generations to come. Energy that could fundamentally transform civilization, ushering in an era of unprecedented prosperity and progress. Energy that could lift billions from poverty, providing access to electricity and opportunity, and power our future, sustainably and equitably. Yet, despite decades of dedicated effort by scientists and engineers around the globe, commercially viable fusion power remains tantalizingly just out of reach, a challenge that continues to drive innovation. The core difficulty lies in the incredibly extreme conditions that fusion demands, pushing the boundaries of what's physically possible, conditions far beyond anything we encounter in our daily lives, in our homes, or even in most industrial processes. Achieving, and more importantly, maintaining those extreme conditions with incredible precision and stability, even for a few fleeting seconds, represents a monumental feat of scientific and engineering prowess. So, what exactly makes achieving controlled fusion so extraordinarily hard? What are the fundamental obstacles we face? The answer lies deep within the fundamental forces of nature and the sheer violence needed to overcome those forces and unlock the energy within the atom. To truly understand the magnitude of the challenge, let's take a closer look at the only working fusion reactor we currently know of, our very own Sun. By carefully studying how the Sun achieves fusion naturally, we can begin to truly grasp the immense scale of the scientific and engineering challenge we face in replicating that process here on Earth. Fusion, the process that powers the stars, might seem like an incredibly complex phenomenon, but the basic principle is surprisingly simple in theory. It's all about bringing atomic nuclei together under the right conditions. The core idea is to smash two light atomic nuclei together with such force that they overcome their natural repulsion and fuse into a heavier one. This fusion process releases a tremendous amount of energy, far more than any chemical reaction. This is precisely what happens in the Sun's core, not just every day, but every single second. It's a continuous, ongoing reaction that sustains the Sun's energy output. The Sun, a giant ball composed primarily of hydrogen, possesses the incredible ability to create immense pressure and staggeringly high temperatures within its core. These conditions are absolutely crucial for fusion to occur. We're talking about temperatures soaring to approximately 15 million degrees Celsius. That's hot enough to vaporize any material we know of on Earth. At these extreme temperatures, matter exists in a state known as plasma. In this chaotic environment, hydrogen nuclei are stripped of their electrons, creating a sea of charged particles. Normally, protons, which are the nuclei of hydrogen atoms, repel each other due to their positive charge. It's like trying to push together the same poles of two magnets. You feel a strong resistance. But the Sun's extreme heat and pressure, generated by its immense gravity, force these protons close enough together to overcome that repulsive force. When they get close enough, the strong nuclear force, a fundamental force of nature, kicks in and binds them together, fusing them into helium. This is where the magic happens. This specific sequence of fusion reactions, primarily the proton-proton chain, is the Sun's engine, the source of its incredible power and light. Every single second, the Sun fuses an astounding hundreds of millions of tons of hydrogen into helium. The scale of this process is almost incomprehensible. In doing so, it converts a small fraction of that mass directly into energy, according to Einstein's famous equation E = mc2. This energy reaches us as sunlight, providing warmth and sustaining life on Earth. The Sun's sheer size and immense gravity are what make this process seem relatively straightforward, at least from a cosmic perspective. On Earth, however, we lack that crucial gravitational force. Therefore, we must find alternative and ingenious ways to force atomic nuclei together with sufficient energy to initiate fusion. Replicating this stellar alchemy, achieving fusion without the benefit of a star's massive gravitational field, is the real and significant scientific challenge. We need to artificially create similar conditions to those found in the Sun's core, the same extreme levels of heat and pressure, but within the confines of a laboratory. And that's where the difficulty truly begins, pushing the boundaries of engineering and scientific understanding to their absolute limits. So, let's delve deeper and see how we are attempting to recreate a star's heart right here on Earth, and the innovative technologies being developed to achieve this ambitious goal. The Sun, a colossal fusion reactor in the sky, harnesses the immense power of gravity to compress and heat hydrogen atoms until they fuse. This process releases staggering amounts of energy. We, however, can't replicate the Sun's gravitational forces here on Earth. So instead of gravity, we rely on cutting-edge technology and innovative engineering to achieve the three essential conditions for fusion. These conditions, often referred to as the triple product, are the key to unlocking fusion energy. First, ultra-high temperature. Second, enough pressure. And third, sufficient confinement time, the triple product. This refers to the duration for which we can maintain the plasma at the required temperature and density. Miss any one of these crucial elements and the fusion reaction simply fizzles out, failing to produce any significant energy. It's a delicate balancing act. Let's start with temperature. Achieving fusion on Earth requires heating matter to at least 150 million degrees Celsius. That's 10 times hotter than the sun's core, an almost unfathomable level of heat. At this extreme heat, matter undergoes a dramatic transformation, becoming plasma, a seething soup of positively charged nuclei and negatively charged electrons, all moving at incredible speeds. Next, confinement. Since nothing can physically touch plasma this hot without instantly vaporizing, we use powerful magnetic fields to suspend it in a vacuum, preventing it from contacting the reactor walls. This creates what's known as a magnetic bottle, a carefully shaped field that contains the superheated plasma. Magnetic confinement is currently the leading approach to fusion energy, but building a stable and incredibly strong magnetic cage capable of withstanding these extreme conditions is a monumental engineering feat. Finally, we must keep the plasma stable and confined for a sufficient amount of time, long enough for fusion reactions to occur and release energy, whether that's seconds, minutes, or even longer. The ultimate goal is ignition, achieving a self-sustaining burn where the energy released from fusion reactions is enough to maintain the plasma's temperature, creating a continuous cycle. But plasma is inherently wild and unstable, prone to turbulence and unpredictable behavior, constantly trying to escape the confines of the magnetic field. Therefore, taming these plasma instabilities and maintaining stable confinement is one of the greatest scientific and engineering challenges in the pursuit of fusion energy. Achieving all three of these critical conditions, ultra-high heat, immense pressure, and sustained confinement time, remains the central quest in the global effort to unlock the promise of fusion power. So, the question remains, how do we actually build a magnetic bottle strong enough to contain this superheated plasma and create the conditions necessary for sustained fusion? Enter the tokamak, a leading contender in the race to harness fusion energy. In the 1950s, Soviet scientists invented the tokamak, a donut-shaped magnetic bottle for plasma. The idea: bend the magnetic field into a closed loop so plasma can't escape. Large coils create a toroidal field around the donut, confining the plasma, but that's not enough. Plasma drifts outward, so a second magnetic field is needed. A central solenoid drives a huge current through the plasma, generating a poloidal field. Combined, these fields create a helical magnetic cage, keeping plasma stable. Tokamaks have set records for temperature and confinement, making them the world's leading fusion design. The most ambitious is ITER in France, aiming to prove fusion can produce more energy than it consumes. If successful, ITER will be a turning point for fusion power. But tokamaks aren't the only path. Some scientists saw a flaw in tokamaks. The huge plasma current causes dangerous instabilities. Could we confine plasma without that current? Enter the stellarator. Invented in the 1950s, the stellarator uses twisted, complex external coils to create the helical magnetic field no plasma current needed. This design is incredibly complex, requiring supercomputer simulations and precision engineering. The payoff stellarators are inherently stable and can run continuously, a big advantage for power plants. The Wendelstein 7X in Germany is the world's most advanced stellarator, proving this concept can work. Stellarators are making a comeback thanks to modern technology. The race between tokamaks and stellarators is heating up. The global fusion race is now a showdown, tokamak versus stellarator. Tokamaks are simpler to build and heat plasma efficiently, but their pulsed operation and instabilities are major drawbacks. Stellarators are complex engineering marvels but offer steady, disruption-free operation. Tokamaks, like ITER, hope to solve their instability issues and achieve long pulse operation. Stellarators like W7X bet on stability and continuous running, despite their construction challenges. Each design has strengths and weaknesses, speed and simplicity versus stability and complexity. The winner may depend on which can scale up to commercial power first. Both are pushing the boundaries of science and engineering. The next decade will reveal which path is best, or if a new contender emerges. The fusion race is far from over. Even with advanced designs, fusion faces huge challenges. Plasma is turbulent and unstable, always seeking to escape its magnetic cage. Tokamaks risk sudden disruptions that can damage the reactor. Stellarators avoid these but still battle heat-leaking turbulence. Materials must survive relentless heat and neutron bombardment, far harsher than a spacecraft's re-entry. Scientists are developing new alloys and tungsten components to withstand these extremes. Another challenge: breeding tritium fuel inside the reactor, using lithium blankets to capture neutrons. Solving these problems is as tough as confining plasma itself. Why pursue fusion despite the challenges? Because the reward is civilization changing. Fusion uses deuterium from seawater and tritium bred from lithium fuel for millions of years. It produces no carbon emissions, no long-lived radioactive waste, and only harmless helium. Reactor components become mildly radioactive but decay safely within decades, not millennia. Fusion is inherently safe. If anything goes wrong, the reaction stops instantly, no meltdown, no runaway chain reaction. Only a few grams of fuel are inside at any time, minimizing risk. Clean, abundant, and safe fusion is the holy grail of energy. That's why the quest continues, with passion and determination. The world's future could depend on it. In 2025, fusion's future is brighter than ever. Will the tokamak, led by ITER, deliver the first commercial fusion power, or will the Stellarator's stability win out? ITER's success could cement the tokamak as the first generation of fusion plants. Stellarators, with their continuous operation, may prove better for the long run. Meanwhile, startups are exploring new concepts: compact tokamaks, linear devices, and more. A breakthrough could come from anywhere. The final chapter isn't written yet, but one thing is certain: building a star on Earth is humanity at its most ambitious, and its success will change the world forever. Imagine the universe moments after its birth, a time when everything we know was condensed into an incredibly hot and dense point, a singularity. This was the beginning of everything, the dawn of time and space itself. The Big Bang's energy crackles, a chaotic soup of particles colliding at unimaginable speeds. This explosion set the stage for the universe's expansion, creating a seething, roiling mass of energy and matter. In this extreme environment, some physicists believe defects arose in the very fabric of space-time, like cracks in newly formed ice. These defects are not just random occurrences, but are thought to be fundamental features of the universe. These hypothetical defects, known as cosmic strings, are thought to be incredibly thin, perhaps thinner than a proton, yet stretching across vast distances, potentially even spanning the entire observable universe. Imagine a thread so fine yet so long that it could weave through the entire cosmos. These are not the strings of string theory, which operate on a much smaller scale. Cosmic strings are a different concept entirely, existing on a scale that boggles the mind. Cosmic strings, if they exist, are remnants of the universe's earliest moments, wrinkles in the fabric of space-time itself. They are like scars left over from the universe's violent birth, holding clues to its most profound secrets. Their existence, while still theoretical, is a captivating possibility that could reshape our understanding of the cosmos and perhaps even unlock the secrets of time travel. The idea that these strings could influence the flow of time is both thrilling and perplexing. The search for cosmic strings is a testament to our insatiable curiosity about the universe. Astronomers and physicists alike are driven by the desire to uncover these elusive threads, scanning the night sky for any hint of their presence. It reflects our desire to understand the most fundamental laws of physics and to unravel the mysteries of our cosmic origins. The quest to find cosmic strings is more than just a scientific endeavor. It's a journey to understand our place in the universe. The possibility, however remote, that these cosmic threads hold the key to time travel adds an extra layer of intrigue to this already fascinating area of research. If proven true, it could revolutionize our understanding of time and space, opening doors to possibilities we can only dream of. One of the most mind-boggling aspects of cosmic strings is their predicted density. Imagine compressing the mass of Mount Everest into something smaller than an atom. That's the kind of extreme density we're talking about with cosmic strings. This incredible density arises from the way cosmic strings are thought to have formed as defects in the very structure of space-time itself. Despite their immense density, cosmic strings would be incredibly difficult to detect. Their thinness, combined with their vast distances from Earth, makes them frustratingly elusive for even our most powerful telescopes. However, their extreme density means they would have a profound effect on the space around them, warping the fabric of space-time in a manner unlike anything else in the universe. This warping of space-time, a consequence of Einstein's theory of general relativity, is key to understanding how cosmic strings might enable time travel. Their immense gravitational pull could, in theory, be harnessed to create shortcuts through space-time, allowing us to journey through time as well as space. Albert Einstein's general theory of relativity revolutionized our understanding of gravity. Before Einstein, gravity was thought to be a force acting at a distance, as described by Isaac Newton. However, Einstein's theory introduced a radical new concept. It tells us that gravity is not a force acting at a distance, but rather a curvature of space-time caused by mass and energy. This means that massive objects like stars and planets warp the very fabric of the universe around them. Imagine a bowling ball placed on a trampoline, causing the fabric to sag. Smaller objects placed on the trampoline will naturally roll towards the bowling ball, not because they are being pulled by a force, but because the fabric is curved. This is a simple analogy for how massive objects warp the fabric of space-time around them. The more massive the object, the greater the curvature, and thus, the stronger the gravitational effect. Cosmic strings, with their immense density, would create even more extreme distortions in space-time. These hypothetical one-dimensional defects in the fabric of the universe could stretch across vast distances. Instead of a gentle sag, imagine a deep, narrow well running along the length of the string. This well would be incredibly steep, creating a dramatic effect on the surrounding space-time. This well would not only affect objects moving near the string, but could also create unusual pathways through space-time, potentially allowing for time travel. The intense gravitational fields could bend space-time in such a way that closed time-like curves, or loops in time, might be possible. This warping of space-time is not merely a theoretical curiosity. It has been observed and confirmed in various ways. Scientists have detected gravitational waves, ripples in space-time caused by massive cosmic events, which further validate Einstein's predictions. For example, the bending of starlight around massive objects, a phenomenon known as gravitational lensing, provides direct evidence for the curvature of space-time predicted by Einstein's theory. This effect allows us to observe distant galaxies and stars that would otherwise be hidden from view. If cosmic strings exist, their extreme density would create even more dramatic lensing effects, potentially offering a way to detect them. These cosmic phenomena could open new windows into understanding the fundamental nature of our universe. In the 1990s, physicist J. Richard Gott proposed a fascinating idea. What if we could use the space-time warping abilities of cosmic strings to create closed time-like curves, loops in space-time that could enable time travel? These cosmic strings, hypothetical one-dimensional defects in the fabric of space-time, are thought to be incredibly dense and possess immense gravitational pull. Gott's idea relies on the fact that near a cosmic string, space-time is so warped that it's possible for an object to travel in a loop and arrive back at its starting point in both space and time. This warping effect is due to the immense gravitational forces exerted by the cosmic string. Imagine two cosmic strings passing each other at high speed. The interaction between their gravitational fields could create a unique and extreme warping of space-time. The combined gravitational effects of these strings could potentially warp space-time so severely that a closed, time-like curve would form. This curve would essentially be a loop in time, allowing for the possibility of time travel. A spaceship traveling along this curve could, in theory, travel back in time, arriving at a point in space-time before it even left. This concept, while mind-bending, is grounded in the principles of general relativity. While this idea sounds like something out of science fiction, it is based on the established laws of physics as we understand them. The mathematics behind it is sound, but the practical implementation is another story. Of course, there are many practical challenges to overcome before we could even dream of building a time machine based on Gott's idea. The energy requirements alone would be astronomical, and we have yet to even confirm the existence of cosmic strings. Nonetheless, the concept opens up fascinating possibilities for the future of time travel and our understanding of the universe.
Imagine a star, heavier than our sun, dying. This colossal entity, having burned for millions of years, reaches the end of its life cycle. The fuel that once powered its radiant glow is exhausted, and the star begins to collapse under its own immense gravity. It explodes as a supernova, a cataclysmic event that outshines entire galaxies for a brief moment. The explosion sends shockwaves through the cosmos, scattering elements that will one day form new stars, planets, and perhaps even life. Its core collapses, crushed by its own gravity. This implosion is so intense that it forces protons and electrons to merge into neutrons, creating an incredibly dense object. This is how neutron stars are born. These remnants are the cores of massive stars left behind after the outer layers have been blown away. Neutron stars are stellar ghosts, denser than imaginable. They pack more mass than our sun into a sphere just a few kilometers across. A teaspoonful would weigh billions of tons. This unimaginable density is due to the neutrons being packed so closely together, creating a state of matter unlike anything we experience on Earth. These extreme objects spin rapidly. Some neutron stars, known as pulsars, rotate hundreds of times per second, emitting beams of radiation as they spin. They emit powerful beams of radiation. These beams sweep across space like cosmic lighthouses, and when they point towards Earth, we can detect them as regular pulses of radio waves. These cosmic lighthouses offer a glimpse into extreme physics. The study of neutron stars helps scientists understand the behavior of matter under the most extreme conditions. They exist at the edge of our understanding. The extreme conditions within neutron stars challenge our theories of physics and push the boundaries of what we know about the universe. Their fate is a cosmic mystery. Some neutron stars may eventually collapse further to become black holes, disappearing from view and leaving us with more questions than answers. Stars are cosmic furnaces, the brilliant powerhouses of the universe. They fuse hydrogen into helium through a process known as nuclear fusion, releasing immense amounts of energy. This fusion process powers them for billions of years, allowing them to shine brightly and sustain their immense heat and light. Eventually, stars exhaust their nuclear fuel. When this happens, gravity takes over, causing the star to collapse under its own weight. For massive stars, this collapse is particularly violent. This catastrophic collapse triggers a supernova explosion, one of the most powerful events in the universe. During the supernova, the core of the star is compressed to incredible densities, far beyond what we can imagine on Earth. In this extreme environment, protons and electrons are squeezed together so tightly that they combine to form neutrons. This process results in the creation of neutron stars, aptly named for their composition. These remnants are incredibly small, only a few miles across, yet they are among the densest objects in the universe. Despite their small size, neutron stars pack the mass of the Sun into a sphere no larger than a city, showcasing the extreme density and unique nature of these stellar remnants. Neutron stars defy gravity. Their extreme density creates outward pressure. This balances the inward pull of gravity. This precarious balance has a limit. The Tolman-Oppenheimer-Volkoff, or TOV limit, is critical. It defines the maximum mass a neutron star can have. It's a cosmic tightrope walk. Imagine a balloon. You can only inflate it so much. The TOV limit is like that. Exceed it, and the star collapses. The inevitable collapse. Some stars are born heavy. Their supernova remnants exceed the TOV limit. Gravity becomes unstoppable. The neutron star shrinks. Imagine a force squeezing the star. It gets smaller and denser. Nothing can stop this collapse, not even the strong nuclear force. The star's density approaches infinity. Space-time warps infinitely. This is the birth of a black hole. A new cosmic chapter. Black holes are cosmic enigmas. They are regions of space-time where gravity is extreme. Nothing, not even light, can escape. The collapsed neutron star becomes a singularity, a point of infinite density. The surrounding region is the event horizon. Cross the event horizon, and there's no turning back. It's a one-way ticket to oblivion. Black holes are the ultimate cosmic prisons. Understanding neutron stars and black holes is crucial. They reveal the extremes of physics. They test the limits of our knowledge. These objects probe gravity's power. They offer insights into the evolution of stars. They challenge our understanding of space and time. By studying them, we unravel the cosmic tapestry. We gain a deeper understanding of our universe's grand design. In the vast expanse of the universe, our Milky Way galaxy is just one of billions. Yet, it is our home, a tiny speck in the grand cosmic arena. From neutron stars to black holes, the cosmos is a stage. These celestial objects, with their immense gravitational forces, play pivotal roles in the universe's structure and evolution. It hosts a grand cosmic ballet. Stars and galaxies move in a delicate dance, influenced by the invisible threads of gravity, creating a mesmerizing spectacle that has fascinated humanity for millennia. Stars are born, evolve, and die. In the stellar nurseries of nebulae, new stars ignite, shining brightly for millions or even billions of years before ending their lives in spectacular supernovae. This cosmic dance shapes the universe. The remnants of dead stars, like cosmic dust and gas, become the building blocks for new stars and planets, continuing the cycle of creation and destruction. It creates the elements necessary for life. The fusion processes within stars forge elements like carbon, oxygen, and iron, which are essential for the formation of planets and ultimately life itself. We are all connected to this cosmic drama. Every atom in our bodies was once part of a star, linking us intrinsically to the universe and its ongoing story. Understanding these cosmic events humbles us. It reminds us of our small place in the grand scheme of things, yet also of our unique ability to comprehend and appreciate this vastness. It reminds us of the vastness and wonder of the universe. The sheer scale and beauty of the cosmos inspire awe and curiosity, driving us to explore and understand more. It sparks our curiosity to explore further. As we venture into space, we seek not only to uncover the mysteries of the universe, but also to find our place within it, continuing the timeless quest for knowledge and discovery.
Have you ever gazed up at the night sky and wondered why the moon always shows us the same face? It's a question that has captivated skywatchers for centuries. This celestial phenomenon, where one side of the moon perpetually faces Earth, is known as tidal locking. In this cosmic exploration, we'll delve into the fascinating world of tidal forces, orbital mechanics, and the intricate dance between Earth and its lunar companion. Join me as we unravel the mysteries behind the moon's unchanging gaze. Throughout history, cultures around the world have woven myths and legends around the moon, attributing its unchanging face to gods, goddesses, and celestial beings. While these stories add a touch of magic to our understanding of the cosmos, the true explanation lies in the realm of physics. By understanding the fundamental forces that govern the universe, we can unlock the secrets behind this celestial spectacle. From our vantage point on Earth, it appears as though the moon doesn't rotate. Night after night, we are greeted by the same familiar craters, mountains, and lunar seas. This has led to the misconception that the moon has a dark side, a hidden hemisphere, shrouded in perpetual darkness. However, this is a cosmic fallacy. The moon, like Earth, rotates on its axis. It's just that its rotation period is perfectly synchronized with its orbit around our planet. This synchronous rotation means that as the moon orbits Earth, it also spins on its axis at precisely the right rate to keep the same face pointing towards us. Imagine two people walking side by side, with one person always facing the other. The person facing inward would need to turn their body as they walk to maintain this orientation. Similarly, the moon's rotation is synchronized with its orbit to keep the same hemisphere facing Earth. The phenomenon responsible for the moon's synchronized rotation is known as tidal locking or synchronous rotation. It's a celestial dance orchestrated by the invisible force of gravity. Just as Earth's gravity tugs on the moon, keeping it in orbit, the moon's gravity exerts a pull on our planet. This gravitational tug-of-war is what gives rise to tides in Earth's oceans. Tidal forces are differential forces, meaning they vary in strength depending on the distance between objects. The side of Earth facing the moon experiences a stronger gravitational pull compared to the side facing away. This difference in gravitational force creates bulges of water on opposite sides of Earth, resulting in high tides. As Earth rotates, these tidal bulges move across the planet's surface, causing the familiar rise and fall of ocean levels. Section 4, Unraveling the Physics, How Gravity Shapes the Moon's Rotation. Now, how did the Moon become tidally locked to Earth? Billions of years ago, when the solar system was in its infancy, the moon was spinning much faster than it is today. However, Earth's gravitational pull on the moon's tidal bulges acted as a brake, gradually slowing down its rotation. Over vast stretches of time, this braking effect brought the moon's rotation into sync with its orbital period, resulting in the tidal locking we observe today. It's important to note that tidal locking is not a one-way street. While the moon's gravity has a more noticeable effect on Earth's oceans, it also has a subtle influence on our planet's rotation. The tidal bulges created by the moon exert a slight drag on Earth's spin, causing our planet's rotation to gradually slow down over time. This means that in the far distant future, Earth's rotation will also become tidally locked to the moon, and one Earth day will be as long as a lunar month. Section 5. The Far Side. A hidden hemisphere unveiled. For centuries, the far side of the moon remained a tantalizing mystery. Hidden from our view, it sparked imaginations and fueled speculation. However, thanks to space exploration, we have lifted the veil on this hidden hemisphere. In 1959, the Soviet spacecraft Luna 3 captured the first images of the far side of the moon, revealing a landscape starkly different from the familiar face we see from Earth. Unlike the near side, which is characterized by vast lunar seas, dark flat plains formed by ancient volcanic eruptions, the far side is heavily cratered and mountainous. This difference in appearance is thought to be due to variations in the lunar crust and the history of asteroid impacts. The far side's lack of large lunar seas suggests that volcanic activity was less prevalent in this region. Section 6. Beyond the Moon. Tidal locking in the solar system and beyond. Tidal locking is not unique to the Earth-Moon system. In fact, it's a relatively common phenomenon throughout the cosmos. Many moons in our solar system are tidally locked to their host planets, including Jupiter's moon, Europa, and Saturn's moon, Titan. Even Pluto and its largest moon, Charon, are tidally locked to each other, perpetually facing one another in a celestial waltz. Beyond our solar system, astronomers have discovered exoplanets, planets orbiting other stars, that are tidally locked to their host stars. These planets, known as hot Jupiters due to their size and proximity to their stars, have one side perpetually facing the scorching heat, while the other side remains in perpetual darkness. Section 7, Conclusion, a timeless waltz in the cosmic ballet. The moon's unchanging face is a testament to the power of gravity and the vastness of cosmic timescales. Over billions of years, the invisible force of gravity has choreographed a celestial dance between Earth and its lunar companion, resulting in the tidal locking we observe today. This phenomenon, once a source of myth and speculation, is now understood as a fundamental principle of celestial mechanics. As we gaze up at the moon, we are reminded that the cosmos is a place of constant motion and change, even when those changes unfold over eons. The moon's hidden side, once shrouded in mystery, is now a testament to human ingenuity and our insatiable thirst for exploration. And as we continue to explore the universe, we are sure to uncover even more wonders that challenge our understanding and ignite our imaginations.
If a tree falls in a forest and no one is around to hear it, does it make a sound? This age-old philosophical riddle has puzzled thinkers for generations, challenging our understanding of reality and perception. This question isn't just a whimsical thought experiment. It probes the very nature of existence and our role as observers in the universe. It asks us to consider the relationship between the physical world and our sensory experiences. Sound, we know, is a vibration that travels through a medium, such as air, and is then detected by our ears. These vibrations are converted into electrical signals that our brains interpret as sound. But what if there were no ears to hear? Would the vibrations still exist? The vibrations would still occur, but without an observer, the experience of sound would be absent. Most would say yes, arguing that the existence of sound is independent of an observer. They would claim that the physical processes that create sound waves are objective realities, unaffected by human presence. But what if we take this question to the quantum realm? where the very act of observation seems to influence the outcome of events. In this microscopic world, the rules of classical physics no longer apply. What if reality itself behaves differently when observed? In the quantum world, particles can exist in multiple states simultaneously, a phenomenon known as superposition. The world of quantum mechanics, the physics that governs the universe at its smallest scales, is a realm of perplexing paradoxes and mind-bending possibilities. It challenges our conventional understanding of reality. Here, particles can exist in multiple states at once, blurring the lines between what we perceive as real and what exists as a ghostly potential. This duality is at the heart of quantum mechanics. It is a realm where the act of observation seems to play a crucial role in shaping the very fabric of reality. The observer effect suggests that the mere act of measuring or observing a quantum system can alter its state. This perplexing interplay between the observer and the observed lies at the heart of one of the most profound mysteries in modern science, the observer effect in quantum mechanics. It raises questions about the nature of consciousness and its role in the universe. Does consciousness, the very essence of our being, somehow influence the world around us at the most fundamental level? Could our awareness be intertwined with the fabric of reality itself? Or is there a deeper, more subtle explanation for this strange entanglement of mind and matter? The answers to these questions could reshape our understanding of the universe. The implications of this question extend far beyond the realm of theoretical physics, challenging our very understanding of the nature of reality and our place within it. It touches on philosophy, metaphysics, and the essence of existence. Join me as we delve into the heart of this quantum enigma, exploring the experiments, interpretations, and philosophical debates that have captivated scientists and philosophers for over a century. Together, we will uncover the mysteries that lie at the intersection of observation and reality. Our journey begins with a seemingly simple experiment that would forever alter our perception of the quantum world. The double-slit experiment, a cornerstone of quantum mechanics, reveals the strange and counterintuitive nature of particles and waves. Imagine a wall with two narrow slits cut into it. This setup might seem simple, but it forms the basis of one of the most intriguing experiments in the history of science. Behind the wall is a screen that can detect the passage of tiny particles, such as electrons. This screen is highly sensitive and can capture even the smallest interactions, providing us with a detailed map of where each particle lands. Now, picture firing a beam of electrons at the wall. These electrons are tiny, almost unimaginably small, and they travel at incredibly high speeds. What kind of pattern would you expect to see on the screen? Would it be random, or would there be some order to it? Common sense suggests that the electrons would pass through the slits and create two distinct bands on the screen, much like tiny bullets leaving their mark on a target. This is what we would expect if electrons behaved purely as particles. However, the quantum world has a different story to tell. When this experiment, known as the double-slit experiment, is actually performed, something truly remarkable occurs. Instead of two distinct bands, we observe an interference pattern on the screen, a series of light and dark fringes that is characteristic of waves, not particles. This pattern is similar to what you would see if you were to drop two pebbles into a pond and watch the ripples interact. This pattern arises because, in the quantum realm, particles like electrons can behave as both waves and particles, a phenomenon known as wave-particle duality. This duality is one of the cornerstones of quantum mechanics and challenges our classical understanding of physics. But the mystery deepens if we try to observe which slit each electron passes through. By placing a detector near one of the slits, the interference pattern disappears. This suggests that the act of measurement itself has a profound impact on the behavior of the electrons. The act of observation seems to force the electrons to choose a path, collapsing their wave-like nature and revealing their particle-like behavior. This is a direct manifestation of the observer effect, where the mere act of observing a quantum system can alter its state. This bizarre phenomenon, often referred to as the observer effect, is one of the most compelling pieces of evidence suggesting that consciousness, or at least the act of observation, may play a fundamental role in shaping quantum reality. It raises profound questions about the nature of reality and the role of the observer in the universe. It is as if the electrons know they are being watched and change their behavior accordingly. This idea challenges our traditional notions of objectivity and suggests that the universe at its most fundamental level is deeply interconnected with the act of observation. How can the mere act of observation, of gaining knowledge about which slit an electron passes through, influence the outcome of the experiment? This question has puzzled scientists and philosophers alike for decades. Does this imply that our minds, our consciousness, can directly affect the physical world at the quantum level? If so, what does this mean for our understanding of reality and our place within it? The double-slit experiment, in all its simplicity and elegance, reveals the profound strangeness of the quantum world and the deep mysteries that lie at the heart of our understanding of reality. It challenges us to rethink our assumptions and opens up new avenues of inquiry into the nature of the universe. As we continue to explore the quantum realm, we may uncover even more surprising and mind-bending phenomena that will further challenge our understanding and expand our horizons. The journey into the quantum world is just beginning, and it promises to be an exciting adventure filled with discovery and wonder.
Imagine never truly dying. Imagine a reality where the end is just the beginning of another journey. Imagine a reality where every choice, every decision you make creates a new path, a new universe. Every possible outcome, every potential future, exists in an infinite expanse of parallel universes. Each universe is a reflection of the myriad possibilities that stem from our actions. This is the captivating allure of quantum immortality, a concept that suggests our consciousness might transcend the boundaries of our physical existence. Quantum immortality intertwines science fiction with the bizarre world of quantum mechanics, proposing that our essence continues in another universe when we face death in this one. It suggests that death, as we perceive it, might be an illusion, a mere transition to another reality within the vast multiverse. Imagine a world where our consciousness seamlessly shifts from one universe to another, a transition to another reality within the vast multiverse where every version of us continues to live, explore, and experience. The idea, while mind-boggling, stems from the many worlds interpretation of quantum mechanics. This theory posits that all possible alternate histories and futures are real, each representing an actual world or universe. A theory that challenges our fundamental understanding of reality, suggesting that the universe is much more complex and interconnected than we ever imagined. Could it be that our consciousness, like an eternal flame, simply flickers on in another universe, untouched by the demise of our physical bodies in this one? This eternal flame of consciousness might continue to burn brightly across the multiverse. Untouched by the demise of our physical bodies in this one, our consciousness might walk through the portals of the multiverse, exploring new realms and realities. Let's delve into the science and explore the implications of this captivating yet controversial theory. Join us as we journey through the fascinating world of quantum mechanics and the mysteries of the multiverse, uncovering the secrets that lie beyond our current understanding. Imagine a coin toss. Heads or tails, a simple binary outcome. But what if this simple act was more complex than it seems? Now imagine that instead of one outcome, both occur, but in different universes. Each flip of the coin creates a new reality. This is the essence of the many worlds interpretation. It suggests that every possible outcome of a quantum event actually happens, but in separate, parallel universes. Every quantum event, every decision, every possibility splits the universe into countless branches, each representing a different outcome. Imagine the vastness of possibilities. In one universe, you might choose to eat a salad for lunch. In another, you savor a juicy burger. Each choice, no matter how small, creates a new branch of reality. Each choice creates a new reality, a parallel existence where all possible outcomes manifest. The implications are profound. This dizzying concept, while lacking direct experimental proof, offers a compelling explanation for the probabilistic nature of quantum mechanics. It challenges our understanding of reality and opens up a universe of infinite possibilities. Quantum immortality takes the many worlds interpretation a step further. If every possible outcome exists in some parallel universe, then a universe must exist where you never die, at least not in the traditional sense. Imagine surviving a fatal car crash in this reality only to find yourself unscathed and bewildered in another. While your consciousness ceases in the original timeline, it continues in the parallel universe where the accident never happened. This unending chain of survival of consciousness hopping across universes forms the crux of quantum immortality. Section 4. Echoes of Infinity Near-Death Experiences and Beyond. Could near-death experiences be glimpses into these parallel realities? People who've had near-death experiences often describe vivid sensations of light, peace, and even encounters with deceased loved ones. While these experiences can be explained by neurological phenomena, the possibility, however remote, that they represent a brief foray into a parallel universe is both intriguing and unsettling. Perhaps our consciousness, even for a fleeting moment, brushes against the fabric of the multiverse. Section 5. The Skeptic's Lens, Unraveling the Enigma. However enticing the concept of quantum immortality may seem, it's crucial to approach it with a healthy dose of skepticism. The scientific community remains divided on the validity of the many worlds interpretation, let alone its implications for immortality. Critics argue that the theory lacks testability, a cornerstone of scientific rigor. Furthermore, the sheer extravagance of infinite universes raises questions about energy conservation and the very nature of reality. While the idea is captivating, it remains, for now, in the realm of speculation. Section 6. A reality redefined your existence in the multiverse. Despite the lack of scientific consensus, the concept of quantum immortality forces us to confront our place in the cosmos. If our consciousness persists across a multitude of universes, what does it mean to be alive? What defines our identity if we exist in infinite variations across the multiverse? These questions, while currently unanswerable, challenge us to expand our perception of reality. Perhaps our understanding of life and death is merely limited by our current understanding of the universe's true nature. Section 7. Join the cosmic conversation. What do you believe? The concept of quantum immortality, while rooted in complex scientific theories, ultimately boils down to a matter of belief. It challenges our understanding of life and death, suggesting that consciousness might continue in an alternate reality. Imagine a world where every decision you make creates a new branch of existence, a new version of you. This theory, while speculative, opens up fascinating possibilities about the nature of our universe and our place within it. Do you entertain the possibility of a reality where death is not an ending but a transition? This idea can be both comforting and unsettling. It suggests that our journey doesn't end with our physical demise, but continues in another form, in another dimension. This perspective can change how we live our lives, how we make decisions, and how we perceive our own existence. Does the idea of infinite versions of yourself, living out every possible scenario, spark excitement or trepidation? The multiverse theory suggests that every possible outcome of every decision you make is played out in an alternate universe. This means there could be countless versions of you, each experiencing a different reality. This concept can be thrilling, offering endless possibilities, but it can also be daunting as it challenges our sense of individuality and uniqueness. Share your thoughts, your beliefs, your fears. Engaging in this cosmic conversation allows us to explore these profound ideas together. By discussing and debating, we can expand our understanding and perhaps find comfort in the shared human experience. Your perspective is valuable, and your voice adds to the rich tapestry of ideas that shape our collective understanding of existence. The universe is vast, and our understanding of it is constantly evolving. As we learn more about the cosmos, we uncover new mysteries and new questions. This journey of discovery is never-ending, and each new piece of information brings us closer to understanding the true nature of reality. Our quest for knowledge drives us to explore the unknown and to seek answers to the most profound questions. Engage in the cosmic conversation, and let's explore the mysteries of existence together. By coming together and sharing our insights, we can push the boundaries of what we know and venture into the realms of what we can only imagine. The universe is a vast, wondrous place, and our collective curiosity is the key to unlocking its secrets. Join us in this journey, and let's discover the wonders of existence, one conversation at a time.
Have you ever wondered if the choices you make are truly your own? Or are we simply cogs in a giant pre-programmed machine, our destinies already written in the fabric of the cosmos? This is the fundamental question at the heart of the debate about free will versus determinism. Determinism, a concept deeply rooted in classical physics, posits that everything in the universe is predetermined. Think of the universe as a giant clock. Every tick and tock, every movement of its gears, is a consequence of the previous state of the clock. Similarly, determinism suggests that the universe, governed by immutable physical laws, unfolds in a predictable and inevitable manner. From the largest galaxy to the smallest atom, everything dances to a predetermined tune. This idea is deeply unsettling to some. If our choices are merely consequences of prior events, what does that say about our sense of agency, our belief that we are the masters of our own fate? Do we have any control over our lives, or are we just along for the ride, our paths already laid out before us by the ironclad laws of physics? Now let's delve deeper into this deterministic view of the universe. Imagine, if you will, a hypothetical being with infinite intelligence and knowledge, Laplace's demon. This all-knowing entity, conceived by the French mathematician Pierre-Simon Laplace, possesses complete knowledge of the universe's current state. Armed with this knowledge and the unchanging laws of classical physics, particularly Newtonian mechanics, Laplace's demon can, in theory, predict the future with absolute certainty. Every event, from the fall of an empire to the flutter of a butterfly's wings, becomes knowable, predictable, and inevitable. This thought experiment brilliantly illustrates the implications of hard determinism. If the universe operates like a giant, perfectly predictable machine, then free will, as we commonly understand it, might be a mere illusion. Our choices, desires, and aspirations would be nothing more than predetermined outcomes of the universe's initial conditions and the laws that govern it. But wait, there's more to the story. As we delve further into the mysteries of the cosmos, we encounter Albert Einstein's groundbreaking theory of relativity. Relativity challenges our intuitive understanding of time, suggesting that it's not absolute, but rather relative to the observer's frame of reference. Imagine two people, one standing still, and the other traveling at near the speed of light. Time would pass differently for both individuals. The one traveling at high speed would experience time dilation, where time slows down relative to the stationary observer. This mind-bending concept suggests that our perception of time as a linear, forward-flowing entity might be an illusion. This leads us to the block universe theory, which proposes that the past, present, and future all exist simultaneously within the fabric of space-time. Imagine a loaf of bread where each slice represents a moment in time. The entire loaf, all moments coexisting, is the block universe. This perspective challenges the notion of free will even further. If all moments already exist, are our choices truly free, or are they just points along a predetermined path in this static, unchanging block? Section 4. Quantum Mechanics. Introducing uncertainty into the equation. Just when we thought we had a handle on the deterministic universe, quantum mechanics, the study of the very small, throws a wrench into the works. Unlike the predictable, clockwork universe of classical physics, the quantum realm is inherently uncertain. The Heisenberg uncertainty principle, a cornerstone of quantum mechanics, states that we cannot simultaneously know both the position and momentum of a particle with perfect accuracy. The more precisely we know one, the less we know about the other. This inherent uncertainty isn't due to limitations in our measuring tools, but rather a fundamental property of the quantum world. This inherent randomness at the quantum level challenges the deterministic view of the universe. If the building blocks of reality behave unpredictably, can we truly say that everything is predetermined? Could this quantum indeterminacy be the source of true randomness in the universe, potentially leaving room for free will to operate? Section 5. The Many Worlds Interpretation, a Universe of Infinite Choices. Let's dive deeper into the rabbit hole of quantum mechanics. One fascinating interpretation of quantum uncertainty is the many worlds interpretation. This mind-boggling theory proposes that every quantum measurement, every interaction at the subatomic level, causes the universe to split into multiple parallel universes, each representing a different outcome. Imagine, for instance, that you're faced with a choice to eat an apple or a banana. In one universe, you choose the apple, while in another, you opt for the banana. Each choice creates a new branch of reality, a parallel universe where that outcome unfolds. The many worlds interpretation suggests that all possible outcomes of every quantum event are realized in some parallel universe. If this interpretation holds true, it paints a fascinating, albeit dizzying, picture of reality. Our lives become an exploration of countless parallel universes, each representing a different path we could have taken. This perspective reintroduces the concept of choice, although in a dramatically different light. We may not have free will in the traditional sense, but our choices could determine which branch of reality we experience. Section 6. The brain, a biological machine making choices for us. Now let's shift our focus from the vastness of the cosmos to the intricacies of the human brain. Neuroscience, the study of the brain and nervous system, offers intriguing insights into the biological basis of decision-making. Some neuroscientific studies suggest that our brains might be making decisions before we're even consciously aware of them. For example, experiments using brain imaging techniques such as fMRI have shown that certain brain regions display activity related to a decision moments before a person consciously reports making that decision. This raises the question, if our brains are already making choices before we're consciously aware of them, how much control do we truly have over our decisions? Of course, correlation doesn't equal causation. Just because there's neural activity before a conscious decision doesn't necessarily mean free will is an illusion. It could be that our conscious awareness simply lags behind the unconscious processes already underway in the brain. Nevertheless, these findings raise fascinating questions about the nature of consciousness and the extent to which we truly control our thoughts and actions. Section 7. Free will or illusion? A question that continues to puzzle. So, where does this leave us in the grand debate about free will? We've journeyed from the deterministic clockwork universe of classical physics to the mind-bending realms of quantum mechanics and the mysteries of the human brain. We've encountered thought-provoking concepts like Laplace's demon, the block universe, the many worlds interpretation, and pre-conscious decision-making. The question remains, do we have free will, or is it all an elaborate illusion, a trick of our consciousness? The answer, my friends, is far from simple. The universe continues to reveal its secrets to us, and with each discovery, new questions arise. Perhaps free will exists, not in absolute terms, but rather as a spectrum, influenced by a complex interplay of deterministic factors and quantum randomness. As we delve deeper into the mysteries of the cosmos and the human mind, we must remain open to new possibilities, embracing the wonder and uncertainty that comes with exploring the universe's greatest enigmas. Ultimately, the question of free will challenges us to think critically about the nature of reality, consciousness, and our place in the grand scheme of things. A question that will likely continue to fascinate and perplex us for generations to come.
Imagine stepping out your front door one morning to find yourself not on your familiar street, but on a street remarkably similar, yet subtly different. The air feels the same, the sky is the same shade of blue, but something is off. You can't quite put your finger on it, but the world around you feels like a distorted mirror image of your own reality. The houses are painted in unfamiliar colors, hues that seem almost too vibrant, too surreal to be real. It's as if an artist with a wild imagination has taken a brush to the neighborhood, creating a palette that defies the norms of your everyday life. The trees are a species you've never seen before, their leaves shimmering with an otherworldly glow. They stand tall and proud, casting strange shadows that dance on the pavement in patterns you've never encountered. And the faces passing by are unknown, each person a stranger in what should be your own neighborhood. They move with a purpose, yet their expressions are foreign, their mannerisms slightly off-kilter. You feel a shiver run down your spine. Have you stumbled into a parallel universe? The thought sends a thrill of fear and excitement through you. What if this isn't just a dream or a figment of your imagination? What if you've truly crossed the boundary into another reality? This isn't just the stuff of science fiction. For decades, writers and filmmakers have tantalized us with tales of alternate realities and parallel worlds. But what if there's more truth to these stories than we ever dared to believe? The idea of a multiverse, a vast ensemble of possibly infinite universes existing alongside our own, has captivated physicists, philosophers, and the public alike. It's a concept that challenges our understanding of existence and pushes the boundaries of what we consider possible. What if our universe, vast as it seems, is just one of many, each with its own unique set of laws, constants, and possibilities? Imagine a cosmos where every decision you've ever made has spawned a new reality, a new universe branching off from the old. This essay delves into the mind-boggling concept of the multiverse. We'll explore the scientific theories that suggest its existence and ponder the philosophical implications of living in a reality that is but one of countless others. We will explore the leading scientific theories that suggest its existence, from the inflationary cosmos giving rise to bubble universes, where each bubble is a separate universe with its own distinct properties, to the mind-bending implications of quantum mechanics, which propose that every possible outcome of a quantum event actually occurs, each in its own separate universe. And then there's string theory, with its hidden dimensions and the potential for multiple universes existing in parallel, each one a different vibration of the same fundamental strings. Join me on a journey beyond the familiar, as we explore the potential existence of unseen worlds. We'll venture into the unknown, seeking to understand the true nature of reality and our place within it, and grapple with the profound implications of a reality far grander than we ever imagined. The multiverse theory not only expands our understanding of the cosmos, but also invites us to reconsider our own lives and choices within this vast interconnected web of existence. The multiverse, in its simplest form, is the theoretical concept of multiple universes coexisting. Our observable universe, with its billions of galaxies stretching out as far as our telescopes can see, might just be a tiny bubble in a much larger cosmic structure. Think of it like this. Our universe is a single soap bubble, drifting alongside countless others in a vast, ever-expanding foam of multiversal possibilities. But what form do these other universes take? How do they relate to our own? These questions lie at the heart of multiverse theory. There isn't just one answer, as different theoretical frameworks within physics give rise to different multiverse models. One compelling picture of the multiverse emerges from the theory of cosmic inflation. This theory posits that in the first fraction of a second after the Big Bang, the universe underwent an exponential expansion. Imagine a tiny balloon being inflated to the size of a galaxy in less than the blink of an eye. That's inflation. But what if this inflationary process didn't end everywhere at the same time? This is where the concept of eternal inflation comes in. In this scenario, pockets of space could stop inflating while others continue, creating a kind of cosmic bubble bath. Each bubble would then become its own universe, with potentially different properties and physical laws. Another path to the multiverse comes from the strange world of quantum mechanics. This field, which delves into the very fabric of reality, offers a perspective that is both mind-bending and revolutionary. Quantum mechanics doesn't just describe the behavior of particles, it challenges our very understanding of existence. This theory governs the interactions of particles at the atomic and subatomic level, and it presents us with a reality that is inherently probabilistic. Unlike the deterministic world of classical physics, where outcomes are predictable, quantum mechanics introduces a level of uncertainty and randomness. Particles don't have fixed positions or velocities until they are observed. Instead of particles having definite properties, they exist in a superposition of states, like a coin spinning in the air before landing on heads or tails. This superposition means that particles can be in multiple states at once, only settling into a single state when measured. It's as if reality itself is undecided until we look at it. The many worlds interpretation of quantum mechanics, developed by physicist Hugh Everett III, suggests that every time a quantum measurement is made, every time the metaphorical coin lands, the universe splits, creating a separate branch of reality for each possible outcome. This means that for every decision or event, there is a universe where each possible outcome is realized. In one universe, the coin lands on heads, in another, it lands on tails. This branching doesn't just apply to simple events like coin flips, it extends to every choice and action, no matter how trivial or significant. Each decision we make could potentially create a new universe. Each choice, no matter how small, could spawn a new world. From the mundane decisions like what to eat for breakfast, to life-changing choices like career paths or relationships, every action has the potential to create a new branch of reality. The multiverse is a vast, ever-expanding tapestry of possibilities, woven from the countless choices made by every particle, every person, and every moment in time. String theory, a leading candidate for a theory of everything, offers yet another intriguing glimpse into the multiverse. This theory aims to unify all fundamental forces of nature, including gravity, electromagnetism, and the strong and weak nuclear forces, into a single, coherent framework. By doing so, it seeks to bridge the gap between general relativity, which describes the large-scale structure of the universe, and quantum mechanics, which governs the behavior of particles at the smallest scales. String theory proposes that the fundamental building blocks of the universe are not point-like particles, but tiny, vibrating strings. These strings can vibrate at different frequencies, and each unique vibration corresponds to a different particle. This elegant idea suggests that all the diverse particles we observe, from electrons to quarks, are simply different vibrational modes of these fundamental strings. Just like the different vibrations of a violin string produce different musical notes, the different vibrations of these fundamental strings give rise to all the particles and forces we observe in nature. This analogy helps us visualize how a single underlying entity can manifest in a multitude of forms, much like how a single instrument can produce a symphony of sounds. However, string theory requires the existence of extra spatial dimensions beyond the three we experience in our everyday lives. These additional dimensions are necessary for the mathematical consistency of the theory and allow for the rich variety of physical phenomena we observe. In fact, string theory suggests there could be as many as 10 or even 11 dimensions, each playing a crucial role in the fabric of reality. These extra dimensions are thought to be curled up and hidden from view, much like a garden hose might appear as a one-dimensional line from a distance, even though it has a two-dimensional surface. This concept, known as compactification, means that these dimensions are compacted into incredibly small scales, making them imperceptible to our current instruments and senses. The way these extra dimensions are curled up or compactified could determine the physical laws and constants of our universe. The specific shape and size of these compactified dimensions influence the types of particles and forces that can exist, potentially explaining why our universe has the particular properties it does. This intricate dance of dimensions and vibrations offers a tantalizing glimpse into the deeper structure of reality, hinting at a universe far more complex and beautiful than we can currently imagine. Section 6. Can we prove the multiverse? The idea of the multiverse is undoubtedly captivating, but is it scientifically sound? Can we ever hope to prove or disprove its existence? While directly observing another universe seems highly improbable, there might be subtle ways to find evidence of the multiverse's influence on our own. One potential avenue of investigation lies in the cosmic microwave background radiation. This faint afterglow of the Big Bang provides a snapshot of the early universe. Some physicists believe that collisions between our bubble universe and others might have left detectable imprints on the CMB, like bruises on the surface of a balloon. Section 7. Living in a multiverse: philosophical implications. The philosophical implications of the multiverse are as profound as the scientific ideas themselves. If our universe is just one of many, does that diminish its significance? What does it mean for our understanding of our place in the cosmos? The multiverse challenges our notions of uniqueness and purpose. It suggests that the laws and constants of our universe, once considered fundamental, might be just one particular set of possibilities in a much larger cosmic landscape. This realization could lead to a sense of cosmic humility, a recognition that we are but one small part of an unfathomably vast and complex reality. Section 8. The unending quest for cosmic understanding. The quest to understand the multiverse is still in its infancy. The theories are bold, the questions are profound, and the answers remain elusive. But this is the nature of scientific exploration. We push the boundaries of our knowledge, driven by curiosity and a desire to comprehend the universe and our place within it. Whether or not we ultimately prove the existence of other universes, the very act of investigating these ideas expands our cosmic perspective. It forces us to confront the limits of our understanding and embrace the possibility of a reality far stranger and more wondrous than we ever imagined. Section 9. A tapestry of unseen worlds. The multiverse, with its promise of unseen worlds and infinite possibilities, is a concept that captures the imagination. It challenges us to rethink our place in the cosmos and embrace the vastness of the unknown. While the search for definitive proof continues, the very idea of the multiverse serves as a powerful reminder of the boundless wonder and mystery that lie at the heart of our existence. Perhaps, just beyond the veil of our perception, a tapestry of unseen worlds awaits, each with its own story to tell, forever intertwined with our own.
Imagine stepping into a booth, pressing a button, and in the blink of an eye, instantly appearing on the other side of the world. This is the captivating dream of teleportation, a concept long relegated to the realm of science fiction. From Star Trek to countless sci-fi novels, teleportation has captured our imaginations. Yet, in the bizarre world of quantum mechanics, teleportation is not merely fantasy. It's a scientific reality, albeit in a form more subtle and complex than typically portrayed. While we may not be beaming ourselves across continents anytime soon, the principles of quantum teleportation offer a tantalizing glimpse into a future where information, not physical matter, travels instantaneously across vast distances. Imagine the possibilities: instant communication, secure data transfer, and revolutionary advancements in computing. This revolutionary technology hinges on the mind-boggling principles of quantum mechanics, a realm where particles behave unlike anything we experience in our everyday lives. The future of teleportation may not look like the sci-fi movies, but it promises to be just as exciting. Quantum teleportation isn't about dematerializing objects and reassembling them elsewhere. Instead, it focuses on transferring quantum information, the fundamental properties that define a particle's state, from one location to another. Think of it like sending a blueprint, not the actual object. This information is encoded in the delicate quantum states of particles, such as the spin of an electron or the polarization of a photon. These states are incredibly fragile, susceptible to collapse upon the slightest interaction with their environment. The challenge lies in transferring this delicate information without disturbing its integrity. The key to this extraordinary feat lies in a peculiar phenomenon known as quantum entanglement. Imagine two particles linked in such a way that they share the same fate, no matter how far apart they are. This interconnectedness, dubbed spooky action at a distance by Einstein, is the bedrock of quantum teleportation. When entangled particles are measured, their fates are intertwined. If one particle is found to be spinning up, its entangled partner instantly assumes the opposite spin, even if separated by light years. This instantaneous correlation forms the invisible channel through which quantum information is teleported. Section 4. The Teleportation Tango, a Quantum Choreography. In the realm of quantum mechanics, teleportation isn't just a figment of science fiction, it's a fascinating reality. Quantum teleportation is a delicate dance involving three actors: Alice, Bob, and a pair of entangled particles. This intricate process allows the transfer of quantum information from one location to another without physically moving the particles themselves. Alice possesses the qubit, the quantum bit of information. She wants to teleport to Bob. A qubit is the fundamental unit of quantum information, representing a superposition of states. They each receive one of the entangled particles. Entanglement is a unique quantum phenomenon where particles become interconnected, such that the state of one instantly influences the state of the other, no matter the distance. Alice performs a joint measurement on her qubit and her entangled particle, causing their fates to intertwine. This measurement collapses the qubit's state, entangling it with the particle. This measurement yields a set of classical bits, ordinary information that can be transmitted through conventional channels. These bits are crucial as they carry the information needed to reconstruct the qubit's state. Meanwhile, Bob's entangled particle undergoes a transformation based on Alice's measurement results. This change is instantaneous, thanks to the entangled nature of the particles. Alice transmits her classical bits to Bob, who then uses this information to manipulate his particle. The transmission of these bits can be done through any classical communication channel, such as the internet or a secure line. By applying specific operations guided by Alice's message, Bob can reconstruct the original qubit state onto his particle, effectively completing the teleportation. This process, though complex, showcases the incredible potential of quantum mechanics in revolutionizing communication and information transfer. Section 5. Quantum leaps in computing and communication. Quantum teleportation holds immense promise for revolutionizing information technology. One of its most significant applications lies in the realm of quantum computing. By enabling the transfer of qubits between different parts of a quantum computer, teleportation could pave the way for building large-scale, fault-tolerant quantum computers. Moreover, quantum teleportation could revolutionize communication, enabling the development of ultra-secure communication networks. The act of eavesdropping on an entangled system would inevitably disturb the delicate quantum states, alerting the communicating parties to the intrusion. Section 6. The allure of instantaneous information. The prospect of instantaneous information transfer holds a certain allure, captivating our imaginations with visions of a world connected in unforeseen ways. While quantum teleportation doesn't violate the cosmic speed limit imposed by the speed of light, it offers a tantalizing glimpse into the potential for instantaneous communication. Imagine a world where information could be shared instantly between distant space probes and Earth, revolutionizing space exploration. Picture a future where global communication networks operate with unparalleled speed and security, transforming how we interact and share information. Section 7. Quantum Horizons, a future ripe with possibilities. Quantum teleportation is still in its infancy, a nascent technology with vast, untapped potential. This groundbreaking field is capturing the imagination of scientists and technologists around the globe. The idea that information can be transmitted instantaneously across vast distances without any physical medium is nothing short of revolutionary. While teleporting humans or objects remains firmly in the realm of science fiction, the ability to teleport quantum information could usher in a new era of technological advancement. Imagine a world where data transfer is instantaneous, secure, and immune to traditional hacking methods. This could transform industries, from telecommunications to cybersecurity and beyond. As we delve deeper into the enigmatic world of quantum mechanics, we unlock the secrets to manipulating the very fabric of reality. The principles of superposition and entanglement are not just theoretical constructs, they are the keys to a new technological revolution. Quantum teleportation, once a theoretical curiosity, is now a stepping stone on our journey towards a future shaped by the boundless possibilities of the quantum world. The implications are profound, promising advancements that could redefine our understanding of communication, computation, and even the nature of reality itself. Imagine a world painted in a single vibrant hue. That's how physicists once viewed the cosmos. They believed a single elegant force governed everything. However, as we delved deeper, the universe revealed its true complexity. We discovered a multitude of forces, each playing a unique role. These forces dictate the dance of particles, the birth of stars, and the very fabric of space-time. But what if this division is an illusion? What if, at the universe's core, a single unified force binds everything together? This is the tantalizing possibility driving the search for the grand unified theory, or GUT. GUT represents one of the most ambitious pursuits in physics, to weave the tapestry of the cosmos from a single thread. It's a quest for ultimate simplicity amidst apparent complexity, a journey towards an equation that could unlock the universe's deepest secrets. This quest isn't just about scientific curiosity. It's about understanding our place in the universe. It's about questioning the very nature of reality. It's about peering beyond the veil of the known and glimpsing the elegant machinery of existence itself. The grand unified theory, at its heart, is an elegant idea. It proposes that the seemingly disparate forces governing our universe are, in fact, different manifestations of a single fundamental force. Imagine a prism splitting white light into a rainbow of colors. GUT envisions the opposite, merging those colors back into a unified beam. This unification wouldn't just be a mathematical trick, it would revolutionize our understanding of the universe's building blocks. To grasp the significance of GUT, we need to meet the players in this cosmic drama, the four fundamental forces. First, we have the strong force, the glue that binds atomic nuclei. It's incredibly strong but operates over tiny distances. Then there's the weak force, responsible for radioactive decay. It's weaker than the strong force and acts over even shorter distances. Next comes electromagnetism, the force behind light, electricity, and magnetism. It's much weaker than the strong force but acts over infinite distances. Finally, we have gravity, the force of attraction between objects with mass. It's the weakest of all but governs the large-scale structure of the universe. GUT aims to weave these four forces into a single, harmonious framework. It's a bold vision, a quest to find the universe's source code, the elegant equation that underpins the symphony of existence. The dream of unification is not new. It has captivated the minds of scientists for centuries. Sir Isaac Newton took the first giant leap in the 17th century. He showed that the same force, gravity, governs both falling apples and orbiting planets. This unification of celestial and terrestrial mechanics was a landmark achievement. Then came James Clerk Maxwell in the 19th century. He unified electricity and magnetism into a single force, electromagnetism. This unification led to groundbreaking technologies like radio and telecommunications. In the 20th century, physicists tackled the challenge of unifying the electromagnetic and weak forces. This led to the development of the electroweak theory, a triumph confirmed by experiments. Today, the pursuit of a grand unified theory continues, driven by the desire to bring gravity into the fold. This task proves to be the most challenging, pushing the boundaries of theoretical physics and demanding innovative experimental approaches. Section 4. The fundamental four forces shaping reality. To truly appreciate the ambition of Gouet, we need to delve deeper into the four fundamental forces. These forces aren't just abstract concepts, they are the architects of reality, shaping everything from the smallest atoms to the largest galaxies. The strong force, true to its name, is the strongest of the four. It acts like a powerful glue, holding together quarks, the fundamental particles that make up protons and neutrons. Without it, atomic nuclei would fly apart, and matter as we know it would cease to exist. The weak force, though less powerful, plays a crucial role in the universe's evolution. It's responsible for radioactive decay, the process by which unstable atoms transform into more stable ones. This process powers stars and is essential for the creation of elements heavier than hydrogen and helium. Electromagnetism is perhaps the most familiar force in our daily lives. It governs the behavior of electrically charged particles and is responsible for light, electricity, magnetism, and the interactions between atoms and molecules. It's the force that allows us to see, to feel warmth, and to interact with the world around us. Finally, we have gravity, the weakest but most far-reaching of the four. It's the force that holds the Earth in orbit around the Sun, shapes galaxies, and governs the large-scale structure of the universe. Despite its weakness, gravity's influence is undeniable, shaping the cosmic landscape on a grand scale. Section 5. Gravity's dance card, the challenge of unification. Unifying the four fundamental forces is like completing a challenging puzzle, with gravity being the elusive final piece. The strong, weak, and electromagnetic forces have been successfully woven together in the standard model of particle physics, but gravity, like a solitary dancer, resists joining the waltz. The heart of the problem lies in the vastly different ways these forces operate. The standard model describes forces through the exchange of particles. Gravity, on the other hand, is described by Einstein's theory of general relativity, which attributes it to the curvature of space-time. These two frameworks, while incredibly successful in their own domains, seem fundamentally incompatible. Another challenge lies in the extreme energy scales required to probe the unification of gravity with other forces. These energies are far beyond the reach of current particle accelerators, making experimental verification incredibly difficult. Despite these challenges, physicists remain optimistic. The pursuit of a grand unified theory is a testament to our insatiable curiosity and our drive to understand the universe at its deepest level.
Gravity. It's the force that holds us to the Earth, guides the Moon in its orbit, and binds galaxies together across unimaginable distances. It's a fundamental force of nature, woven into the very fabric of the cosmos. For centuries, our understanding of gravity was shaped by the brilliant mind of Isaac Newton. But in the early 20th century, Albert Einstein revolutionized our view of the universe with his groundbreaking theory of general relativity. Einstein's theory didn't just refine Newton's laws, it fundamentally changed how we understand gravity, revealing it not as a force acting across space, but as the curvature of space-time itself. Isaac Newton's law of universal gravitation, published in 1687, was a triumph of science. It stated that every object in the universe attracts every other object with a force proportional to their masses and inversely proportional to the square of the distance between them. This elegantly simple law explained the falling apple, the Moon's orbit, and the motions of the planets with remarkable accuracy. Newton's law remained essentially unchallenged for over 2 centuries, becoming a cornerstone of classical physics. However, as our understanding of the universe deepened, cracks began to appear in Newton's seemingly perfect theory. Astronomers observed slight anomalies in the orbit of Mercury that couldn't be explained by Newton's laws. Additionally, Newton's theory treated gravity as an instantaneous force acting at a distance, a concept that felt at odds with the emerging understanding of light and electromagnetism. Enter Albert Einstein. In 1905, he published his theory of special relativity, which revolutionized our understanding of space and time. Special relativity showed that space and time were not absolute, but were interwoven into a single four-dimensional fabric called space-time. This fabric was not merely a backdrop for events, but an active participant in the drama of the cosmos. Building upon special relativity, Einstein spent the next decade developing his masterpiece, the general theory of relativity. Published in 1915, general relativity provided a radical new explanation for gravity. Einstein proposed that gravity was not a force at all, but rather a consequence of the curvature of space-time. Section 4. Warped space-time gravity's true nature. Imagine a bowling ball placed on a trampoline. The ball's weight causes the trampoline surface to curve downward. Now imagine rolling a marble across the trampoline. Instead of traveling in a straight line, the marble's path will curve as it follows the contours of the warped trampoline surface. This analogy, while imperfect, helps visualize Einstein's concept of gravity. Massive objects like stars and planets warp the fabric of space-time around them. This curvature dictates the paths of objects moving through space-time, just as the bowling ball's weight dictates the path of the marble on the trampoline. These paths, called geodesics, are not the result of a force, but rather the natural trajectories of objects through curved space-time. Section 5. Einstein's equations, the language of gravity. At the heart of general relativity lie Einstein's field equations. These 10 interrelated equations, expressed in the language of tensor calculus, describe the relationship between the distribution of mass and energy and the curvature of space-time. While the mathematics of general relativity is highly complex, the underlying concept is profound. Mass and energy tell space-time how to curve, and curved space-time tells mass and energy how to move. Think of the sun. Its immense mass warps the space-time around it, creating a gravitational well. Earth, following its geodesic through this warped space-time, orbits the sun not because of a mysterious force, but because it's following the natural curvature of space-time created by the sun's mass. Section 6. Proof in the cosmos. Evidence for general relativity. Einstein's theory, while elegant and revolutionary, needed observational evidence to support it, and evidence did come, validating general relativity in spectacular fashion. One of the first and most famous confirmations came in 1919 during a total solar eclipse. British astronomer Arthur Eddington observed that starlight passing near the sun was slightly bent, precisely as predicted by general relativity. This bending was due to the sun's gravity warping the path of the starlight. Another striking confirmation is gravitational time dilation. Einstein predicted that time slows down in stronger gravitational fields. This effect, though tiny, is measurable and has profound implications for technologies like GPS satellites. These satellites rely on extremely precise timekeeping to determine location. To account for the slower passage of time in orbit, corrections based on general relativity must be applied. Perhaps the most dramatic confirmation came in 2015 with the detection of gravitational waves by the Laser Interferometer Gravitational Wave Observatory, or LIGO. These ripples in spacetime, generated by cataclysmic events like the collision of black holes, were predicted by Einstein a century earlier. Their detection not only vindicated Einstein's theory, but opened a new window into the cosmos, allowing us to study the universe in a way never before imagined. Section 7. The Universe Unveiled. Black Holes, Cosmology, and Beyond. General relativity has profoundly impacted our understanding of the universe on the grandest scales. It's the cornerstone of modern cosmology, providing the framework for understanding the evolution of the universe from the Big Bang to the present day. It explains the existence of black holes, regions of space-time where gravity is so strong that nothing, not even light, can escape. However, despite its successes, general relativity is not the final word on gravity. One of the biggest challenges in modern physics is reconciling general relativity with quantum mechanics, the theory that governs the subatomic world. These two pillars of modern physics seem incompatible at their core, suggesting that a deeper, more fundamental theory is needed to unify them. Einstein's theory of general relativity stands as one of the greatest intellectual achievements in human history. It has revolutionized our understanding of gravity, space, and time, revealing a universe stranger and more wondrous than we ever imagined. Yet, it also reminds us that our journey of cosmic discovery is far from over. As we continue to probe the universe's deepest mysteries, we may find that even Einstein's mind-bending theory is just a stepping stone on the path to a deeper and even more profound understanding of the cosmos. The question remains, what other secrets does the fabric of space-time hold, waiting to be unveiled?
Look around you. What do you see? You might spot a window, a drinking glass, or even the screen you're reading this on. What do these objects have in common? They're all made of glass, a material so commonplace that we rarely stop to ponder its remarkable properties. The most obvious, of course, is its transparency. But have you ever wondered why glass lets light pass through while other materials like a wooden table or a brick wall remain stubbornly opaque? The answer lies in the fascinating world of atoms and photons, the tiny particles that make up everything around us, including light. Let's embark on a journey to unravel the science behind glass's transparency, exploring the fundamental laws of physics that govern this everyday phenomenon. To understand why glass is transparent, we must first understand the nature of light itself. Light is not just a simple beam. It is a complex phenomenon that has intrigued scientists for centuries. Light, that ethereal phenomenon that bathes our world in warmth and color, is a form of electromagnetic radiation. It encompasses a wide range of wavelengths, from the visible spectrum that we can see to the invisible realms of ultraviolet and infrared. Imagine light as a wave, similar to the ripples on a pond, but instead of water, it's made up of oscillating electric and magnetic fields. These fields interact with the materials they encounter, influencing how light behaves. These waves of light travel at an astonishing speed, the fastest in the universe, covering approximately 300,000 kilometers in just 1 second. This incredible speed allows light to traverse vast distances in the cosmos. When these waves encounter matter, they can be reflected, absorbed, or transmitted, depending on the properties of the material. The interaction between light and matter is a fundamental aspect of our understanding of the physical world. Transparent materials like glass allow light to pass through them with minimal absorption or scattering. This unique property makes glass an essential material in various applications, from windows to lenses. But how does this happen at the atomic level? The answer lies in the unique structure of glass. The arrangement of atoms in glass allows light to pass through without significant hindrance, making it an invaluable material in both everyday life and advanced technology. Imagine a bustling city with skyscrapers representing atoms. In most solid materials like the aforementioned brick wall, these atoms are arranged in a highly ordered repeating pattern, like a well-planned city grid. This rigid structure is what makes these materials opaque. When light waves encounter this organized lattice, they get absorbed by the atoms or bounce off in different directions, preventing them from passing through. Glass, on the other hand, is different. Its atomic structure is more akin to a frozen liquid, a state known as an amorphous solid. It's like the city suddenly froze mid-activity, with buildings haphazardly placed, lacking any long-range order. This seemingly chaotic arrangement is the key to glass's transparency. Section 4. Light's journey through glass. A game of billiards? Not quite. While billiards is a game of precision and angles, the journey of light through glass is a dance of physics and nature. Now let's picture a beam of light approaching a sheet of glass. This isn't just a simple interaction, it's a fascinating process that reveals much about the nature of light and materials. Unlike a solid wall, where light waves get blocked by the organized atoms, glass presents a different scenario. The loosely packed, disordered structure of glass allows light to interact differently. This disordered arrangement is key to understanding how light can pass through. Instead of being absorbed or reflected, the light photons essentially squeeze through the gaps between the atoms. It's almost like the light is threading a needle through the fabric of the glass. Think of it like this. Imagine trying to navigate a crowded room. The way you move through the crowd can be compared to how light moves through glass. If everyone is standing in neat rows, it's difficult to make your way through. The organized structure acts as a barrier, but if the crowd is more haphazardly arranged, you can weave your way through the gaps. This is similar to how light navigates through the disordered structure of glass. This is a simplified explanation, of course. The actual process is more complex and involves intricate interactions at the atomic level. The actual interaction involves the light's energy being absorbed and re-emitted by the electrons in the glass atoms. This absorption and re-emission process is what allows light to pass through. However, the net effect is that the light continues its journey through the material, maintaining its path but with some changes, albeit with a slight delay due to the time taken for these interactions to occur, which is why we see objects on the other side of the glass. This delay is imperceptible to us, but it's a crucial part of the light's journey. Section 5. The limits of transparency when glass turns opaque. While we perceive glass as transparent, it's important to note that it's not transparent to all types of light. Different wavelengths of light interact with glass in various ways, leading to some fascinating effects. Ultraviolet radiation, for instance, which is responsible for sunburns, is largely blocked by glass. This is why you don't get sunburned when sitting behind a window, even on a sunny day. This is because UV light has a higher energy level than visible light. The higher energy photons are absorbed by the glass, preventing them from passing through. The electrons in the glass molecules absorb this higher energy, preventing the UV radiation from passing through. This absorption process is crucial in protecting us from harmful UV rays. Similarly, infrared radiation, which we perceive as heat, is also partially blocked by glass. This is why you can feel the warmth of the sun through a window, but not as intensely as if you were outside. This is why greenhouses work. They trap the sun's heat inside. The glass allows visible light to enter, which warms the interior surfaces. The glass allows visible light to enter and warm the interior, but the infrared radiation emitted by the heated objects inside is partially blocked, keeping the greenhouse warmer than the outside environment. This selective transparency of glass is what makes it such a unique and useful material in various applications. Section 6. Glass, a versatile material with surprising applications. From windows and bottles to fiber optic cables that carry vast amounts of information across continents, glass plays a vital role in our modern world. Its transparency, combined with its strength, durability, and ability to be molded into various shapes, makes it an incredibly versatile material. Fun fact: did you know that glass is actually 100% recyclable? It can be melted down and reformed countless times without losing its quality. This makes it an environmentally friendly material, especially compared to plastics, which often end up polluting our oceans and landfills. Section 7. A glassy conclusion. More to discover. The next time you gaze through a window or sip from a glass, take a moment to appreciate the wonders of this seemingly simple material. Glass's transparency, a consequence of its unique atomic structure and its interaction with light, is a testament to the elegance and complexity of the natural world. And while we've uncovered some of the secrets behind glass's transparency, there's still much more to discover. Scientists are constantly developing new types of glass with enhanced properties, from self-cleaning windows to super strong glass that's thinner than a human hair. The future of glass, it seems, is as clear as ever.
Imagine a world without elevators. Skyscrapers wouldn't exist. Getting to your high-rise apartment would be a workout. Thankfully, we have elevators. These mechanical marvels are everywhere, silently moving millions of people every day. But where did it all begin? Believe it or not, the earliest elevators weren't for people. They were used in mines to haul heavy materials. Ancient Greeks and Romans had systems using ropes and pulleys, powered by humans or animals. It wasn't until the 1800s that elevators became safe and practical for human passengers. Elisha Otis, an American inventor, developed a safety brake that prevented elevators from plummeting if a cable broke. This invention revolutionized building design, making skyscrapers possible. Think about it. Elevators literally changed the shape of our cities. They allowed us to build upwards, creating the stunning skylines we see today. So how do these metal boxes carry us up dozens of floors, sometimes at incredible speeds? It's a question that might seem complex at first, but the underlying mechanics are quite fascinating and elegantly simple. The answer is surprisingly simple: a clever combination of counterweights, cables, and a powerful motor. These components work together seamlessly to create a system that is both efficient and reliable. Imagine a giant seesaw. On one end is the elevator car, and on the other end is a counterweight. This counterweight system is crucial for balancing the load and ensuring smooth operation. The counterweight is carefully calibrated to be slightly heavier than an empty elevator car. This precise calibration helps in minimizing the energy required to move the elevator. This means that it takes less energy to move the elevator up or down. The energy efficiency of this system is one of the reasons elevators can operate so smoothly and quickly. Connecting the car and counterweight are strong steel cables. These cables are designed to withstand immense tension and ensure the safety of the passengers. These cables loop over a large grooved wheel called a sheave. The sheave plays a pivotal role in the movement of the elevator. The sheave is connected to an electric motor. This motor is the powerhouse of the entire system, providing the necessary force to move the elevator. When the motor turns, the sheave rotates, moving the cables and lifting or lowering the elevator car. This synchronized movement is what allows elevators to function so effectively. It's like a high-tech version of a pulley system you might have used in a physics class. The principles are the same, but the scale and precision are much greater. Except instead of lifting a bucket of water, we're lifting tons of steel and people, smoothly and safely. This remarkable system is a testament to human ingenuity and engineering prowess. Let's get a little more scientific for a moment. Understanding the principles behind elevators can give us a deeper appreciation for the everyday marvels we often take for granted. Elevators are a fantastic example of basic physics principles in action, specifically Newton's laws of motion and the interplay of forces. They demonstrate how forces work together to create smooth and efficient movement. Gravity, of course, is the force pulling everything downwards, including the elevator car. This ever-present force is what makes the elevator descend when it's not being pulled up by the cables. The tension in the cables is the force pulling upwards, counteracting gravity. These cables are incredibly strong and are designed to handle the weight of the elevator car and its passengers. When the elevator is at rest, these forces are balanced, and you feel a normal sense of weight. This balance is crucial for the smooth operation of the elevator. When the elevator accelerates upwards, the tension in the cables increases, becoming stronger than gravity. This increased tension is what lifts the elevator car and its occupants. This is why you feel slightly heavier for a brief moment. The sensation is due to the increased force acting on your body. Conversely, when the elevator accelerates downwards, the tension decreases and you feel slightly lighter. This lighter feeling is because the force pulling you up is reduced. The counterweight plays a crucial role in managing these forces and making the system energy efficient. It balances the weight of the elevator car, reducing the load on the motor. Because it offsets the weight of the car, the motor doesn't have to work as hard, reducing energy consumption. This efficiency is key to the sustainable operation of modern elevators. Safety is paramount when it comes to elevators. These vertical transport systems are a marvel of modern engineering, designed to move people quickly and efficiently between floors. After all, we're traveling vertically at considerable speeds in a metal box. This makes the need for robust safety mechanisms even more critical. Thankfully, modern elevators have numerous safety features to prevent accidents. These features are meticulously designed and rigorously tested to ensure passenger safety. One crucial component is the brake system. This system is essential for controlling the elevator's movement and ensuring it stops precisely where it should. Elevators have multiple brakes that engage automatically if the car starts moving too fast. These brakes are a failsafe to prevent the elevator from accelerating uncontrollably. These brakes are usually located on the sheave and work by clamping down on the sides, stopping the rotation, and bringing the elevator to a halt. This mechanism is both simple and highly effective. Another critical safety feature is the governor. This device plays a vital role in monitoring and controlling the elevator's speed. The governor is a speed-sensing device that constantly monitors the elevator's velocity. It ensures that the elevator operates within safe speed limits. If the car exceeds a certain speed, the governor triggers the brakes and activates a safety system called the buffer system. This dual action is crucial for preventing accidents. The buffer system is essentially a large shock absorber located at the bottom of the elevator shaft. It acts as a final line of defense. If the brakes fail and the car plummets, the buffer system cushions the impact, preventing a catastrophic crash. This system is designed to absorb the energy of the falling car. Finally, elevators have emergency brakes inside the car itself. These brakes are an additional safety measure to ensure passenger security. These are usually activated by a button labeled Emergency Stop and are designed to stop the elevator immediately in case of an emergency. This feature gives passengers a way to halt the elevator if they feel unsafe. Elevator technology has come a long way since the days of simple rope and pulley systems. Modern elevators are marvels of engineering, incorporating advanced control systems, regenerative braking for energy efficiency, and even destination dispatch systems that group passengers heading to similar floors. In the future, we can expect to see even more innovative elevator designs. Some concepts include cable-free elevators that use magnetic levitation to move vertically and horizontally, and even space elevators that could transport people and cargo into orbit. Ever wondered how fast elevators can actually go? The speeds vary greatly depending on the building and the type of elevator. Standard elevators in residential buildings might travel at a leisurely 1 to 2 meters per second. However, high-speed elevators in skyscrapers can reach speeds of over 10 meters per second. That's like traveling the height of a 3-story building every second. The fastest elevators in the world can even reach speeds of over 20 meters per second, making them faster than some cars. Elevators are just one example of how physics is all around us, often in unexpected places. From the simple act of walking to the complex workings of smartphones, physics governs the world we live in. So next time you step into an elevator, take a moment to appreciate the science that makes it all possible. And who knows, maybe it will spark your curiosity to learn more about the fascinating world of physics.
Imagine trying to pinpoint the exact location of a tiny, fast-moving marble. Not so difficult, right? Now shrink that marble down to the size of an electron, a fundamental particle inhabiting the quantum realm. Suddenly our task becomes impossible. This isn't a matter of having better tools. It's a fundamental law of nature, Heisenberg's uncertainty principle. This principle states that we cannot simultaneously know both the exact position and momentum of a particle like an electron. The more precisely we try to measure one, the more uncertain the other becomes. This isn't just a limitation of our instruments, it's a fundamental truth about the nature of reality at the quantum level. Our everyday intuition about how the world works is rooted in classical physics. Objects have definite positions and speeds, and we can measure them with precision. However, as we delve into the microscopic world of atoms and subatomic particles, we enter the strange and counterintuitive realm of quantum mechanics. Here, the rules of classical physics break down. Particles like electrons don't behave like tiny marbles. They exhibit wave-like properties, existing in a haze of probability rather than definite locations. Heisenberg's uncertainty principle isn't just a quirk of quantum mechanics, it's a direct consequence of the wave-like nature of particles at this scale. The essence of Heisenberg's uncertainty principle is captured in a simple yet profound equation. This principle is one of the cornerstones of quantum mechanics, fundamentally altering our understanding of the microscopic world. The equation delta x times delta p is greater than or equal to h bar over 2 encapsulates a profound truth about the nature of reality. Here, delta x represents the uncertainty in a particle's position. In other words, it tells us how precisely we can know where a particle is at any given moment. Delta p, on the other hand, represents the uncertainty in its momentum, which is a measure of how precisely we can know the particle's motion and speed. And h bar, or h, is a fundamental constant known as Planck's constant, which plays a crucial role in the quantum world. This equation tells us that the product of these uncertainties must always be greater than or equal to a very small but finite value. This is not just a mathematical curiosity, it has real implications for how we understand the universe. This means that if we shrink the uncertainty in position, delta x, towards 0, the uncertainty in momentum, delta p, blows up to infinity, and vice versa. This reciprocal relationship is a fundamental aspect of quantum mechanics. The more precisely we try to measure one property, the less precisely we can know the other. This inherent limitation is not due to flaws in our measurement tools, but is a fundamental property of nature itself. We can never know both with perfect accuracy at the same time. This principle challenges our classical intuitions and forces us to rethink what we know about the fabric of reality. It is a humbling reminder of the limits of human knowledge and the mysteries that still lie beyond our grasp. To grasp the strangeness of quantum uncertainty, let's compare it to a familiar classical example. Classical physics, the realm of Newton and Einstein, operates on principles that are intuitive and predictable. It's a world where objects follow clear, deterministic paths, and where cause and effect are straightforward and observable. Imagine trying to track a tennis ball's trajectory. You can see it, measure it, and predict where it will land with great accuracy. In classical physics, we can simultaneously measure the ball's position and momentum with high precision. This means we know exactly where the ball is and how fast it's moving at any given moment. Using this information, we can predict its future path with remarkable accuracy. The equations of motion allow us to forecast its trajectory, accounting for factors like gravity and air resistance. Now let's shrink the tennis ball down to the size of an electron. Here, the rules of classical physics no longer apply. We enter the realm of quantum mechanics where particles behave in ways that defy our everyday experiences. If we try to pinpoint the electron's position with a photon of light, the very act of observation disrupts its momentum. This is due to the Heisenberg uncertainty principle, which states that the more precisely we know one property, like position, the less precisely we can know another, like momentum. Conversely, if we measure its momentum accurately, we lose track of its position. This trade-off is not due to technological limitations, but is a fundamental aspect of nature at the quantum level. This inherent fuzziness is a fundamental characteristic of the quantum world, not a reflection of our measurement limitations. It challenges our classical intuitions and forces us to rethink the nature of reality itself. Quantum mechanics reveals a universe that is probabilistic rather than deterministic, where certainty is replaced by a spectrum of possibilities. Section 5. The Observer. Effect does looking change reality? The act of measurement in quantum mechanics isn't a passive observation. It's an active participation that inevitably affects the system being observed. This means that the very act of looking at something on a quantum level changes its behavior. Unlike classical physics, where measurements can be made without disturbing the system, quantum mechanics tells us that the observer and the observed are intrinsically linked. This is known as the observer effect. It's a phenomenon that has puzzled scientists and philosophers alike for decades. The observer effect challenges our understanding of reality, suggesting that reality itself is not fixed but is influenced by our observations. When we try to measure an electron's position or momentum, we are forced to interact with it, typically using photons of light. These photons are not just passive carriers of information. They actively engage with the electron, altering its state in the process. However, these photons carry energy and momentum, which they transfer to the electron during the interaction. This transfer of energy and momentum is not negligible. It has significant consequences for the electron's behavior. This transfer inevitably alters the electron's momentum and position, introducing uncertainty into our measurements. This uncertainty is not due to any flaw in our measuring instruments, but is a fundamental aspect of quantum mechanics, encapsulated in Heisenberg's uncertainty principle. This isn't just a matter of clumsy measurement, it's a fundamental consequence of the quantum nature of both the observer and the observed. The observer effect forces us to rethink our notions of reality, suggesting that at the quantum level, the universe is a dynamic interplay between the observer and the observed, where the act of observation itself is a form of interaction that shapes the very fabric of reality. Section 6. Wave-particle duality, the electron's two faces. To further understand the uncertainty principle, we need to embrace the strange concept of wave-particle duality. In the quantum realm, particles like electrons don't behave like tiny solid balls. Instead, they exhibit a dual nature, behaving like waves and particles, depending on how we observe them. When we measure an electron's position, we force it to collapse from its wave-like state into a particle-like state, localizing it at a specific point in space. However, this localization comes at a price. We lose information about its momentum. Conversely, when we measure its momentum, we emphasize its wave-like nature, making its position more uncertain. Section 7. Implications of uncertainty, from microscopes to quantum computers. Heisenberg's uncertainty principle isn't just an esoteric concept confined to theoretical physics. It has profound implications for technology and our understanding of the universe. For example, it sets limits on the resolution of electron microscopes, which use beams of electrons to image tiny objects. The uncertainty principle also plays a crucial role in quantum computing. Quantum bits, or qubits, exploit the superposition principle where a particle can exist in multiple states simultaneously. However, the uncertainty principle limits how precisely we can manipulate these qubits, presenting challenges for building reliable quantum computers. Section 8. Beyond misconceptions. It's not about our instruments. It's tempting to dismiss the uncertainty principle as a limitation of our measurement tools. However, this is a misconception. It's not that we lack precise enough instruments. It's that the very act of measurement at the quantum level inherently introduces uncertainty. Even with hypothetical, infinitely precise instruments, we would still encounter the uncertainty principle. It's not a reflection of our technological limitations, but a fundamental feature of the quantum world, a world where certainty gives way to probability and fuzziness. Section 9. Embracing the unknown, a quantum leap in understanding. Heisenberg's uncertainty principle, at first glance, seems like a frustrating limitation on our knowledge. However, it's actually a doorway to a deeper understanding of the universe. It challenges our classical intuitions and forces us to embrace the probabilistic nature of reality at the quantum level. This principle reminds us that the universe is full of surprises, and our quest to unravel its secrets is an ongoing journey. By letting go of our need for absolute certainty, we open ourselves to the wonders of the quantum world, a world where uncertainty reigns and the impossible becomes possible.
Section 1. A galaxy far, far away. But could it be real? Lightsabers, the iconic weapon of the Jedi and Sith. These elegant weapons of light have captivated audiences for generations. But could we ever build a real lightsaber? The answer, like many things in science, is complicated. To understand the challenges, we need to delve into the science behind lightsabers. We'll explore the nature of plasma, the power of magnetic fields, and the immense energy requirements of such a device. Fasten your seatbelts, science fans, as we journey into the fascinating world of lightsabers and explore the possibility of bringing this science fiction fantasy into reality. Section 2. Plasma, the fourth state of matter. We all know about solids, liquids, and gases. But have you heard of plasma? Plasma is often called the fourth state of matter. It's what happens when you heat a gas so much that its atoms lose some of their electrons, becoming electrically charged. Think of the sun. The sun is essentially a giant ball of hot plasma. Lightning is another example of plasma here on Earth. Plasma is all around us, even if we don't always realize it. Scientists have been studying plasma for decades. We use it in various technologies, like those fancy plasma TVs and those super hot plasma torches that can cut through metal. Yes, you read that right. Plasma can be incredibly hot and powerful. Section 3. Magnetic fields, an invisible force. Now let's talk about magnetic fields. These invisible forces are all around us, yet we often don't notice them in our daily lives. You've probably played with magnets before. Remember how they could stick to your fridge or push each other away? You know they can attract or repel each other even without touching. This fascinating behavior is due to the magnetic fields they generate. That's because magnets create invisible fields around them called magnetic fields. These fields are like invisible lines of force that extend out from the magnet. These fields can interact with electrically charged particles like those found in plasma. Plasma is a state of matter similar to gas, but with charged particles. Think of it like an invisible hand that can push and pull on plasma. This interaction can be harnessed in various ways. If we can create a strong enough magnetic field, we might be able to contain and shape plasma much like a lightsaber blade. This concept is both exciting and challenging. This idea of using magnetic fields to contain plasma isn't just science fiction. It's a real scientific endeavor with significant potential. Scientists are experimenting with this right now in nuclear fusion research. They are working tirelessly to make this a reality. They're trying to create miniature suns here on Earth by using powerful magnetic fields to contain and control extremely hot plasma. This could revolutionize energy production. The goal is to generate clean and sustainable energy. If successful, this could provide a nearly limitless source of power for future generations. Section 4. Powering the plasma blade. Okay, so let's say we could create a blade of plasma and contain it with a magnetic field. There's still one big problem: energy. Lightsabers require an enormous amount of energy to function. Think about it. A lightsaber can cut through almost anything and deflect blaster bolts. That takes a lot of power. We're talking about energy levels far beyond what our current batteries can provide. Some scientists have theorized that a compact fusion reactor could potentially power a lightsaber. After all, fusion is the process that powers the sun. However, fusion technology is still in its early stages of development, and building a reactor small enough to fit in a lightsaber's hilt is a monumental challenge. Section 5. Real-world lightsabers? Not quite. So, where do we stand with real-life lightsabers? The idea of wielding a lightsaber, much like the Jedi in Star Wars, is a dream for many. But how close are we to making this dream a reality? While we've made remarkable progress in plasma physics and magnetic field manipulation, we're still a long way off. The science behind creating a blade of pure energy that can cut through almost anything is incredibly complex. The energy requirements alone are a major hurdle. To generate and sustain a plasma blade, we'd need a portable power source far beyond our current capabilities. However, that doesn't mean we can't draw inspiration from the iconic weapon. Engineers and scientists are constantly looking to science fiction for ideas that can be translated into real-world technology. Remember those plasma torches I mentioned earlier? These tools are already in use in various industries and are a testament to the power of plasma. Those are essentially miniaturized plasma jets. They operate at extremely high temperatures and can cut through metal with ease, showcasing the potential of plasma technology. They're not quite lightsabers, but they demonstrate the power and potential of plasma technology. The principles behind these tools could one day lead to more advanced applications. Furthermore, advancements in superconducting materials, which can conduct electricity with zero resistance, could make it easier to generate and control the strong magnetic fields needed to contain plasma. This is a crucial step towards creating a stable plasma blade. So, while a fully functional lightsaber may remain a fantasy for now, the underlying technologies are areas of active research with potential real-world applications. The journey to a real lightsaber is ongoing, and who knows what the future holds. Section 6. The challenges of lightsaber construction. Building a lightsaber presents numerous engineering challenges beyond just the power source. The complexity of the design requires a deep understanding of advanced physics and engineering principles. Creating a blade that can extend and retract on command would be incredibly complex. The mechanism must be both reliable and durable, capable of withstanding intense use without failure. You'd need a mechanism to generate the plasma, project it a certain distance, and then retract it safely, all at the flick of a wrist. This requires precise control over the plasma's properties and behavior. Then there's the issue of heat dissipation. Managing the immense heat generated by the plasma blade is crucial to ensure the device's safety and functionality. A lightsaber generates an immense amount of heat. This heat must be effectively managed to prevent damage to the device and ensure the user's safety. Without proper heat shielding, the hilt would become dangerously hot, potentially melting the handle or even harming the user. Advanced materials and cooling systems are essential to address this challenge. Furthermore, the interaction of the lightsaber blade with its surroundings would be difficult to manage. The blade's energy must be controlled to prevent unintended damage. A lightsaber that cuts through everything would be incredibly dangerous and impractical. Safety mechanisms must be in place to ensure it can be used without causing unintended harm. You'd need some way to control its cutting power, perhaps by adjusting the plasma temperature or intensity. This level of control would allow for precise and safe operation, making the lightsaber a practical tool rather than a hazardous weapon. Section 7. The Future of Lightsabers, A Distant Hope. While a true lightsaber, as depicted in science fiction, remains a distant possibility, the pursuit of such a technology could lead to exciting scientific breakthroughs. Advancements in plasma physics, magnetic field manipulation, and energy storage could have far-reaching applications in various fields, from medicine to manufacturing to energy production. Perhaps one day, we will have technologies that resemble lightsabers in some form or another, but for now they remain a product of our imagination, inspiring us to push the boundaries of science and technology. So keep dreaming, keep questioning, and who knows what the future holds. The journey of scientific discovery is often more exciting than the destination itself.
Light is fascinating. It's one of the most intriguing phenomena in the universe, captivating scientists and laypeople alike for centuries. From the way it illuminates our world to the mysteries it holds at the quantum level, light is a subject of endless wonder and study. It can act like a wave. This wave-like behavior of light can be observed in various phenomena such as interference and diffraction. When light waves overlap, they can create patterns of constructive and destructive interference, much like ripples on a pond. It can also act like a particle. These particles, known as photons, are the smallest units of light. They travel in straight lines and can be absorbed or emitted by atoms, leading to the various colors and intensities of light we see. This dual nature is key to understanding lasers. Lasers rely on the precise control of light's wave and particle properties to produce coherent, focused beams of light that can be used in everything from cutting-edge medical procedures to everyday barcode scanners. Think of waves on the ocean. Just as ocean waves can vary in height and frequency, light waves can vary in wavelength and amplitude. These variations determine the light's color and intensity. They have peaks and troughs. The distance between these peaks and troughs is known as the wavelength, and it's a crucial factor in determining the properties of light. Light waves are similar, carrying energy. This energy can be transferred to other objects, causing them to heat up or even emit light themselves. This is why sunlight feels warm on your skin, and why certain materials glow under ultraviolet light. Now, imagine tiny packets of light energy. These packets, or photons, are like little bundles of energy that travel through space at the speed of light. Each photon carries a specific amount of energy, which is related to its wavelength. These are photons, the particles of light. Photons are responsible for the photoelectric effect, where light striking a material can eject electrons from it. This effect is the basis for many modern technologies, including solar panels and light sensors. Each photon has a specific amount of energy. This energy determines the color of the light, with higher energy photons corresponding to blue or violet light, and lower energy photons corresponding to red or orange light. This energy determines the color of the light. When light passes through a prism, it is separated into its component colors, revealing the spectrum of visible light from red to violet. Understanding both aspects of light is crucial. By studying light's wave and particle properties, scientists can develop new technologies and deepen our understanding of the universe. This dual nature of light is a fundamental concept in physics. bridging the gap between classical and quantum theories. It's like having two keys to unlock the secrets of lasers. With these keys, we can harness the power of light in ways that were once thought impossible, opening up new possibilities in science, medicine, and technology. Atoms are the building blocks of everything around us. They are the fundamental units of matter, the smallest pieces that retain the properties of an element. Everything you see, touch, and even breathe is made up of atoms. These tiny particles are so small that millions of them could fit on the head of a pin. They are incredibly small, but they hold the key to lasers. Lasers, which stand for light amplification by stimulated emission of radiation, rely on the unique properties of atoms to produce coherent light. This light is used in countless applications, from cutting-edge medical procedures to everyday items like barcode scanners. Imagine an atom as a tiny solar system. Just as planets orbit the sun, electrons orbit the nucleus of an atom. This model helps us understand the structure and behavior of atoms, even though the reality is much more complex. At the center is the nucleus. The nucleus is composed of protons and neutrons, which are held together by the strong nuclear force. This force is one of the four fundamental forces of nature and is incredibly powerful, keeping the nucleus intact despite the repulsive forces between the positively charged protons. Electrons orbit the nucleus like planets around a star. These electrons are negatively charged and are attracted to the positively charged nucleus, creating a balance that keeps the atom stable. The way electrons move and interact with the nucleus is governed by the principles of quantum mechanics. These electrons occupy specific energy levels, like steps on a ladder. Each energy level corresponds to a certain amount of energy, and electrons can move between these levels by absorbing or releasing energy. This quantized nature of energy levels is a fundamental concept in quantum mechanics. An electron can jump to a higher step by absorbing energy. This energy can come from various sources, such as heat, light, or electrical energy. When an electron absorbs enough energy, it moves to a higher energy level, temporarily leaving its original state. When it jumps back down, it releases that energy as light. This process is known as spontaneous emission, and the light emitted can be in the form of visible light, ultraviolet light, or other types of electromagnetic radiation, depending on the energy difference between the levels. The color of light emitted depends on the energy difference between the levels. Different elements emit different colors of light when their electrons transition between energy levels, which is why we see a variety of colors in fireworks and neon signs. This phenomenon is also used in spectroscopy to identify the composition of distant stars and galaxies. This process is fundamental to how lasers work. In a laser, atoms are excited to higher energy levels, and when they return to their lower energy states, they emit light in a highly organized and coherent manner. This coherent light is what makes lasers so powerful and precise, enabling their use in a wide range of technologies and scientific research. Imagine an electron in an excited state, sitting on a higher energy level step. Now, a photon comes along carrying the same amount of energy as the gap between the steps. This triggers the excited electron. The electron jumps down to the lower energy level. In the process, it releases a new photon. This new photon is an exact copy of the one that triggered it. They have the same energy, direction, and phase. This process is called stimulated emission, and it is the heart of laser technology. The laser medium is a material that can amplify light through stimulated emission. It could be a gas, a crystal, or even a semiconductor. The medium is chosen specifically for its energy levels. When a photon enters the medium, it triggers a chain reaction. One photon becomes two, two become four, and so on. The light amplifies exponentially as it travels through the medium. This amplification is what makes lasers so powerful. It takes a weak beam of light and turns it into an intense, concentrated beam. Section 5. The laser cavity, a hall of mirrors. The laser cavity is where the magic happens. This is the heart of the laser, the place where light transforms into a powerful, coherent beam. Imagine a small chamber, meticulously designed to amplify light through a process known as stimulated emission. This chamber is what we call the laser cavity. It consists of the laser medium placed between two mirrors. The laser medium can be a gas, liquid, or solid, depending on the type of laser. This medium is crucial, as it is the source of the photons that will eventually form the laser beam. One mirror is highly reflective, while the other allows some light to pass through. The highly reflective mirror ensures that most of the light bounces back into the medium, while the partially reflective mirror lets a small portion of the light escape as the laser beam. The photons bounce back and forth between the mirrors, passing through the laser medium repeatedly. Each time they pass through the medium, they stimulate the emission of more photons, amplifying the light. With each pass, more photons are created through stimulated emission. This process is what makes the light in a laser so intense and coherent. Stimulated emission is a phenomenon where an incoming photon causes an excited electron to drop to a lower energy level, releasing a new photon in the process. The result is a highly directional, coherent beam of light. This means that the light waves are all in phase and travel in the same direction, making the laser beam extremely focused and powerful. This means all the photons have the same wavelength, phase, and direction, a unique property of laser light. This coherence is what allows lasers to be used in a wide range of applications, from cutting and welding to medical procedures and communication technologies. The laser cavity with its hall of mirrors is truly a marvel of modern science. Section 6. Types of lasers. A spectrum of innovation. There are many types of lasers, each with unique properties and applications. Gas lasers, like helium neon lasers, are common and affordable. Solid-state lasers, like ruby lasers, are more powerful and used in industry. Semiconductor lasers, or diode lasers, are tiny and energy efficient. These are found in everything from barcode scanners to laser pointers. Each type of laser has its own strengths, making them suitable for different tasks. The possibilities are constantly expanding with new research and development. Section 7. Applications of lasers from science to surgery. Lasers have revolutionized numerous fields. In medicine, they are used for delicate surgeries like eye surgery and tumor removal. Their precision allows for minimally invasive procedures. In industry, lasers cut and weld materials with incredible accuracy. They are used in manufacturing, telecommunications, and even space exploration. Lasers have also become essential tools in scientific research, enabling us to study the world at the atomic level. Section 8. Lasers in our lives, an invisible revolution. Lasers are everywhere, even if we don't always see them. They are in our homes, powering CD and Blu-ray players. They are in supermarkets, scanning barcodes at checkout. They are even used in fiber optic cables, transmitting vast amounts of data at the speed of light. Lasers have become an indispensable part of our modern world. From entertainment to communication, lasers have transformed the way we live, work, and interact with the world around us. Section 9. The future of lasers, limitless potential. The future of lasers is bright, with limitless potential. Researchers are constantly developing new types of lasers with enhanced properties and capabilities. These advancements will lead to even more innovative applications in fields like medicine, energy, and computing. Lasers have come a long way since their invention. As we continue to unlock their secrets, we can expect even more groundbreaking discoveries and advancements in the years to come. For centuries, humanity clung to the idea of a static, unchanging universe. The stars, fixed points of light, reinforced this notion. Great minds like Aristotle and Ptolemy envisioned a geocentric cosmos. This model held sway for over a millennium. During the Renaissance, Copernicus challenged this view. His heliocentric model shifted our perspective. Earth became just another planet in orbit. The universe, as we now know, is far from static. It's a dynamic, ever-evolving entity. Imagine the sound of a car racing towards you. The pitch of the engine seems to rise as it approaches, then drops as it speeds away. This change in pitch, known as the Doppler effect, isn't just an auditory phenomenon. It applies to light waves as well. Just as sound waves compress as an object approaches, causing a higher pitch, light waves from an approaching object get compressed, shifting towards the blue end of the spectrum. This is called blue shift. Conversely, as an object moves away, light waves stretch, shifting towards the red end of the spectrum, known as redshift. Now imagine this phenomenon on a cosmic scale. Astronomers using powerful telescopes observed that light from distant galaxies exhibited a distinct redshift. This redshift indicated that these galaxies were moving away from us. The farther the galaxy, the greater the redshift, and consequently, the faster it seemed to be receding. Enter Edwin Hubble, an American astronomer who revolutionized our understanding of the cosmos. In the 1920s, using the powerful Hooker telescope at Mount Wilson Observatory, Hubble meticulously measured the distances and redshifts of numerous galaxies. His findings, published in 1929, sent shockwaves through the scientific community. Hubble discovered a direct correlation between a galaxy's distance and its redshift. This relationship, now known as Hubble's law, provided the first concrete evidence that the universe is expanding. It wasn't that galaxies were flying away from us through space. Rather, the very fabric of space itself was stretching, carrying galaxies along for the ride. Imagine baking a raisin bread, with each raisin representing a galaxy. As the dough bakes and expands, the raisins move farther apart. Similarly, as the universe expands, the space between galaxies increases, causing them to recede from one another. Section 4. Echoes of the Big Bang, the cosmic microwave background. If the universe is expanding, logic suggests that it must have been smaller and denser in the past. Extrapolating backwards, scientists theorized that the universe originated from an incredibly hot, dense state, the Big Bang. This theory, while groundbreaking, needed further validation. The missing piece of the puzzle arrived serendipitously in 1964. Arno Penzias and Robert Wilson, two radio astronomers at Bell Telephone Laboratories, stumbled upon a faint, persistent hum emanating uniformly from all directions of the sky. This hum, after careful analysis, turned out to be the afterglow of the Big Bang itself, the cosmic microwave background, or CMB radiation. Think of the CMB as the faint echo of the universe's explosive birth. This radiation, emitted just 380,000 years after the Big Bang, has been traveling through the cosmos ever since, its wavelength stretched by the expansion of space into the microwave region of the electromagnetic spectrum. The discovery of the CMB provided compelling evidence for the Big Bang theory, transforming it from a radical idea into the prevailing model of the universe's origin. Section 5. The Accelerating Cosmos, a universe picking up speed. The discovery of the expanding universe was just the beginning. In the late 1990s, two independent teams of astronomers studying distant supernovae made a startling finding. The expansion of the universe wasn't constant, it was accelerating. This discovery, which earned the 2011 Nobel Prize in Physics, shook the foundations of cosmology. The prevailing theory had been that the gravitational pull of matter in the universe would gradually slow down the expansion. Instead, the expansion was speeding up, as if some unknown force was counteracting gravity, pushing everything farther and faster apart. This mysterious force, dubbed dark energy, remains one of the most profound enigmas in modern science. It's estimated that dark energy makes up roughly 68% of the total energy density of the universe, while dark matter, another mysterious component, accounts for about 27%. This leaves a paltry 5% for all the normal matter we observe: stars, planets, galaxies, and even ourselves. Section 6. Unveiling the Future, Dark Energy, and the Unknown. The discovery of the accelerating universe and the enigmatic nature of dark energy have profound implications for the fate of the cosmos. Will the expansion continue to accelerate indefinitely, leading to a big rip where even atoms are torn apart? Or will dark energy's influence wane over time, perhaps allowing gravity to regain control and pull the universe back together in a big crunch? These questions remain at the forefront of cosmological research. Scientists are actively pursuing various lines of inquiry, from studying distant supernova to mapping the large-scale structure of the universe, in hopes of unraveling the mysteries of dark energy and its ultimate influence on the cosmos. The study of the expanding universe is a journey into the unknown, a quest to comprehend the fundamental forces shaping our cosmos. It's a testament to human curiosity and our insatiable desire to understand our place in the grand tapestry of the universe. Section 7. Cosmic Curiosity, the Never-Ending Quest. The exploration of the expanding universe stands as a testament to the power of human curiosity and our relentless quest to comprehend the cosmos. From ancient astronomers gazing at the night sky to modern-day scientists probing the depths of space with sophisticated telescopes, our fascination with the universe has been a constant driving force in our intellectual evolution. The discovery of the expanding universe, redshift, and the cosmic microwave background radiation has revolutionized our understanding of the cosmos. These groundbreaking findings have not only reshaped our scientific worldview, but have also ignited our imaginations, prompting us to ponder the ultimate fate of the universe and our place within its grand design. As we delve deeper into the mysteries of dark energy and the accelerating expansion, we embark on a journey of discovery that promises to reveal even more astonishing truths about the nature of our universe. The quest to understand the cosmos is a never-ending adventure, one that will continue to inspire and challenge us for generations to come. Imagine standing on a street corner as a fire truck races towards you, its siren blaring. The sound is intense, almost overwhelming as it echoes off the buildings around you. As the truck approaches, the siren's pitch sounds higher, more urgent. It's a sound that demands attention, signaling the urgency of the situation. Then, as the truck speeds past and disappears down the street, the siren's pitch noticeably drops. The sound becomes less intense, fading into the distance. This change in pitch, this auditory shift, is not a trick of the mind. It's a real, measurable phenomenon. It's the Doppler effect in action, a fundamental phenomenon that governs how we perceive waves, both in sound and light. This effect is crucial in many fields of science and technology. The Doppler effect shapes our everyday experience of sound more than we realize. It influences how we interpret the world around us. Whether it's the changing pitch of a passing car horn or the altered tone of a train whistle as it rumbles by, these auditory cues provide us with valuable information about the movement of objects around us. They help us understand speed, distance, and direction. But the Doppler effect's reach extends far beyond our terrestrial soundscape. It plays a crucial role in astronomy and the study of the cosmos. It stretches across the vast expanse of space, revealing profound truths about the universe we inhabit. Through the Doppler effect, we can measure the movement of stars and galaxies, unlocking the secrets of the cosmos. The Doppler effect, named after Austrian physicist Christian Doppler, who first described it in 1842, describes the change in frequency of a wave as its source moves relative to an observer. This phenomenon is not only limited to sound waves, but can also be observed in light waves and other types of waves. When a source of waves, like a siren, moves towards an observer, the waves are compressed, leading to a higher observed frequency. This is why a siren sounds higher pitched as it approaches you. Conversely, when the source moves away, the waves are stretched, resulting in a lower observed frequency. This explains why the siren's pitch drops as it moves away from you. This relationship between frequency, speed, and the observed shift in waves can be expressed mathematically, where f is the observed frequency, which is what the observer actually hears or detects. F is the actual frequency, the true frequency of the source when it is stationary. V is the speed of sound in the medium, which can vary depending on factors like temperature and medium type. Vo is the velocity of the observer relative to the medium, positive if moving towards the source, affecting how the frequency is perceived. Versus is the velocity of the source relative to the medium, positive if moving towards the observer, influencing the compression or stretching of the waves. This equation captures the essence of the Doppler effect, demonstrating how the observed frequency of a wave changes depending on the relative motion between the source and the observer. It is a fundamental concept in physics with applications in various fields, from astronomy to medical imaging. The Doppler effect's influence extends beyond the roar of sirens and the rumble of trains. It is a fundamental principle that affects many aspects of our daily lives. It underpins a variety of technologies we rely on every day, from communication devices to medical equipment. One prominent example is the radar speed gun used by law enforcement to track vehicle speeds and ensure road safety. These devices emit radio waves that bounce off moving vehicles, allowing officers to monitor traffic effectively. By measuring the change in frequency of the reflected waves, the radar gun can accurately determine the speed of the vehicle, ensuring compliance with speed limits. In the medical field, the Doppler effect finds crucial application in Doppler ultrasound, a vital diagnostic tool. This non-invasive imaging technique uses sound waves to create images of blood flow through blood vessels, aiding in the diagnosis of various conditions. By analyzing the frequency shifts in the reflected ultrasound waves, doctors can diagnose a range of conditions, from blood clots to heart valve problems, enhancing patient care. These are just a few examples of how the Doppler effect, a seemingly simple concept, has profound implications for technology and our understanding of the world around us, shaping the way we live and interact with our environment. Section 4. Redshift and blueshift. The Doppler effect in light. The Doppler effect, while initially conceived for sound waves, applies equally to light waves, albeit with a crucial difference. Unlike sound, which requires a medium like air or water to travel, light can travel through the vacuum of space. As a result, the Doppler effect for light depends on the relative velocity between the source of light and the observer, not on their motion relative to a medium. When a source of light, like a star, moves towards an observer, the light waves are compressed, shifting towards the blue end of the electromagnetic spectrum. This phenomenon is known as blue shift. Conversely, when a star moves away from an observer, its light waves are stretched, shifting towards the red end of the spectrum, a phenomenon called redshift. Section 5. Cosmic clues. Unraveling the universe with redshift. Redshift in particular has revolutionized our understanding of the cosmos. By analyzing the light from distant galaxies, astronomers discovered that the vast majority of galaxies exhibit redshift, indicating that they are moving away from us. This observation forms the cornerstone of the Big Bang theory, the prevailing cosmological model for the universe's origin and evolution. The farther a galaxy is from us, the faster it appears to be receding, a relationship described by Hubble's law. This law, formulated by astronomer Edwin Hubble in the 1920s, provided the first observational evidence for an expanding universe. The redshift of distant galaxies is not merely a consequence of their motion through space. It's a testament to the very fabric of space-time stretching and expanding over cosmic timescales. Section 6. The Expanding Universe. Echoes of the Big Bang. The discovery of redshift and the expanding universe fundamentally altered our perspective on the cosmos and its origins. It suggests that the universe was once much smaller and denser than it is today, originating from an incredibly hot, dense state billions of years ago, the Big Bang. The cosmic microwave background radiation, a faint afterglow of the Big Bang, provides further compelling evidence for this model. This radiation, discovered in 1964, exhibits a uniform redshift, indicating that it originated from a time when the universe was much hotter and denser, consistent with the predictions of the Big Bang theory. Section 7. Conclusion. A universe in motion. The Doppler effect, a seemingly simple concept observed in the changing pitch of a siren, has unlocked profound truths about the universe we inhabit. From radar speed guns to Doppler ultrasound, its applications have revolutionized technology and medicine. Yet its most profound impact lies in its ability to unravel the secrets of the cosmos. Redshift, the stretching of light waves from distant galaxies, provides compelling evidence for an expanding universe, a universe born from the cataclysmic explosion of the Big Bang. As we continue to explore the universe, the Doppler effect will undoubtedly remain an invaluable tool, helping us decipher the symphony of light and motion that shapes the cosmos. From the moment we open our eyes, we are bathed in light. It illuminates our world, revealing a tapestry of colors, shapes, and movements. But what exactly is this ethereal phenomenon that allows us to perceive the universe around us? This fundamental question has captivated scientists and philosophers for centuries, leading to a profound exploration of light's true nature. The ancient Greeks pondered the nature of light, with some believing it to be composed of tiny particles emitted from our eyes. Others, like the philosopher Empedocles, proposed that light traveled as waves, similar to the ripples on the surface of a pond. However, it wasn't until the scientific revolution that a more rigorous investigation into the properties of light began. The stage was set for a scientific duel, a clash of titans that would forever change our understanding of the cosmos. Two competing theories emerged, each seeking to explain the mysteries of light, the wave theory and the particle theory. Like two sides of a cosmic coin, these theories would shape our scientific understanding, leading us on a journey of discovery and wonder. In the late 17th century, Dutch scientist Christian Huygens put forth a compelling argument for the wave-like nature of light. Huygens proposed that light travels outward from a source in a series of expanding spheres, much like ripples spreading from a stone thrown into a pond. This became known as Huygens's principle. Huygens's wave theory elegantly explained several observed properties of light, such as reflection and refraction. Reflection, the bouncing of light off a surface, could be understood as waves bouncing off a barrier. Refraction, the bending of light as it passes from one medium to another, could be explained by the change in speed of the light waves. However, Huygens's theory faced a significant challenge. It couldn't explain the phenomenon of diffraction. Diffraction refers to the bending of light waves around obstacles, causing them to spread out. It was not until the early 19th century that a crucial experiment would solidify the wave theory's place in the scientific landscape. Sir Isaac Newton, a towering figure of the scientific revolution, proposed an alternative theory of light. Newton believed that light was composed of tiny, weightless particles that he called corpuscles. According to his corpuscular theory, these particles traveled in straight lines and interacted with matter like tiny billiard balls. Newton's theory could readily explain reflection and refraction. Reflection was simply the bouncing of corpuscles off a surface, while refraction was explained by the change in speed and direction of the corpuscles as they passed from one medium to another. Furthermore, Newton's reputation and the elegance of his theory led to its widespread acceptance for over a century. The wave theory, lacking a definitive explanation for diffraction, remained overshadowed. However, the tide was about to turn, ushering in a new era of understanding about the nature of light. Section 4. Einstein, Planck, and the Quantum Revolution. As the 19th century ended, cracks appeared in classical physics. Phenomena like blackbody radiation and the photoelectric effect challenged the wave theory of light. In 1900, Max Planck proposed quantum theory to explain blackbody radiation. Planck suggested energy is emitted in discrete packets called quanta. This idea challenged the classical view of energy as a continuous wave. In 1905, Einstein explained the photoelectric effect using Planck's quantum theory. Light shining on a metal surface causes electron emission, unexplained by wave theory. Einstein proposed light exists as discrete packets called photons. These discoveries shattered classical physics, revealing a stranger universe. Light was not simply a wave or a particle, but more enigmatic. Section 5. Wave-particle duality, light's strange secret. The early 20th century witnessed a paradigm shift in our understanding of light. It became increasingly clear that light exhibited a bewildering dual nature, behaving as both a wave and a particle depending on the experiment and the way it was observed. This wave-particle duality, as it came to be known, challenged the very foundations of classical physics. In 1924, Louis de Broglie proposed a revolutionary idea. If light, a wave, could also behave like a particle, then perhaps particles like electrons could also exhibit wave-like properties. This radical notion, known as de Broglie's hypothesis, was experimentally confirmed a few years later, further blurring the lines between the macroscopic world of our everyday experience and the bizarre, counterintuitive realm of quantum mechanics.